Good morning, everyone. I am Mudrika, a professor in the Department of Material Science and Metallurgical Engineering at IIT Hyderabad, and it is my pleasure to welcome you all here to celebrate the Crystal Year celebration for Carbon Lab. I also welcome all the viewers online who have joined us here. The journey of Carbon Lab at IIT Hyderabad, a laboratory that truly embodies the spirit of C for creative, A for advanced, R for research, B for based on nanomaterials, carbon, built on the pillars of research, teamwork, innovation, collaboration. The lab has steadily evolved into a vibrant hub of interdisciplinary scientific endeavors. The journey of Carbon Lab began in 2011 with a vision to harness the potential of carbon in its most versatile form, be it ranging from nanofibers, films, to complex hierarchical structures. Over time, this vision has expanded into a broad research portfolio that addresses critical challenges not only at national level but at global level as well, which encompasses energy, healthcare, environment, sensing, and so on. The lab has made significant contribution to the development of advanced energy storage systems, including metal ion batteries, metal sulfur, metal carbon dioxide batteries, and so on. Not just energy storage systems, but the lab has also made contribution in the area of healthcare, female hygiene, oil spillage remediations, and so on. What makes Carbon Lab truly distinctive is its approach in identifying the societal and global challenges and working on them with a lot of collaborations. And the signature of that is all the people sitting here. We have students, alumni, collaborators, well-wishers, mentors, and all the people who have facilitated the Carbon Lab in its entire journey of last 15 years. Organizing this 15th year of Carbon Lab as Crystal Anniversary in the form of Summit itself is an example of out-of-the-box thinking, which is led by Professor Chandrasekhar Sharma, and of course felicitated and facilitated by his students. It's my privilege also as a collaborator, friend, and a well-wisher to welcome you all here on this day. Without further delay, let me introduce our chief guest as well as guest of honor. Our chief guest today is Dr. R. Vijay, Director ARCI Hyderabad, and our guest of honors are Professor U.B. Desai, Founding Director IIT Hyderabad and Vice President INSA, Dr. Tata Narsingh Rao, Vice Chairman Sri Venkateshwara University, Tirupati, and Professor G.N. Shastri, Dean Sponsored Research and Consultancy at IIT Hyderabad. May I please invite all our distinguished guests, along with Professor Chandrasekhar Sharma, to kindly grace the dais. Can we welcome them by a huge round of applause? I extend heartfelt gratitude for sparing out time to be here with us to celebrate this journey. We'll start with the lighting of the lamp, as the light signifies knowledge, and that's what has been trying as an effort of Carbon Lab. I request all our guests to kindly join Professor Chandrasekhar Sharma to light the lamp. I request Parnika to kindly sing Saraswati Vandana alongside.
या कुन्देन्दु तुषारहार धवला या शुभ्रवस्त्रान्विता या वीणा वरदण्ड मण्डितकरा या श्वेत पद्मासना या ब्रह्माच्युत शङ्कर प्रभृतिभिर् देवै सदा पूजिता सा मां पातु सरस्वती भगवती निःशेष जाड्यापः।
Thank you, Parnika. Now I invite Professor Chandrasekhar Sharma, the inventor, creator, and the founder of Carbon Lab, to kindly do the welcome address.
Good morning, good morning, everyone. Respected Chief Guest, Dr. R. Vijay, Director of ARCI. Respected Guest of Honors, Professor Desai, Founding Director of IIT Hyderabad and currently the Vice President of INSA. Dr. Tata Narasimha Rao, Vice Chancellor, Shri Venkateswara University, Tirupati, and former SRC Advisor, IIT Hyderabad. And Professor Shastri, Dean SRC at IIT Hyderabad. Esteemed speakers, my dear colleagues, dear alumni, collaborators, students and friends. It's both a privilege and an emotional moment for me to welcome all of you for this C15, the Carbon Future Summit, as we celebrate the 15 years of Carbon Lab at IIT Hyderabad. Today, it's not just a beginning of a conference, it's a celebration of a journey. When I look back 15 years, the Carbon Lab did not begin as a grand vision. It began with a simple idea: to ask meaningful questions and to build something that lasts. Those early years were formative. There were constraints, uncertainties, and many unknowns. But what we had was far more powerful: belief, curiosity, and the courage to begin. And over time, that small beginning evolved into something much larger, not just as a research group, but a vibrant ecosystem of people, ideas, and impact. At this moment, I would like to express my deep gratitude to a few individuals who have been instrumental in this journey. And I'm so glad that all of them will be joining this summit. First and foremost, I would like to acknowledge my PhD advisor and mentor, Professor Sharma, whose guidance has shaped not just my scientific thinking, but also my approach to build the research with purpose. His influence continues to guide this journey even today. Professor Sharma will be joining us tomorrow morning. Professor U.B. Desai, our founding director, who recruited me as a young faculty member right after my PhD, and more importantly, gave me the freedom to dream big. That trust laid the very foundation of this Carbon Lab. I would also like to acknowledge our current director, Professor B.S. Murthy, for his continuous encouragement, belief, and the motivation towards the research excellence and perseverance. His support has been instrumental in sustaining both momentum and the ambition in our journey. Professor Murthy will also join us tomorrow morning. Dr. Tata N. Rao, who has been not only a distinguished leader in carbon science, but also my first collaborator at IIT Hyderabad way back in 2011 when we started this journey. He has been a constant source of guidance and support. And also our chief guest, Dr. R. Vijay, Director of ARCI, an institution with which not only the Carbon Lab, but IIT Hyderabad as a whole share a long-standing and meaningful partnership built on trust and collaboration. Professor Saptarshi Mazumdar, Professor Kishlay Mitra, Professor Mudrika Khandelwal, for their unwavering support and encouragement, and for being a strong pillar throughout this journey not just as a valuable colleague, but more than a friend. I sincerely thank all of you, and I am so glad that you are all part of this special occasion. Today, when I reflect on these 15 years, we have come across a long way since we started. We have published more than 180 international peer-reviewed journals papers with citations close to 6,000, H-index 43, filed 23 patents, out of which 6 patents are granted. We also did 1 technology transfer. 21 PhD students are graduated from this lab, and out of that, 5 are now faculty in various premier institutions of the country, including NITs and BITS. More than 100 students are guided in these 15 years, including 15 postdocs and summer interns. We executed 21 projects of worth more than 23 crores. Several awards and recognitions at national and international level are received by the group members. However, more importantly, at this occasion, I do not see just milestone or matrices. I see the people. Students who came with curiosity and left with confidence. Collaborators who expanded our horizons. Colleagues who supported and strengthened this journey. And alumni who are now carrying the Carbon Lab spirit across the world. To all of you, this journey belongs to you. Over the years, we have worked at the intersection of fundamental science and the real world relevance. Because we have always believed that science should not stop at discovery, it should strive towards impact. And that belief is reflected in the theme of this summit, Crystal, Carbon Research Yielding Sustainable Technological Advances for the Life. This is not just a theme, but it's a commitment to ensure that our work contributes to the sustainable technologies, meaningful solutions, and societal progress. C15 is therefore both a reflection and a renewal. Over the next 2 days, we will engage in discussions spanning over carbon materials, energy technologies, sustainability, and panel discussions on 2 important topics, translation research and also on the research evaluation, bringing together perspectives from academia, industry, and the translational research. I am particularly delighted to welcome our alumni back to the campus. You came here as students, but you leave as ambassadors of this journey. Your growth and achievements are the true legacy of the Carbon Lab. Welcome back home. I would also like to acknowledge all of our collaborators and partners. Your continuous support allows us to expand our horizons. I also express my sincere gratitude to our sponsors whose support has made this summit possible. As we celebrate this milestone, it's also a moment to look ahead. If the first 15 years were about building a foundation, the next phase must be about scaling the impact. We must ask ourselves, can we design the research with translation in the mind from the beginning? Can we ensure that the work contributes meaningfully to the sustainability? Because ultimately, the success of the science lies not just in what we discover, but in what we enable. Let me conclude with a simple reflection. What began as a question became a journey. That journey became a community, and that community now has the responsibility to shape the future. With that, I warmly welcome you all to the C15 Carbon Future Summit. I wish you 2 days of engaging discussions, meaningful connections, and inspiring ideas while recalling our proud journey of last 15 years. Thank you one and all.
Thank you, Chandra. And this is now time to first felicitate and welcome our guests. I request Professor Chandrasekhar Sharma to kindly present a bouquet to our chief guest, Dr. R. Vijay, Director ARCI Hyderabad. I also request a bouquet to be presented to our guest of honors, Professor U.B. Desai, Founding Director IIT Hyderabad and Vice President INSA. I request Professor Chandra to also present a bouquet to Dr. Tata Rao, Vice Chancellor Sri Venkateshwara University, Tirupati, ex-director ARCI Hyderabad. I also request him to welcome Professor G. Nari Shastri, Dean Sponsored Research and Consultancy, IIT Hyderabad. Before we go forward, there is a special book to be launched. I request all our guests on the dais to kindly join Professor Chandra in launching the book which captures the journey of Carbon Lab till date. It's an illustrated coffee table book. Thank you, everyone. Now I invite Dr. R. Vijay, Director ARCI. Sorry, I'm sorry for that. Yeah. First. Okay, sorry for the earlier mistake. Now I invite a guest of honor, Professor U.B. Desai, Founding Director of IIT Hyderabad and Vice President INSA, for an address to the gathering here.
Good morning, everyone. At the outset, let me start by congratulating Chandra and his team, Chandra, Mudrika, and everybody else who has been associated with Carbon Labs. There are two things. One is starting something is very easy, okay, in a sense, starting a lab and other things, but sustaining it is the hard thing, and also then growing and doing better and better each day, that's even harder. So in that sense, Carbon Lab deserves a very huge applause and many, many congratulations to them. Okay. This journey started 15 years ago, as you were saying, and there were some pictures out there which brought back a lot of memories from our old campus, so the temporary campus in Ordnance Factory. And on a lighter note, that campus was located in a place called Yedumelaram. And till today, I have never met, I give enough talks, meet enough people in the city of Hyderabad. Nobody knows Yedumelaram. Okay, because after my talk, they know, yes, IIT has started there. Okay. Shankarpalli, everybody knows. Okay, it's very well. And now Shankarpalli has become even bigger than the time when IIT Hyderabad started. So we started in a kind of a God-forsaken place. And also on another lighter note, when we were there, I think it's around the same time, maybe 15 years or 16 years ago, when we invited Shashi Tharoor, for a big talk. We used to have on the terrace, we had built an auditorium. Now this is a much better and a prettier and a far more better auditorium out here. So first thing that happened, he was staying at Taj Krishna. So this is what he told me when he came here. So he got into his car and he said, I want to go to IIT. Google Maps was there, but this is Shashi Tharoor, so he didn't check for Google Maps. And the driver says, there is no IIT out here. I know there is one triple IT. So he first took him to triple IT Hyderabad in Gachibowli. And can you imagine the triple, when he entered there is nobody to receive him. And when he said that, the guy says, we didn't invite you. I mean, telling Shashi Tharoor that was like a big thing, And then finally those people said, no, IIT is far away. So from triple IT, then he had to drive all the way through Narsingi, to IIT Hyderabad, which was located in Ordnance Factory. When he came, he was almost fuming. And he said, Professor Desai, this place is in a jungle. If I had known, I would have never come here. So he was, of course, delayed by a long time. the good part was, he said, I will not lecture now because, a lot of time has been lost, but I'll do Q&A. So for about 45 minutes, he did Q&A, and he was absolutely brilliant. I think he floored all the students, faculty who were there with the questions they asked and the answers that he gave. So that's taken the story as to where we were and how we were perceived. And to start a good lab in that kind of an environment is really a very difficult task. Okay, and this is something that I always talk about, that what builds an institutions. And I gave a talk the other day at INSA. We had this leadership summit. Okay, and I did talk about it out there. Recruiting great faculty, and I'm really proud to see some of them out here. I won't go through all the names. There are many of them out here, so it'll take me too long. But I think that was perhaps, if I look at the two biggest contributions in IIT Hyderabad for me, from my side, is recruiting very good faculty. And I think all of them have done exceptionally well, to the extent that now, not just national, they also have international recognition. Okay, so please, on my behalf, give a clap for applause for all the faculty, those who are here and also those who are not here. I think they built the institute, and you should keep that in mind, that when they came, again, as you said, they came and joined this place called Yudumelaram IIT in that area, and they made their home. Many of them were staying on campus. We had these small accommodations that were available from Ordnance Factory. They made their home and they built this institute. And for that, I'm eternally obligated to them. The director is there, but director can only do so much without having a good team. A captain can't win a cricket match, right? He needs a good team. We need a team of bowlers, batsmen, wicket keepers, good fielders, etc., etc. So I was very fortunate that a lot of good people joined IIT Hyderabad in spite of all these uncertainties. If you look at that place, it's like not even a high school. It was a middle level school building. And someone like Sashi Tharoor almost hit his head, I think, while climbing those stairs. So there they came, and for that I am highly obligated to them. The second part is that if you want to build a great institution, besides faculty, and as Chandra mentioned, is give them total freedom. You have to trust them. If you don't, and you start, usually in India, unfortunately, what we do is we micromanage. This word accountability has become very, very popular. In a sense, a director is not a Munimji. Okay, a director is a director. Okay, so you should actually trust them. They will make mistakes. Director himself, or who has come, they have made hundreds of mistakes. By the way, they don't talk about it. That's all. They project as if they have never made any mistake. Every director has made thousands of mistakes by the time they reach that particular position. Nobody in the world can become, even, I don't want to say more than that, any leader anywhere in the globe. You don't reach a point without making a large number of mistakes. So you should allow them to make those mistakes and, be there to help them out so that the mistakes are not repeated and things can be better. So that's second part. And the third part is you build labs. See, buildings can come up. We took a long time. What you see in the campus, people come here, people say good things about our campus. And I'm happy to hear that, but that is an external projection. Eventually, the content is what happens inside the building. Okay, the building you can have the prettiest of building, the best of building, but if you don't have a great lab in that particular building, it will just remain a shell. Okay, and I think for that I was very fortunate. Large number of faculty members actually invested a lot of their time to start labs in tiny places. Sometimes they were highly cramped, and we also invested a large amount of money. In fact, I diverted some of the money which was meant for construction into buying equipment. Of course, the ministry did take me to task. Faculty may not know about it, but I felt that labs are more important. It is not necessary that you should have. Buildings will eventually come up. They come up in 2 years, 5 years. It's not rocket science. Of course, you have to spend time if you want to build nice, long-lasting buildings where you feel comfortable to work. Takes a little bit of time, and I think we did spend time. There also the faculty contribution was very, very important. Practically every department building, the specifications were provided by the faculty. You look at the physics department, you can look at chemical engineering, you look at electrical, any department on the campus. Okay, so I think that was very important. These are the two big things that are required, and I was very fortunate, as I said, that both the things happened. In fact, by the time my tenure got over in 2019 June, I think we had approximately, I think about 120 labs, and I could be off, maybe 110 labs or 120 labs, I don't remember. I think that's a sizable number to have that kind of number of labs in 10 years' time, given the fact that for almost 6 years, we moved to this campus. I was the first person to move in 2015. At that time, this campus also was like a barren land, literally, except for one building. Okay, and I think it was by 2016 is when things started shaping up a little bit out here. Okay, so for several years we were still on the old campus. Okay, and I think that in starting labs out there, doing things out there is quite remarkable. So for that, I really congratulate everybody out here, and I'm just hoping that now Carbon Lab has spent 15 years, a good foundation has been laid, it will go much further. I really wish them that they will look it up. And my one common suggestion, which I normally talk about once you have established yourself, is, so you have published large number of papers, congratulations, you have large number of citations, as you said. Many PhDs have come out from this place, many of them are occupying faculty positions in leading institutes. I think that's a great achievement. Now you should work on at least one problem, which is a very difficult problem, and if possible, an impossible problem. A problem that everybody feels that you really can't do much. And recently we saw the example of that. All of you saw that a fast breeder reactor went critical just about few days ago. That is almost more than 30 years of work that has gone into it. And for whatever reason, so many directors and chairmen of atomic energy and directors of BRC came, directors of Kalpakam labs came, and they sustained that. One could have easily given up, saying that, man, this is not going to work. 10 years is what we have spent. We have used thorium reserves, and they kept at it. In fact, recently also, Kakodkar was mentioning somewhere that we should never give up this. Because once we succeed on this, will be literally our energy security can be guaranteed. Okay. So that kind of thing is required, that you take a problem which everybody feels is very difficult to solve or impossible to solve, and stick to it. I'm not saying all the problems should be that way. If Carbon Lab is solving, say, as an example, 7 problems, at least 1 out of the 7 should be a problem where you will take 30 years. It will probably be solved by the time Chandra retires. Okay, so it doesn't matter, But I think that's the kind of problem we should kind of focus on. Okay, so with these words, once again, I wish Carbon Lab, Chandra, Mudrika, and other chemical engineering faculty all the very best. Build more labs. I feel very proud when I read about them and I see that, yes, they are getting recognition both nationally and internationally. So wish you all the very best.
Thank you, sir. I'm sure, I'm very emotional right now listening to you. I'm sure Chandra is, and all the colleagues here who joined during your time. And I'll just sum up in one word, is thank you, sir. That's all I think we can say. Because we all know the kind of entrepreneurial skills you have used that time to initiate us. So we owe a lot to you, sir. Yeah, so moving forward, let me invite Dr. Tata N. Rao, Vice Chancellor, Sri Venkateshwara University, Tirupati. He was the first collaborator from ARCI with Professor Chandrasekhar Sharma, and I think they've graduated multiple students together, so special address from you. Thank you.
Thank you. Good morning, everyone. Thank you so much, Mudrika, for being as a close colleague, associate for a long time, and helping us, our Carbon Lab. I feel I'm also part of Carbon Lab because yeah. So we're also colleagues in MSME now. Thank you so much, and then thank you, Sharma ji, for inviting me, and then. Sir, Desai Saab, of course, we are on several committees, and then I keep meeting, and then I get excited whenever I meet because we don't see his age. He always very fresh, and then comes with a lot of enthusiasm and energy. He's like a role model. So coming to IIT, my interaction with IIT is as long as probably Professor Desai, because when it started in Edumailaram, I was scientist in ARCI, and then we were working that time. Nanotechnology was very hot topic because national nano mission was in full swing, and then ARCI we were doing a lot of things on nano silver, nano titanium, textiles, and huge amount of translation, because ARC is known for translation technology. Vijay can tell better now. So, but we never thought we'll do on battery materials. So when IIT Hyderabad started, it was mentored by IIT Madras, Professor Murthy and UV Varadarazu. They both were there leading that. And then Varadarazu was my long time friend from my MSc days. So he called me and asked, we don't have much teaching staff that time, because people used to come from IIT Madras and teach. So can you teach chemistry? So it's very far from Balapur to this side Shankarapalli. It used to take almost 1.5 to 2 hours, but I cannot say no to any of my friends. I said, okay, I'll take at least one topic, that is chemical kinetics. So once in a week I used to come and then spend 2 hours there, and during that time I met young faculty like Atul Deshpande and our Sharmaji. And we used to discuss, sometime there is an open place for a tea stall and all, and we used to discuss. And Varadarazu motivated me to get into this battery field. And then once myself, Dr. Varadarazu, went to our that time director Sundararajan, and then went with a small LED and with a small coin cell battery. And then just to convince him, because seeing his believing, Dr. Sundararajan will not get convinced so easily. Then we went and then lit the LED with a small coin cell, and then he said, this is the time we should get into this, and then there is a lot of future for battery technologies, and ARCA being a translational research center, this with a lot of fundamental background and knowledge of IIT, we should collaborate and then take it forward. So that time I started, and our first student is one side Akubhaskar and then one side Anuleka. Anuleka joined with Sharmaji, and then Akubhaskar with Deepa. They both were that time the faculty who were working in these areas. So the journey started like that, and today ARCA is very well known in the country for their battery, supercapacitor, energy research. And like Professor Desai said, it took almost 20 years, and then now things are going so well. And then after my retirement, Vijay took it to the quantum jump to a very high level with a huge chunk of funding, and then putting a lot of facilities coming, prototype facilities, and 2 megawatt they're going to establish. So it's a wonderful journey. So that's one part. But then my association with Sharma's lab, Chandrasekhar Sharma's lab of carbon, it's really amazing, because Anuleka, our first student, for you also first student is Anuleka. Yeah. So we really worked so hard, and then she is a fantastic student, and actually she is from some bio background. She was doing an electrospinning and all. Then for some biomedical application, I said energy is the one where we should start working on that one. After one paper published, I moved her to this battery field, and then she joined IIT, because ARCA doesn't give degrees. We need to collaborate, and then IIT she joined. And today she published so many papers, and then today she went as postdoc, got married, and then US, and she works for US Defense, Air Force, in a very big position. And like that, whoever worked with our collaboration, especially in this lab, and they are doing so well. And now the latest is Sony. So we are so proud of all these people, and then we feel so young. And in fact, actually, we learn a lot from these people, because they work so hard for their PhD, and then they keep coming and then telling us what is updating, and then we get motivated, and then we start adding to that. It is incremental innovation. Like Professor Desai said, while we work and then do a lot of things and then publish excellent papers and all, but of course you need fundamental, very strong research to get a best technology. Otherwise, you can always do technology up to 90%, 95%, but the last mile of the technology gap, where you want to excel and then be comparable with a imported and then substitute the so-called self, that is only possible when you have the fundamental knowledge, enough fundamental. Otherwise, you cannot fill the gap. There, the chances are very high, because when you reach, if you see the purity of a material, you can reach 98% very easily. As you go from 99.999, you are working against thermodynamics. You need to do a lot. That's why all the precious metals or the semiconductor metals, what we require, like gallium and silicon, and we are not able to produce in this country, and then we still depend because the last mile of the technology is missing. So, and this is one thing what we need to cover it up in all our research labs, and then collaborate with the labs who are doing technology like ARCI and NCL or many other labs. And while not leaving our own strong fundamental research, being in an academic institute, and that is what our job. Because when we train the PhD student, if they are not strong in their fundamental research, then the future of the technology will not progress. That's one thing. And the second thing is, Chandra's lab has done excellent work with a lot of carbon materials for various kind of applications, whether it is CO2 battery and then supercapacitor, hybrid capacitor, lithium-ion batteries, lithium sulfur now, they are doing so well, again in collaboration with Dr. Sarada of ARCA. But like Professor Desai said, we need to also keep some challenging tasks with us for the future, so that we, if being experts in carbon, if our lab cannot do, and then others cannot think. A simple example I am telling is, I think if Chandra agrees, the quantum technologies what are coming, and then presently the government is looking for the quantum hardware. Quantum software, it is possible because it's only software, and then you can have new algorithms for the new technologies what are coming. And then if you see in the Amaravati tomorrow on 14th International Quantum Day, they are going to demonstrate the test beds, bringing all the TIFR, IASC and all. They have 6 qubit, 10 qubit quantum computing systems already developed, both superconducting and photonic qubit quantum systems. And while what is there being demonstrated in Amaravati, that is a superconducting quantum qubit based system, where you need cryogenics and the chip has to be maintained at them, because it is a superconducting niobium or some metals what are coated on silicon wafer. The temperature has to be millikelvin. That means you have to use liquid helium, maybe helium-4, and then bring the cryogenics so to bring to that one. And whatever you see the superconductor IBM, that's all cryogenics. The chip is actually a simple chip what is in the bottom, and that works. So, and that is not viable in many terms, because how do you, the country, if you want to become self-reliant and manufacturing of quantum hardware in this country, and that is not really viable, because you have to maintain this temperature, and 100 qubits or 150 qubits what is being set up, that is very small. Eventually, maybe a decade after, you need to have millions of qubits to run the actual computational algorithm. So, what is required now is a quantum hardware where the qubits work at room temperature. You have photonic qubits which work at room temperature. You also have the ion pair, neutral atoms and all. And one of the things what is relevant to carbon is nitrogen vacant centers in diamond. And then those work at room temperature, and they are, since they are in the lattice, the spins, and they are not disturbed by the external disturbances, even the temperature such as, which is the difficult problem for the quantum qubits. That's why you need to have the cryogenic temperature. So, we have a lot of expertise in the country, and Professor Ramchandra got in IIT got a huge funding for making lab grown diamonds, and then I think it's a CVD based diamond. We can work on that, and then if Chandra doesn't start that one, I think others may take more time. I think we Chandraji, we still work. I can also help, because we have long-standing diamond experience. Also, Dr. Sarada is also there, who did her PhD on that one. And then, so let us see that. And then the other side of, since you are already in energy systems, you are working, and diamond being a high band gap semiconductor insulator, once you put diamond, can take a lot of boron into that one. You can go up to 10,000 ppm boron, make it conducting like a metal, while keeping its dimensional and then all the remaining properties intact. That means I can use diamond electrochemistry in hydrofluoric acid, which you cannot do with any electrode. And then it also has huge over potential for hydrogen and oxygen evolution, so that you can work in wide potential window. And some of the reactions what you cannot do in aqueous systems, you can still do in aqueous systems with diamond electrodes. A simple example is a redox flow battery, where cerium and manganese we want to use, which has got high potentials, which cannot be done with the normal traditional carbon electrodes because they interfere with the hydrogen and oxygen evolution. You can do the diamond, and then it's already being in practice. I think some of these things, because when Professor Desai was telling, I was thinking, what is that we can do further, and these are things that came in mind, and then I think we should work towards the new systems, alternate systems, while not leaving our traditional which are in practice now. With this I will stop. Probably in panel discussion we'll talk more. Thank you so much for this opportunity. Thank you.
Thank you, Dr. Tata. I mean, this is what, this is the magic of having the great mentors around you. Professor Desai said you should find a problem statement for next 30 years, and Dr. Tata just set it for you. Yeah, so this is the power of having great mentors and well-wishers around you and the facilitators around you. Let me invite Professor Narhari Shastri, Dean Sponsored Research and Consultancy at IIT Hyderabad, who has been ensuring a great system for us to have a great research here.
Thank you, Dr. Mudrika. And at the outset, I thank Professor Chandrasekhar Sharma for his love, because I don't know why he called me, but many things will come when you don't deserve, and you have a chance to either accept or not to accept. I humbly accept it. It's a great thing for me to sit next to Dr. Vijay, Professor Desai, and Professor Tata Rao Garu on this momentous occasion. We need to realize most of the human beings will overestimate what they don't have, but at the same time they underestimate grossly what they have. And I feel that it's very important. Our Bharat Ratna Abdul Kalam says that to have a small goals is a crime. You have to think big. And another thing is, you need to celebrate every single success that you have. That culture has to be developed. But there will be so many things that we have in life, but in research it is a 1% inspiration and 99% perspiration. Perspiring people are the students only, right? So when we have some success, we need to celebrate, and it's very, very important. Carbon, I have lots of association because my career, I am a theoretical chemist now, and I am in the Department of Biotechnology. I got very much inspired when Kroto went to Rice University in Smalley and these labs. They are mass spectrometers, mass spectroscopists. They have found a peak at 720. And they did not know what is that. For 11 days, they hardly slept for 2 hours or 3 hours. And on the 11th day, they submitted this paper to Science, that is C16. None of them have any paper in Science before that. And after that, everything is a history. It has become a molecule of the year, C60. Then the carbon nanotubes have come, single-wall and multi-wall carbon nanotubes. While C60 got a Nobel Prize, the single-wall and multi-wall nanotubes, while they did not get the Nobel Prize, the impact is so high. Then we have graphene, a new avatar of carbon, and carbon nanofiber, carbon dots. Many things have come. We are all, as students, we all say that coal is a carbon and diamond is a carbon. But carbonaceous materials have become so much, it has become a great equalizer of the entire science and engineering streams. A chemist feels that, okay, they are also a part of these carbonaceous molecules. They will be bottom up. People who are working on fragments of carbon like naphthalene, phenanthrene, or coronine, coronulene, sumanine, many other things are there. They are a part of it. Physicists are a part of it. And material science, of course, that's their territory. And engineering people are a part of it. And the applications of these things are wide across different disciplines. So, when somebody the carbon has a very nice acronym, crystal has a very nice acronym, and it's extremely important to find out ways that how we can motivate ourselves to think big. there is a book written by Marshall Goldsmith, which I always see that what brings you here cannot take you there. At every step, we need to know what is that we can do to ourselves to become stronger, and our strength should be useful to our institute and our nation. And if we talk about one leadership that is there in IIT Hyderabad, I think all of us should give a big round of applause to Chandra Sharma, because Chandra has brought in so many DST programs. He developed that trust, confidence and clarity, not only at national level and also at international level. It's not easy. I understand that how many meetings he conducts. Parallelly, he is conducting another meeting and ANRF pair program and artificial intelligence in healthcare. I am a coordinator for that. I have invited somebody there who is a good friend of mine, and I don't know whether I have to sit there or here. But you see, there are human beings can do anything in life, but not everything, right? So we need to have a very clear strategy that what are your priorities, how you want to do it. Leadership is a very, very important thing in India, and I feel that we should learn to emulate as stronger personalities, adopt positive traits in our life, where we have to realize that I am born here, so I have a great potential to do something for my country. You have to strongly believe in that. When you strongly believe in that, everything will happen. Yad bhavam tad bhavati. You have to have a strong determination. And I cannot say no when they say, because I joined here about 2 years before and I did not know anything. I invited some 8 German delegates. I have no idea. Then one day I called Mudrika. He said, oh, don't worry, I am here. I will take care of that. And I did not know what to do. And so there are people who are always there to help you. And we are like a community which were greatly indebted to a great personality called Dr. Yube Desai Garu. So he has made IIT Hyderabad as at a different level. The buildings are different, the class is different, the uncompromising style. It's not that you recruit a great scientist. I think, sir, you recruited scientists and made them great. And this is something I could easily see the type of confidence that you have on your people, right? You just recruit somebody and you put lot of trust in them. You empower them. And people make mistakes. Who will make mistakes? Everybody will make mistakes. So with that type of a base, IIT Hyderabad has been always in the top ranking thing, and this is followed by very energetic Dr. B.S. Murthy Garu, and the tradition continues. And I am very, very sure that, Chandra, this is a great tradition that you have started, and people should not be hesitant to celebrate. Yeah, we have done a great thing, right? This is very important. You have to just celebrate, and then you have to find that this is your right to celebrate. And let this positive thing be infectious in our community. Let us make our IIT Hyderabad not only number 1 in the country, but internationally a very, very important institute in the near future. Thank you very much.
Thank you, Professor. Trust and love, and that is the reason you are here. You started outside, you asked why you are here. So, yeah. Let me invite our chief guest, Dr. R. Vijay, Director ARCI, Hyderabad, for his inaugural address.
Yeah, good morning to you all. And first of all, I am privileged and then honored to be sitting next to the eminent and towering personalities like former director, Professor Desai, and my boss, my guru, former director ARCI and currently Vice Chancellor, Venkateshwara University, Dr. Tata Narsingh Rao. And of course, my friend Chandra and the Dean, Professor Narahar Shastri Garu. He took over, I think, 3-4 years back, right? 2 years back into that. And and I know, this when you talk about carbon, we know when you're looking at from Stone Age and then to the Iron Age, right? So when you're looking at iron, all those tools, it all made hard because of the carbon. It's all coming up to the either carbon in solid solution, or you can forming as a iron carbides, or chromium carbides, M23C6 carbides, which gives the strength to the steel. So we have been knowing that using this carbon as part of our materials and then high kind of things. You can also see that some of the steels, the kind of technology what we used it. If you could see that iron pillar and all, that gives you still it is a kind of a curiosity and all. It doesn't rust. And if you put it in iron, everywhere outside, it rusts and then it spalls off and then eventually it completely disintegrates and all. But that kind of steels. And the famous for any metallurgy guys or material science people, we read about physical metallurgy is that iron carbon diagram, phase diagram. And that's very, very important, the kind of carbon content either in terms of a solid solution or in terms of a formation of different phases. Either it's a perlite or it's a bainite or it's a cementite. So this kind of things, as the structure changes, the carbon, how it influences, it changes the strength, it changes the complete characteristics of those material. And that's what the carbon actually has been playing a major role in our evolution and then in our civilization and in terms of our growth, economy, and then all those tools. If you're looking at all kinds of tools being used in agriculture or then other implements, tools and implements, they are all martensitic steels or then hardened steels, and then so that gives you good hardness and then wear resistance is very less. So coming back to that afterwards, carbon has become an integral part of our life, of course, globe, because coming to the complete circularity, we take, everybody consists of an hydrocarbon materials, and then whether it's a plant or it's a human being or anything. So when we make it into carbon, we use it into different things. In the chemical industries, we always use carbon to as an adsorption or the color change or the odor removal, and then all those things we have been using it. And over a period of time, this usage of the carbon has gone leaps and bounds. And one of the things looking at as an carbon as an energy storage materials, whether it is an anode materials for the graphite, for the lithium ion batteries, or the hard carbon for the sodium ion, or for the supercapacitors for the high power things, and also for the lithium sulfur, you have to put it up sulfur, we have to impregnate or sulfur, distribute sulfur in the carbon in terms of an electrode material. So that's one aspect. And then the other aspect, that's kind of an energy storage, because we are also using as a coal, one form of carbon, and then burn it. We have been using it to convert it into a lot of energy, thermal energy. All our thermal power plants in India, which are coal-based plants, and which gives us a lot of CO2 things. And there is a good technologies which are needed. Government also has committed to reduce the carbon CO2 emissions by 30% by 2030. And then net zero by 2070. So we need to have that kind of a technologies which it converts CO2. But people are talking about conversion of CO2 into methanol or any other organic compounds, but then use again to generate hydrogen or generate energy, and then thereby producing CO2. So it's a kind of, you are still releasing CO2 into the atmosphere. But the question is, if you convert CO2 into a carbon, a solid materials which can be used, and then which can be used to rejuvenate our mother earth, and then you have seen that some of the porous carbon materials or biochar, which is all being used for the materials for the plant growth, and then also needs an absorption of a lot of moisture, and also that we can always save a lot of water. to the plants. So we can try that the new area of the things, and then other things you can also try about carbon dots, quantum dots, as Dr. Tata Narsara was mentioned. Is next is the quantum we should looking at, and then carbon dots. It's quantum dots. We can always work on for these new things, and other important, so let me come back to that. Our association ARC, as mentioned by, of course, Professor Chandrasekhar Sharma and then Professor Dr. Tata Narsingh Rao. And it's all started, with his teaching from ARCI and then teaching at IIT Hyderabad. And then that also made us, initiate an activity on the battery materials, development of battery materials, which all started, it's a long journey, almost 15 years, 2010 or 11, we also started working on development of materials. And that's way it has given us a big a platform and big impetus, and then, made us, create an ARCI, its own niche, its own impact, its own name in Indian, in India, throughout India, in terms of the materials and the fabrication technologies for the battery. And then other thing, and then and I also tell you is an ARCI is a translational research institute, and then our mandate is translating. It's all translational research, and then in fact into technology, and then eventually transfer those technologies to the industries. So we work on takeaway all the way from the proof of concept into the TRL level 5 and 6 things. But that's a very, very challenging jobs. Many of them, they die, while crossing that valley of death. But eventually what we try is, we will take it and then push it and then cross that valley and then go that. And that gives a very, very, a lot of challenges, a lot of hard work by our scientists. And at the same time, the time given for working on the fundamental research by our scientists is little limited. So what we have done over a period of time is we have established collaborations with an academic institutions where the fundamental research is done. Which is done. So we collaborate with them, and then from there we take it, work together, and then take it to the higher TRL levels. And then when you say that, the idea of the battery, which is nucleated, at IIT Hyderabad, and then resulted into a big technologies through an ARCI. So that's a classic example of a collaboration of a institute and then academia, that kind of a joint work. And I also see that kind of things, our students are working on, many of our ARCI research scholars have registered here as a PhD, and they graduated, and then they have been working in a very big institutes and then prominent institutes in India or abroad or in academic institutions. So that gives a pathway and then best examples for a collaborative research. And then now the earlier days, we used to work in our own lab and then do something and then publish papers. And then now it's a time of collaborations. And that makes us to give that, the speed. So essentially now in this term, we have to look at it is to go from invention to then innovation. So you need speed. So if you don't do it, very fast, you will be lost, you will be forgotten, or even the technology is overtaken and the new technology comes in, so it becomes an obsolete. So we will be lost. So to get that, to achieve that speed, the mantra is a lot of collaborations. We have to do that, and then and that's what we have been doing it. And then I'm very fortunate, and then to have Chandra to collaborate with the ARCI, and then a lot of things have come up. And then more recent collaboration is that getting that Maha EV project on the development of materials and then tropical batteries. And that's what we are working. And then we are also part of, and then coming back to that IIT in terms of that, I was, when I started, I joined ARCI in 1994 immediately after my MTech. Then subsequently, I have registered as an external PhD. At that time, there is no IIT at Hyderabad, right? So then I have to go to IIT Madras to register my PhD. Otherwise, I would have done over here, because of that. So from that, small, when you are looking at the from address by Professor Desai, then from a small place, from Edu Mailaram, and then to become over here, and then, big campus, and then the total, his vision, and then his planning, and which come up, seen it in every building, every things, and then even as looking at this hall. So we are also, ARCI is also planning to have a one auditorium. So I was also looking at, just going through what kind of features you need it, and then what kind of things, I can implement it. In fact, I asked my civil team to visit here and then have look at it, this lecture, this conference hall complex, to see that, what we are missing. So that kind of a thing, it just come out very well, state-of-the-art facilities. And then at the same time, it's just not the buildings or anything, it's the people who run it, and then who make things, take that flag, to the high levels, and then keep that impact, keep that, take it to the higher levels. And then, as mentioned by Professor Shastri, that it should become not only number one in India, but also a prominent institute. It should become in the world. And that way, we are all privileged, and then we are also fortunate to have this IIT, and then it's all initially with under the leadership of Professor Desai, and then now with a very dynamic leadership of Professor B.S. Murthy, and it's all going on very well. And then now the Carbon Lab, which is under leadership of Professor Sharma, which is taken 15 years. So it has actually become an infant to the teenage now. It has become a teen. And then now, obviously, so the teens will be very energetic, and then they are all open, and they can go to, they can do, capable to do anything, and then analyze and then talk. So it's also the duty of us is to nurture and then put them on the right track, and then to take it to the higher, whatever the direction, whatever the field we take it, and then, it has, so then you will achieve what you want, and then create an impact of this carbon lab. And also, I would also like to share that we also share both the ARCI and then Carbon Lab. They also share same thing, because Professor Sharma is a student of Professor Ashutosh Sharma, and who happens to, he was our chairman tag of nanomaterials earlier, and he was also instrumental in some of the programs at that. And then right now is also our chairman governing council, ARCI. So it gives us, common, kind of a platform to work, is under the aegis of, under the umbrella of Professor Sharma, Professor Ashutosh Sharma. So that way, we also feel that we are of one family, and of course, IIT Hyderabad and then ARCI always treat that it's a one family, and we are doing a lot of not only in the carbon, but also in the lot of other materials, high temperature materials, additive manufacturing. And then yesterday also, Professor Bhanusankar Rao was talking to me in terms of putting the people together, and then look at the development of high temperature materials, which is a ODS superalloys. It's all GRX, which is all done by the NASA, and which is also testified. So why can't we do that as it's an additive manufacturing? We have a state-of-the-art facilities. And we also got a big facility, or establishing a facility to make powders for the refractory metals, which can be used for the additive manufacturing. So we started with the C103 neo-BMLI for the scramjet engines. So that way, both from the, I always feel that, it's not a one single, so to take it, any technology development, it's not just a single person, it's also a team effort. So it consists of an academicians, and then the engineers, and then the other marketing people we also need, and then and then finance people, so we need that, and then make it into a good package, and so that that can be completely deployed and then adaptable by the industry. So with this, we have been doing that, in terms of an associations with the RCI and then IIT Hyderabad. We have been doing that, and I have seen from the last 10 years how the IIT has here it created its own impact in terms of as part of the many national mission programs, and then more recently it's all in the critical minerals and then metals. It is all declared as a center of excellence for that, and then where ARCI is part of it. And that way, we always feel that we can deliver, we can achieve things, and then we can contribute to the growth of the country and make it India to realize that Viksit Bharat 2047. And I'm also a firm believer that when the system grows, then the individual also will grow, and that's why we always work for growth of institute or growth of the lab, and then thereby indirectly we always everyone who is contributing to that also will grow. So that's another point. It's a win-win situation, and then that's what we have been doing it. And with this, and once again thank you, Professor Sharma, to giving me this opportunity, and then and also to share and then meet people. And I wish all the best, and then I wish this Carbon Lab grows leaps and bounds in the coming years. Thank you very much. Yeah.
Thank you, Dr. Vijay. Indeed, a collaboration can only flourish under the able leadership, where the leadership is open-minded, looking forward to better ideas, is progressive, and looks at sustainability as well in terms of relationship as well. Thank you so much for providing that for IIT Hyderabad and Carbon Lab. Let me take this opportunity to invite Professor Chandrasekhar Sharma to felicitate our guests. We'll start with our guest of honor, Professor U.B. Desai, Founding Director of IIT Hyderabad. And I request the audience to please join me in thanking them for their time. I request Professor Sharma to also felicitate Dr. T.N. Rao, ex-director ARCI. I request Professor Narhari Shastri to kindly join Professor Sharma here, and I request Professor Sharma to felicitate him. Certain things are compulsory, no options. Mandatory. Now I request Professor Sharma to felicitate our guest of honor, Dr. R. Vijay, Director ARCI, our chief guest for today. I request all the guests and the dignitaries to kindly take seats in the audience. We have something special to show on the screen so that you can see it very conveniently. So here is a 15-minute long video of the journey that Carbon Lab has come across. Sit back and have a look and enjoy it.
When we started this journey 15 years back in the ordnance factory, we thought we will make a lab which addresses some of the societal problems with the knowledge what we had that time.
Can I request you to pause the video, please?
We take this.
Yeah. So Professor U.B. Desai has to take a leave now. So please join me in again thanking him here, and we'll watch the video after this. Can I go ahead with the video? Okay. Kindly play the video.
When we started the journey 15 years back in the thought we will make a lab which addresses some of the societal problems with the knowledge what we had that time. If we take this journey as a successful journey, this is all future. So I must credit all the students, all the wonderful students I had last 15 years who have contributed to each and every small journey. So this is very satisfying and very overwhelming that the students from the Carbon Lab, they have now great career, and some of them are of course contributing to the same part of academics.
15 years ago, a vision took shape to build a space for exploration, a place where curiosity could turn into discovery. From a single idea to a journey of research, people, and purpose. What began with challenges has grown into a dynamic ecosystem, pushing boundaries across chemicals and beyond. More than just experiments, this is a space shaped by people, students, researchers, and collaborators driving ideas into impact. Over the years, the lab has contributed to innovation, sustainability, and real-world solutions.
It's quite nostalgic and at the same time exciting to see the Carbon Lab what it is today. The nostalgic because I witnessed the growth of this lab for last 16 years, and exciting is that it has done tremendously good, tremendously well in last decade or so. So the major reason why I saw that in the lab, then myself and Professor Chandra, we actually got recruited in the same batch, and even our journey started from the airport together, coming IIT Hyderabad to give an interview. I could not predict, nobody can, that what could happen. I saw a kind of a tremendous growth of a lab, both in terms of laws like publications, like patents, like working in the technology domain, diversification, but also there is a good amount of professional way of handling the research. To be very frank, if I feel that Professor Chandra's lab or Carbon Lab has one distinctive difference than many of the labs, including my lab, is that the lab culture and the lab, the way that professionally that he handles the entire lab is something praiseworthy.
I've observed this group very closely for last 12 years or so. I've looked at Chandra as a mentor always, and at the Carbon group always as a group that we look as a standard model how a group should function. It's not just an academic group, it's a group which is doing research along with several collaborations, sustaining them, doing a lot of outreach activities. The PI of the group is able to do and take responsibilities only because he or she knows that there is a group behind it.
Scientists at IIT Hyderabad developed a novel green method for recycling orange peel waste, which also has great ecological benefits and commercial potential.
So as I said, whether it's any summer intern who has just spent a couple of months in the lab, or a PhD student who have spent their 5 years or even more than that. Of course, the quantum of contribution might be different, but they all have contributed. In fact, some of the research directions in which we have worked, they have been initiated by the summer interns projects. So, and I think another thing I would also mention that we have catered the students from the different backgrounds. We have not confined ourselves to the chemical engineering discipline only. We have been open from the beginning, from the students from physics, chemistry, nanotechnology, instrumentation,
and material science, bio background. So I think the diversity in our students that has really shaped that vision for a much interdisciplinary research approach. So again, at this point, I will not say any specific names, but I'm really proud of all of my students, right from the summer interns to the BTech to MTech and PhD, and even in the postdocs. In fact, we have guided close to 20 postdocs by now, and some of them have really contributed quite significantly for a great amount of time in the lab, which is generally unusual for a postdoc. We have postdocs who will spend even 3 years' time out there area. So again, I must acknowledge each and everyone in this journey of 15 years of Carbon Lab, and this celebration of 15 years, it's a collective celebration. Success is our vision. That's what I believe in.
Well, I can recall some of the landmark projects we had in the past. One was related to the EV mission by the imprint program, in which we have demonstrated the use of candle soot carbon as an energy storage materials for lithium-ion batteries and supercapacitors. This project was with ARCI, where we have also learned on how to scale up this material. So it was a good exposure in terms of fundamental research to the TRL level 4 research, where we have demonstrated the real prototype for the lithium-ion battery. Another major project which we have done with the DST Nanomission was on the use of polymer nanofibers for the controlled drug delivery, and we have achieved quite success in that, that we were able to demonstrate the use of large molecules like amphotericin for the controlled drug delivery, and we have gained very scientific insights into that particular project. And of course, recently we have been involved with the with EV mission, where again we are looking for lithium sulfur batteries, and we want to go for the higher TRL level research. So some of these research, I think they have shaped our journey over a period of time, and we have learned a lot while executing these projects, and thanks to the funding agencies who have shown the trust in our research capabilities. Well, I think industry collaboration, we have done a project with Tata Steel, in which we have demonstrated that how the low-grade coal, which is in abundance in India, but is not very used, so how we can convert that low-grade coal into graphitic carbon, and that graphitic carbon can be used as an electrode material for the lithium-ion batteries. So I would say the current project which we are doing with the Coal India under the Clean Center of Excellence is a kind of extension of this project, where we are aiming that how we can convert the low-grade coal or high-ash coal into the useful product in terms of graphitic carbon. And I think if we are able to demonstrate it successfully, there is a huge, tremendous benefit, because Indian coal especially is low-grade and high-ash. So if we can utilize that coal into the other alternative products, that will be a major breakthrough for the coal industry. Apart from that, we have in fact the very basic foundation of carbon materials for energy storage devices have come from my PhD background, where we have collaborated with Professor Mark Madhu at UCLY, and we have been continuing that collaboration. Not only that, we have also collaborated with Professor Alamgir Karim, Professor Ramakrishna from NUS. Professor Karim, he was in University of Akron, now he is moved to University of Houston. We have learned how these thin films in the polymers can be modified, or we have used that block copolymers first time in the electrospin nanofibers, and we were able to achieve some of the breakthrough in terms of how we can self-assemble the polymers, especially the block copolymers, and modify them for some surface functionalized surfaces or the nanofibers. So I think international exposure through these collaborations have been quite good, and we would like to continue some of these collaborations, and maybe I think we would like to closely work with the industry in the coming years.
తాగునీటి ద్వారా సోకే ఈ భూతాన్ని తరిమేందుకు ఐఐటి హైదరాబాద్ ప్రయోగాలు చేపట్టింది. తాము తయారు చేసిన పదార్థంతో ఇక నుంచి ఫ్లోరైడ్ రహిత నీటిని పొందొచ్చని చెప్తోంది.
Waste material, which is jamun seed. Generally we throw the jamun after use, and seed is just considered as a waste. So we have utilized, we have shown or demonstrated the potential use of this jamun seed.
मंगल मिशन के लिए धातु कार्बन डाइऑक्साइड बैटरी विकसित. अंतर्ग्रहीय मिशनों की लागत में कमी लाएगा आईआईटी हैदराबाद के शोधकर्ताओं का नवाचार. विज्ञान एवं प्रौद्योगिकी विभाग के स्वर्ण जयंती फेलो प्रोफेसर चंद्रशेखर शर्मा ने अपनी इस तकनीक का हाल ही में प्रयोगशाला स्तर पर परीक्षण किया. अब तक की जानकारी में यह अपनी तरह का पहला अनुप्रयोग है. ज्ञान विज्ञान की एक रिपोर्ट.
If I look back the journey of carbon lab last 15 years, I feel that whatever knowledge we have gained over the last years, that should be translated further into the products. So I think we will look forward to work closely more with the industry to convert some of these technologies into the products, some of the knowledge to the higher level research. And of course, we have transferred one of the technologies so far, but I think it's time to move forward with more technology development and more product development. So I think in the next 5 to 10 years, we plan to work more with the industry, and also some of the new areas of research where, for example, metal CO2 battery, where we started 5 years back, but there is a lot to learn in terms of scientific understanding, especially in terms of Martian atmosphere. So there is much more to gain in terms of scientific understanding and fundamental knowledge. That's also we will focus on. And with time, as the technology is developing, I think we need to look beyond the lithium-ion batteries, beyond the regular battery and capacitors. For example, dual-ion battery. So these are some of the areas which Carbon Lab will be focusing in the subsequent years. Well, I think what drives me or my lab is curiosity and the way we want to impact on the society in the long terms. And that's something which drives me from the core, and we will continue to do that. So if we enjoy the research, not just for getting any academic degree, but as a way or as a tool to contribute to the society, I think that's much more satisfying. And I think that whole journey, whole process, we will be enjoying it a lot, rather than feeling it as a stress or as a kind of some compulsion to do anything research. Say 3 words rather. It's curiosity, collaboration, and the creativity. I think these are the 3 words which define the path.
So after this video, we're almost coming to an end of the inaugural session, but I do want to share a few observations. Chandra then and Chandra now. And several students we have also graduated together. I'm becoming slightly informal now, but several students we have also graduated together, and certainly a lot of things that my group has also learned from him and his group. And we can certainly see a lot of people who made visits, a lot of people changed in dimensions, various kinds of dimensions. Yeah. Okay. So before we close and thank our guests and sponsors, I do have three announcements. One is we'll have a photo right after this, the face facing opposite to the guest house. So that will be on my left, your right hand side. Just follow the crowd. The second is those who have received a T-shirt in their bags. You're requested to wear them tomorrow for another photograph. And if you have objections regarding that, please contact Chandra. Third is your departure plan. You can share it at the registration desk today before the lunchtime preferably, so that they can make the suitable arrangements. And your fourth C in the creativity, curiosity and collaboration can be carbon or crystal. Okay, with that, please join me in thanking all our guests who have graced the dais today. Thank you all for your time. And also, I would again like to acknowledge the sponsors for today for enabling this event even with better capacity. Thank you. Signing off now for now. The next session will be here, which will be a panel discussion. And next 2 days will be full of intellectual curiosity and creativity, 2 panel discussions, 4 technical sessions, and an event full of music and colors in the evening with Varsi Brothers. So stay tuned and please be with us. Thank you, everyone.
to welcome you again onto this panel discussion on translating carbon fundamental research into scalable sustainable technologies. Over the past decade, we have witnessed the remarkable advances in carbon science, be it in advanced materials, energy storage, environmental remediation, or functional interfaces. The science is evolving rapidly, and the possibilities seems almost limitless. And yet, a fundamental question arises: why do so many promising discoveries remain confined to the lab? The journey from fundamental insight to the real world impact is neither straightforward nor guaranteed. It requires not just good science, but also engineering scale up, economical viability, industry alignment, and policy support. In many ways, this journey is where the real challenge and the real opportunities lies. So the real question is not that can we do great science? We clearly can, but the real question is, can we translate that science into something that works at scale, survives in the market, and truly contributes to the sustainability? Today's panel brings together the distinguished experts who represent different but interconnected parts of this ecosystem: academia, translational research, and the startup industry. Their perspectives will help us understand not just what the challenges are, but more importantly, how we can collectively overcome them. With that, let me invite our esteemed panelists, Dr. Tata Rao, Dr. S. Anandan, and Dr. Raghu Shripad, to join me on the dais and start their perspectives. Please. Icon. Yeah, so let me start with a simple and fundamental question to each one of you. And I will start with Dr. Tata. What does this translation really mean to you, and where we are getting it wrong today?
Thank you for inviting me to this panel discussion. And then the question what you said, I slightly differ because actually we are not going very wrong. We are going in the right direction with time. But this question is pertinent some time back, maybe 10 years, 15 years back. But now, with the government initiatives and then a lot of approach and then proactiveness towards the self-reliance, I think even institutes, including your institute, so the day you start your research, you already look for how to translate it, at least at the small TRL 3-4 level. Then the institutes like ARC and they pick up, and then so we are the standing example for that kind of translation research. And then the wrong is that in academic institutes, I tell the faculty that although the insistence is there to take to the translation, but as I said in my opening speech, the deep fundamental research is very important if you want to get good technology also. The contribution of academic institutes, especially like primary institutes like Tier 1 institute like IIT, I think you should focus more on the fundamental side while you collaborate with the research labs or industry. Then they will take to the next level and the translation happens. Otherwise, translation happens to some level, but it will not really take to the fruitful end.
So let me clarify when I am asking you that where we are getting it wrong. So for example, of course, we are doing very well in terms of startups, but most of them are in the softwares. When it comes to the deep tech startups, I think we are still struggling. And even with this field, when we are talking about the carbon energy storage, we have recently seen an example of Log9, which was very successful, and they were doing really very well. But all of a sudden, they had the problems. So in that context, what do you see that?
Yes. Thank you for make me understand the exact question. The Log9, for example, since you are taking, Log9 started so well because L2 has got great promise for the fast charging lithium titanate compared to the carbon, but it has a smaller voltage. The voltage of the cell is less. So the range is a big problem for any electric vehicle when you use LTO battery. But they went ahead with LTO battery, and then there are no takers because once you have the technology, they were doing the electric vehicles and they were also doing the batteries, and that is only sufficient for them. But that will never happen if you want to really become number one, because your battery technology should also be servicing to the other companies. And unfortunately, the manufacturing companies of electric vehicles, they are not ready yet for the LTO batteries. So that will not could not take off. And then their usage of the because the market is not really flushing, so they could not make it. And it was so unfortunate that Log9, it took really like a quantum and then took back. I hope it will again come back at some time. Thank you.
Thank you, Dr. Tata. So let me ask this question to Dr. Anandan, that what does this translation mean to you, especially when it comes to the carbon research? You are working in carbon research, you are working with the ARCI doing the translational research. So what does it mean for you? And again, are we at the right path?
So first of all, very good morning to all. And then I thank Professor Sharma for giving this opportunity to be in that panel discussion. And then it is a privilege and honor to share the dais with my former director and my guru, and then be along with him. This is the first time. So coming in,
I'm also very happy because I'm sitting with my colleague and sharing the dais.
Yeah, yes. Coming to your question on that translational. So basically, translation means how we are progressing lab scale discovery into that the deployable technology through the integration of process, electrode engineering, system integration, validation at the realistic condition. That is very important. To ensure that you need to have that structure, process, property, performance correlations, which is invariant at any scale, wherever it is lab scale or in that large scale level. So I will take that two example of ARCI, what we have done for that. One is for carbon, another one is for LFP material technology. Coming into that carbon material, so we want to design the high performance porous carbon material for supercapacitor application. So it was initiated by our former director. So we want to, it is not only designing the material, we want to go the system level integration and then testing level. So initially we started with the bio-waste. Bio-waste, you know that a lot of challenges, limited carbon content, lot of ash content, so many things are there. So we started with that. Unfortunately, there was no ash content in our bio-waste. We selected the jute stick. So when we are converting into the carbon material, we got only 35% yield. So remaining 65%, it is going as a volatile. So if you want to proceed for translation research, here itself you are facing the issue, which is not attractive. 35% only yield, and then 65% volatility is going. For the treatment you have to do, and then a lot of environmental impact and all it is there. So then we understood the condition, and then we started working on that, the other waste called the pet coke, where that the initial precursor concentration itself 95% carbon, and then 3 to 5% sulfur. When we were converted this carbon pet coke into carbon material, we got that nearly 70% yield, which is commercially attractive. So that kind of attention, or the key aspect when we are selecting the precursor, one has to seriously look into the precursor material. So we have achieved that property. It is not about that achieving that the converting into the hot porous carbon material. We have to look into the various aspects. For example, the tap density, the surface area. So sometime in the lab scale we may excited, we got that 2000 meters squared per gram. But it is attractive, you will get that performance, but at the same time, when you go for the system integration, you have facing lot of issue. Electrode fabrication with 2000 meters squared per gram material, you cannot achieve the desired mass loading. Finally, you will end up with the poor capacitance, poor capacity in the final cell. So those kind of target material property is very important. So that and all we have done for this pet coke derived carbon, and then successfully we have that converted into that electrode, and then we have fabricated 1200 farad supercapacitor, and then we have demonstrated for that EV applications and all. Similarly, if I want to talk about that LFP cathode material, all that inventors are here. Our former director, current director, and myself, we are the three. We have developed that LFP cathode material technology. So initially, I think all of you must have seen TN sir presentation. Many times he must have insisted that why we want to develop a very cost-effective process. So initially, for that LFP cathode material, you need a nano-size LFP particle and then carbon coating. We have started with the two-step process, and then even though performance is at par with the commercial material, but the problem is it is a multi-step process. Again, lot of solvent involved in that. Then we started thinking about that single-step process for making LFP cathode material. We have done that, and then slowly again the next step. We have initially used that imported milling equipment, and then when we estimated the cost, it is going above that the cost of the commercial material. And then try to indigenize the milling unit and then the furnace. Finally, we have delivered that material which is on par with the commercial material. So many aspects we have to consider if you really want to translate lab scale research into that translational research. And the other important thing is, so we have to do kind of third party validation, which we have done based on our the former director recommendation. For LFP cathode material, we went to the IIT Bombay. We have given material with the same material, they have done the cell, and then we have made the cell at ARC. Both we have compared and then benchmark. That kind of confidence, all the industry, they are looking forward if you want to transfer the technology. So lot of these aspects we have to consider if you want to translate the lab scale research into that technology. And then the other question you were asking, where we are getting wrong. So I completely agree with the TN sir. So there are the challenges. It is we are not going wrong. There are challenges. So when we are doing that large scale synthesis, batch to batch, the consistency is not there in terms of surface area, particle morphology, and then tap density. There are a lot of issues are there. So that you have to optimize the condition to maintain the batch to batch consistency. The other thing is that the scalable process right from the beginning you have to develop. So there, if you are developing multi-step process and then handling that solvent, and then that is really challenges when we go for that upscaling and all. And the other thing is, mostly when we are in TRL level 3, always we look for that the extraordinary property. But sometimes it is not required. As I mentioned in the previous, surface area for supercapacitor material only 1500 meters square is more than sufficient. You don't need to go for 2500. It may be excited for us, but really you don't need that much thing. Why you need to concentrate on that? You have to convert those material into electrode. That electrode going into the system. So you have to fine tune the properties if you want to go the system level. For that one, we are not doing that correct. And then another important thing is mostly we restrict our experiment with the half cell studies. When you go for full cell studies only, you really understand that what is the practical challenges. Right from that beginning NIP ratio, negative to positive electrode ratio, and then initial Coulombic efficiency, what is the mass balancing. Those things and all we have to address at the full scale level so that you will have that better understanding for that system level fabrications and all. And the other important thing is the techno-economic and life cycle that we have to carefully consider. What is that energy input, precursor cost, yield, and the environmental impact. Those things and all, right from the day one, we have to consider all the things. So when we consider all the things, successfully we can translate our lab scale into that translational and then suitable for that society.
Thank you, Dr. Anandan. I think you have really provided a lot of fundamental insights about the problem. So I will take this question to Raghu. Now you are at the forefront of doing this at the from lab scale to the you have your own startup, Pilot Energy. So in your view, what does it mean when we say the translation, especially into the carbon research, and where are we? Are we on the right track, or there are certain things which we still need to address?
Yeah, first of all, good morning, everyone. I wish you all a wonderful day. And I'll first I have to thank Professor Sharma to be inviting me to be part of such a distinguished panel. And so coming to the question, as today I'm representing a startup industry, so we have a different point of view from academic or other institutions. So when we wanted to use any carbon materials, so what we look at is the material very consistent? Each and every time when we are receiving the batch, whether the properties are same. If there's any change in the property, our end product is completely going to be different, and which market will not accept. Another thing is it economical? Even if I'm replacing an existing solution to a new materials, whether I'm able to make my product at either cheaper or at the same cost. That is another important point which industry typically looks at. Now, I think I partially also agree with Tata sir that we are in the right path. I think Professor Sharma's groups already adopted this path by taking collaboration into starting from academic to the translational researchers like ARCI and industries. I think most of the institutions, especially the reputed ones, should also adopt this model. Now, coming to this, I think Dr. Vijay has touched up, Dr. Srinivasan has touched upon the core key points there. So, as he mentioned, in academic research, we typically get excited with the results. So our purpose is the peak performance we have to achieve, depending on whatever the synthesis methods or how costly they can be, how costly the precursors are. But once that's exciting to researchers, they can publish papers and patents, but it may not translate to industry. Industry needs is consistency, repeatability, and even if it generates, every process generates some wastage. So taking that into account, net effect, whether it is economical or not, that is important. So to put it in a short way, I think the transition means from the beginning when we start the experiment design or research design or project itself, we should keep the end goal in mind, where it has to reach. Accordingly, we should plan the milestones and goals so that we can track it. That's where the real success will exist for the translation to reach to our factory floors.
Thank you, Dr. Raghu. I think you have given very practical advice to the young students who are looking or who are doing their research in this area. So my next question to Dr. Tata is that, given the focus of the government these days, we all know that they are also looking for advanced energy storage devices, a lot of programs, and there are many startups are coming in India. But all of these startups, if you see, they're focusing mainly on, either LTO or LFP based materials. I have not seen many efforts in terms of carbon materials like graphite or even the hard carbon scale up. So what do you see that, where is the scope and how do we take it in the next direction?
No, you see, in graphite case, the main challenge is only, of course, this epsilon, they are doing that one. It is a synthetic graphite. But natural graphite, people are struggling because although it is cheaper, natural graphite, you need spherical graphite powders to have the good tap density, as Anandan said before. So spheroidization of that is one challenge. And second is in natural graphite that keep changing from the place to place. So if you have some inorganic stuff into that, then that will have the resistance and it will have the problem. So you need to have the quality graphite and spheroidization. Otherwise, synthetic graphite, always it's easy to make the way you like, because you're starting from a precursor and then following a standard procedure and making the spherical part. That's what epsilon is doing. But that is up to the lithium ion battery level. But now when you come to the sodium ion and other chemistries, hard carbon is hard to make a reproducible one, because for publications it's okay, because you can keep getting something lignin or some bio waste, this one, and then you keep changing the parameters, you'll get a hard carbon, and then always you characterize it, and then with Raman and other techniques, and then say that it's hard carbon, and do some cycle charge discharge curve, and then you will get. So you can always publish paper, but for a real technology, like you said, it's not so easy. So you need to have a again I say that like epsilon, you need to start with a right precursor and then get the right procedure to make the hard carbon, and then which is reproducible. Otherwise, there is no hard carbon which is available commercially, because there are no standard process for that one. So I think still some of these companies will come with the hard carbon from the chemical synthesis route. And another one, what is like you said, there are future ones also people have to start in the startup in collaboration with the academic institute like you, like silicon, for example. Long time people are working on silicon, but there is no good achievement of this. But there are very promising candidates for anode. So the problem with silicon is volume expansion, that everyone knows. But the smaller the particle, difficult to fracture it, because already it is a smallest one. So take high volume, high loading of the silicon nanoparticles as small as possible, and start putting into the carbon matrix. And then now recently vertically aligned carbon nanotubes are coming, because they have the single direction diffusion, so you can go very high C rates. And then for silicon nanoparticle, if you merge with them, the volume expansion is absorbed by the carbon nanotubes. What is this? So these are some challenging tasks, but very promising, that is going to come. So people have to look for that one than trying the same thing again and again, which will not take to anywhere.
So if I ask the same question in a different way to Dr. Anandan, that are there any future plans from the ARCI to look into the carbon scale-up production, especially like graphite or even the hard carbon?
First, let me highlight that one. So it is about not neglecting that graphite or hard carbon, which is suitable for this energy storage application. It is driven by the two important things. One is techno-commercial aspect, and another one is immediate market demand. If you can see that overall cell cost, nearly 40 to 55% it is coming only from that cathode. And then whereas the graphite is only 10 to 15%. So in that aspect, if they can develop that cost-effective material, significantly they can reduce that the cost of that cell. That is the one the important reason why all this the startup and all, they have been focusing on that LFP-based material. Another one is since that the EV technology is emerging in India, more company they are looking for this kind of material, but unfortunately there is no company in India. So that is the reason all the company they try to invest in that LFP or LTO. Coming into the technical thing, I think all that audience well aware of that. LFP is suitable for Indian tropical condition because of that high thermal and then chemical stabilities and all. And then similarly LTO also, it can operate wide temperature and then it can able to deliver. That combination, it gives that very high power the capability, and then suitable for even we are trying for that drone application and all, that LFP, LTO and all. So coming into that, why that it is not like neglect, why people are not doing that? It is already well established, mature market. the global industry, we keep on getting all the graphite from China and other company. There is a very few opportunity for that this small startup and all enter into that market. So, but still, as sir mentioned that you can work on that synthetic graphite and all, again converting into spherical particle, battery grade thing, you have that still the opportunity. And then coming into that hard carbon material, still lot of engineering. We have to do pore size engineering in terms of surface area, pore volume, pore diameter. We have to do that two different pore size engineering. One is for supercapacitor, another one for hard carbon. So supercapacitor, you need that high surface area, whereas hard carbon you need less than 10 meters squared per gram. And then similarly that micro meso pores and then tap density, those things and all we have to optimize. So still there are lot of opportunity we cannot neglect. There are opportunity for graphite, battery grade graphite as well as that the hard carbon suitable for sodium ion battery. So coming into that our effort on this one, upscaling. So we have been working on both bio as well as industrial waste. Based on our experience, we understand that the kind of industrial waste which is having that more of carbon, that would be the suitable. Again, we have been tried all the bio waste, lot of ash content and all it is there. Again, you have to do the further processing. You have to use that acid, strong acid, and then you need more of water for that dilution, all the things. So that kind of the industrial carbon waste we have to select for designing that high carbon, hard carbon material for sodium ion batteries and all.
Dr. Raghu, so especially in your startup, what is your strategy in terms of carbon material, carbon anode? Are you also looking into some direct purchase from the import, or do you have any plans to venture into this area?
So today, for supercapacitors, lithium or sodium ion batteries, wherever it is, there's no battery without carbon, definitely. Today, we are completely imported dependent on the graphite and other allied carbon materials. I'll come with the industry point of view, how it is affecting us. So when we import material, once we have import dependency, and today we are seeing there are many geopolitical issues. Anytime, anything can happen with any other country. So that can be a critical point where we may not get import materials. In addition to that, we pay import duty. That means the end user also paying extra cost for that. And it is also important that, especially for the energy security, we should have a local supply chain that everyone understands. We have a lot of graphite resources. We also have petroleum as well. So it should be very obvious that we should be able to make graphite. Of course, Epsilon is in a right path, but even to reach where they are, it took them some time. In fact, several years they have taken to reach there. So why it is happening? Because especially like if you are working with LFP or NMC kind of materials, it's easy. Like you can optimize the synthesis, you can do some dopants and control the parameters, how to synthesize them. And you can replicate in the larger scale, in pilot scales. But coming to graphite, it involves processes which reaches very high temperatures, rigorous processes which are very expensive. So that's why the startups or research groups cannot really venture into that. I think to solve this problem, what I see is, I think a consortium model might work, wherein academic researchers and translation researchers like ARCI and startups and industry, if they come together and plan a phased-wise project, like what is the tier level you want to achieve, in what timeline, then when you want to do it, execute it at a pilot scale, then when you want to do a pre-commercial production. So put it in a detailed manner, and then initial phase academia and translation researchers will be contributing more. As they scale up, the industry comes in. From there, they can take it forward. In that way, so even from the beginning onwards, we're in the right track, because the questions what academic researchers ask, they are different from what the industry really asks. So these all things can be aligned. If all these 4 parameters aligned from the beginning onwards, I think we can achieve that. It might take some time, but still it's the need of the hour. I think we must have the not only graphite, even the hard carbon is also critical now, as sodium batteries can be much cheaper compared to lithium, and we do not have lithium resources. So hard carbon is also very important for us to have it locally.
Thank you. So similar to this, my next question is to Dr. Tata again. That of course now graphite, hard carbon, another major important carbon materials which we are almost 100% importing is carbon fibers, right? Despite we have the fundamental knowledge, lab skill technologies, but we are still not able to produce the carbon fibers in this country. So, in your opinion, what are the key barriers in this area?
It's a very good question you asked. Say, maybe 15 years back, NAL started this actually. And then Reliance also were interested, they put a lot of money. But that time the technology, they just, it is a turnkey based technology, and then the productivity is not good enough. Of course, we have expert Jain Saab is very much associated with when he was in NPL at that time. But the unfortunate thing is it never took off for one reason, that for any kind of technology, as I have been insisting, the fundamental research and then knowledge is very important. To get a carbon fiber of what is required, whether it is T700, T1000 or more, and it is the precursor polymer that is important, where you have to control all the parameters starting from its molecular weight and then block copolymers to connect them and all. So we lack that. We never focused on the scientific part. We're only getting some, import the precursor again, ready, and then put it. So we also visited some textile industry. Which textile industry we visited? Pasupati textile industries. What was the precursor they were using? Pan fiber. So pan is very simple one, what we use in textile. But the pan for that fiber, carbon fiber, that is a long molecular chain one, and then with heavy molecular weight, and that is not done. And then when we were visited, myself and Jain Saab, during my time at ARCI, we visited a Russian company where they were producing the carbon fiber. And then majority of the research is how to make the precursor that is suitable, and then keep on changing the parameter. There is a pilot facility where they focus on the precursor development and the fiber development. From there on, they will take off the top. That is lacking. I don't see any lab working on the precursor part rather than just going, because converting a fiber to a polymer fiber to carbon is very easy. You can take your shirt and put it in nitrogen atmosphere, you will get a carbon shirt probably. But this is not the way. So I think the companies, again, ARCI is entering into that. I am sure Dr. Vijay is putting a lot of efforts with defense organizations to take it forward. But the challenge is still, unless you have the fundamental stuff, and you being a chemical engineer, and then you being a carbon specialist, I think with ARC you should take maybe 1 or 2 PhD students and focus on this while ARC is establishing their pilot facility. But we can do that.
Yeah, I think that is something which we must look into, because carbon fiber is such a very...
because the need for carbon fiber is very heavy. It is not just aerospace industry. All your hydrogen storage, if you need 750 bar storage in the container, it is based on carbon fiber only, right? Yeah.
So my next question is to Dr. Anandan. So many carbon technologies, they claim the sustainability, net zero. So how do we ensure that they are truly net positive, and when they are assessed over their full life cycle?
So very good question. That sustainability in carbon material, it is not just about using biomass or bio waste. There are a lot of entire life cycle assessment and the economical analysis. A lot of other things has to decide that whether it is net positive and all. To ensure net positive effect, first one is life cycle assessment we have to do right from the raw material to that the end of life. And then you have to quantify many metrics, including that how much the CO2 emission it is happening, what is the energy it is required, and then the water usage to neutralize the things, and then that yield. Yield is very important factor. So if the yield is less means a lot of other volatile organic compound, it goes environment. It creates a lot of environmental concern. So and then you have to again spend for that processing those waste for that neutralization and all. So a lot of other things you have to consider. And then, so as other panelists mentioned, always it is the high intense, the atmosphere it is required, high energy required for the synthesis of all the hot carbon or graphite, because you have to do the heat treatment at 900 to 1400 degrees centigrade. It is all the high energy intensive process for the synthesis of all this carbon material. And then, so recently they have asking that regulation, how much kg of CO2 per kilowatt hour it is emitting into the environment. That kind of that analysis recently they have been asking that. And then, so that economic feasibility in terms of that cost or the scalability, those things and all, it is important. So if you are not considering those aspects, simply saying that net positive, that claim may not be that correct. And then that benchmark against the commercial one, whether it is graphite or that hot carbon, those things and all, we have to do it. And then that supply chain impact, transport and pre-processing, often not considered. So these are all that the various aspects that we have to consider, and then we have to make that claim. Once all it is in that in the commercial, on par with the commercial material, then we can claim that it is all that net positive things and all. That is the.
Thank you. I think supply chain management is very integral, and often we miss that part. So Raghu, my question is to you. We often hear about this valley of death. In fact, Dr. Tata was mentioning, right, in the inaugural address. This is valley of death in the innovation and to impact journey. Can you elaborate? Is this valley of death is between the lab and the market? Is it a funding problem, or a mindset problem, or something, a collaboration problem? What do you think?
So here, definitely, I mean, obviously once a company or a startup works on this, so whenever there's a failure, the obvious thing is a funding problem. This is the obvious thing which people can point out at. But today, I think funding is available much better compared to earlier. So there are people waiting to invest money. So the point is, are you pitching your case properly? Are you de-risking the product development in an effective manner so that investors come in? So that's an important thing to think. Coming to valley of death, why usually it is happening is like as we start developing product, initially we think of my product should be superior to any other product existing in the market. Again, we focus on the peak performance, forgetting complete value chain, like you are getting a precursor somewhere, you have import dependency, or whether your precursors are really available widely in a larger scale. If it is not, even though the product is successful, it cannot reach the manufacturing scalability. That is one thing investor also look at. Another thing is you may have certain process. When with the process you have achieved a great product, but is the process really scalable? And a factory can replicate that particular process is another important thing. And apart from that, are you reaching all the regulatory compliances? And when investor want to come in, he thinks each and every aspect, like it is, they call it de-risking from step-by-step manner. Your starting precursors, your process, once you make the product perfect, are there takers, whether market is ready to buy it. Even though you make the best product in the world, if there are no takers, you're not getting funding. That's how the valley of death we typically see. But it's not just that. Why it's also happening is, again, as we discussed, the mindset. Like we need to come out of the mindset like I need to make a best product. We need to see what market needs. So always we need to talk to the customers first. They have a sometimes existing product, but beyond that, what they're looking at, what problems they're facing. Keeping that in mind, we need to plan the strategy. So sometimes X product, you may need X plus 2 delta, but you don't need to target X plus 10 delta. Even if you get it, but if it is not economical, industry will not take it, and you would not get funding. So that's where you need to look at. So whenever you start up our industry plans, look at the customer, what really customer needs, and how you de-risk at each and every step. That's how we can tackle this problem of value of death for a startup especially. And how do we achieve this? Again, keeping everybody in loop. Like if I'm a startup, I need to talk to the customer first, allied industries, and then I need to convince my investors also to put in money. And I also need to show him like how do I project, give the financial projections, for example, once I have a product. Even that also should be a very robust way we need to prepare. So once we achieve all these things, the funding should not be a problem. But most startups fail here, like somewhere or the other de-risking factor they lose, and that's where this kicks in, the value of death.
So, Doctor, would you like to add, because you often talk about this value of death in your talks. So, for you, what is this?
Basic work culture, the country is that we don't want to take risk. Because value of death, the name value of death came because while you cross the translation from TRL 3 to 4, 5, 6, is a challenge of scaling up. And then it is not just scaling up. Scaling up means at the cost with the environment friendly, a lot of factors come. Otherwise, we scaled up several things and we failed during our time. So, but if you see Japan or China, even if the fundamental that itself, they start thinking that whether when I'm working, whether this can be scalable or not. And then many times they succeed also. So when I was in Japan, whenever we go to boss, Professor Fukushima, about some good results, he says immediately call patent attorneys, whether it's a patentable or they call the industry guys. So then you publish, otherwise just go for patent. So it is easy to get multiple publications than taking one publication, one result to the TRL, high TRL levels, which is not there in our culture. It's not nothing wrong in that one. But I think that psychology and then work culture should change. Then definitely it will. Being an academician, you take up to TRL 4, 5 level and say that it is scalable. And then let these guys take off. And it is going to come.
Thank you. So in that connection itself, my question to you is that what should a PhD student working in this area of carbon materials do differently today if they want their research to create the real world impact? So they should ask, are they taking the right questions? Are they designing the research considering the scale in mind? Or they should look for the building partnership to consider their ideas into impact. So what is your advice to the PhD student who are working?
See, first to start with, the PhD students should choose not just one problem, they should choose two problems. One is towards a high risk, high rewarding. That one has to take as one channel, and other channel, because you need to have PhD degree and publications, you keep doing because a lot of problems are there where they generate good publications when you have the fundamental knowledge and right guide and right kind of system and right kind of institute you have. But the taking the second path will take you to a long way, because one, you learn the issues what are associated with the technology development right at the beginning, and two, while you are working for your PhD and the coursework and all, you are getting a lot of fundamental insights. And then also make sure that some people I see that their publications, even many of the students I know, they start is easy to take during my nanotechnology time, silver synthesis. You make silver with any kind of biological or plant-based and all, some silver nanoparticle, keep publishing. And similar is the case with the carbon anodes. You take any bio-waste and then convert to carbon, and then some charge discharge will come and then you keep publishing. But that is not the way. So when you get your material to start, then you start thinking that whether this will take me to the some way, or do few experiments and then give up. Otherwise, once you get into some 6 months, 1 year and tie up, hang up with the wrong choice, then you cannot take it back and you already lost 1 year. So somehow you want to publish paper and then PhD Caracas, but you will lose it. So in first, when you start a new experiment and new concept, first few months or 6 months, thorough research, thorough literature survey and discussions, and then do some fundamental experiments and make sure that that will take you to the next level. Just give up. And we did, during my PhD, I did the same thing. Several of things I gave up after 6 months, and then I got into some new one because I know that it will not sustain, and then I will not get anything in the future as postdoc, because of course we have to build our career. So PhD students should do that. I think that then that will, and of course, some of our students are doing that, but in general I am telling, on a country overall, this is a problem.
Can I add something to that?
Yes, I was about to come to you. Yes.
So, I mean, I have been part of that journey. During my PhD also, like, we were developing wonderful materials which can go for 10,000 cycles also, but now I have my own company, but I can't replicate it in a real world scenario. So what I think we should also do is, if a PhD student is taking a problem which in future is going to scale, take one industry person into the committee. I'm sure in most of the research institutions now, they have something called doctoral committee with that name or some other name, which they typically review every 6 months or 1 year. Also include any industrial into the panel. And he can simply ask the right questions during these review meetings and give some directions. That itself can direct the student in a right path to the scale.
Yeah, thanks for this. So I think before we go to the audience for a couple of questions, I would like to ask each one of you very concisely that in your opinion, what is needed most to translate this carbon research into the scalable technologies? Is it better science, better engineering, better policy, or better collaboration? Dr. Anandan.
Question. I would say that the integration of science, engineering, and then industry collaboration. All three expertise it is required for the successful translation of lab scale into the commercial technology. Because as a scientist, chemist, I don't know about that engineering side, designing the reactor for that to scale up those things and all. And then at the same time, we should know that what is the requirement from the industry. So this way that connect the material science and then engineer and then industry collaboration, that all three work together, and then we have to bring that the lab scale research into that translation research. One of the live example we are sitting here. So sir is TN sir is the chemistry background. Our director is engineering, chemical engineering background. Mine is that chemistry background. So we have worked on that materials development. And then sir has worked on all that designing reactor and then how to go for that upscaling and all. Finally, we went to the industry for that upscaling into that large scale demonstration of our lab scale process, which we developed at 1 kg level into 15 kg level. And then after that, again, it is about the excitement. We got that 20 kg material. But how it is suitable for that system integration and all, that is very much important if you want to see your material into the end product. For example, ours is lithium-ion cell, those things and all. And then again the benchmarking and then cost. All this aspect, it is very important. But the interdisciplinary research, it is very essential for the successful translation of lab scale into that commercial technology. And the other thing, our director nowadays keep on saying that if we want to convert that invention to innovation, the speed is required. Today also he was highlighting that part. So already we missed the bus for that lithium-ion battery. So this is the high time where we can do that lot of research on sodium-ion battery, whether it is cathode and then anode material, where we combine work together and then bring the technology which is suitable for India as well as to make India self-reliance.
Thank you, Dr. Anand. So, Dr. Tata, in your opinion, what is needed most to convert these technologies into the translational research? Would you agree what Dr. Anand mentioned, or you have some other opinion about it?
No, I I totally agree with him because that all happened with all of us together. But interdisciplinary is very important. When you talk about, you can never see science, engineering, and the technology differently, because even you say that I got excellent concept, that is proof of concept, that is shown at the TRL3 level, but during the scale up and then when you're crossing 4, 5, 6, you always need this fundamental concept, because when we were building nano silver reactor for our earlier, we transferred this technology to Resil Chemicals Limited, and now they got a lot of money, and then now 7 years close, and still they are working on that one. So we showed that nano silver can be made in the size what we want and the 100 ml level, but they want 15 liters capacity, and then mixing the precursors. Chemistry is simple, but mixing them in the right speed and right fluid dynamics, all this we don't know. We are only chemists. So then we went with a company, and then the company we gave the inputs, and company started giving the reactor design, even the blade angle and some of the stoppers that we never know. I never thought that makes a difference. And that took almost 1 year for us to optimize at 15 liters level, and then finally it worked, and then the technology was successful. So it's all important, and the fundamental inputs at each level of the development is very important. So it is interdisciplinary, not one lab can do all the things, and then thinking that also has no meaning.
Yeah, that's what I think the role of chemical engineering comes in.
Yeah. I totally agree with you.
So I think before we go to the audience for a couple of questions, so Raghu, what is your opinion very quickly on this?
So when I think of this, I recollect of one thing, like when I was in Israel, I worked in a project, something called Horizon 2020. The model is like this. So they have one common goal. There are 8 countries participating in that. From each country, there are 1 or 2 or 3 research groups. Total, there are 15 research groups and 3 industries part of that project. Their aim is to develop 2 products. And every research group has given goals, and the TRL levels also defined further the timeline and what work package they are working on. This is that's how executed in a phase-wise manner. In phase 1, it's for 2 years. Industry will guide them. They will provide their raw materials to these companies. Today, our research groups, we mostly buy from Sigma, Aldrich, or Merck, but not what the raw material industry use. So initially, industry guides them what we really need, what is the requirement, and they provide their raw materials. These research groups work with that particular raw materials, and they takes these TRI levels to 2, 3, 4, and 5. After the phase 1 is completed, then the industry takes more active part into that, and academia helps into the further piloting. Then there's the next phase where they go to a pre-commercial scale. And as Tata sir rightly mentioned, for one problem, one research group may not be sufficient. So we can also take 2, 3 well-known research groups for each problem, form a consortium, and clearly define the goals. If I take, for example, develop a lithium-ion battery cell. So I'm using multiple products in that, like graphite, NMC, LFP, or different kinds of carbons, binders, separator. There are many things, but I cannot be expert in each and everything. I should be able to take help from who is expert in what particular component. And then we need to define goals to each of them, what we really need. And then once we have this model and we develop each and every component, at least even though it takes some time, but as a country, we will have expertise in each and every component. So, so we have a control in the components and the quality. So with that, I think we can achieve total independence, at least in the critical areas. I think this is a model which we can replicate with whatever suits to Indian philosophy.
Thank you, Raghu. So I think we can take a couple of questions from the audience to the panelist.
Thank you for your all discussions. I have a question, like we are discussing about the scalable technologies and particularly the carbon materials also. and we have the academia also, and we have the startup also here. So when we are developing the materials, we concern about the materials. I am agree with that, but I am not agreeing one point also of our approach is that okay, let's me I develop a material in the lab. Let's say carbon nanotech lab still, or we have developed that machine to develop that much of scale, because most of the scale it comes with the machine only, because we need a precision, we need a repeatability, we need a cost. So but at the same time we don't get that machines in the Indian market basically. So inherently we have to depend on the another countries, that increase our completely setup mind setup differently actually. So what you can say on that perspective?
It is a excellent question you asked. Most of the time, even now the technology of battery is not coming within the country, although we have been talking about PLS scheme, all this one. Still today we don't have an Indian made battery you can't buy in the, because although institutes like ARCA developed the technology of materials and then they gave to the company and the company is ready to produce and then sell it, the battery cell manufacturing companies are not ready. If this guy has to sell the material, the company has to make the material, battery, like Amar Raja or Exit. Why they are still holding? Because when they make cells and make a battery pack, there should be some electric vehicle guy who should buy this one. And they are always importing. And then they are importing because end of the day, the electric vehicle manufacturer, they should make money because they have to give salaries to the company and they have to make the margins. And then they don't care whether it is Indian or foreigner. They will buy the cheapest one, which is what happening now. So why these Indian companies like Amar Raja, they are not able to compete with the import one? One, because the equipment what they are setting up, like you exactly said, if the plant of 1 gigawatt or 50 gigawatt, the plant comes from somewhere and you have to import. And that makes it very expensive. And then it is not just the material, we need to have our own equipment as well. I keep telling that you import basmati rice, you import the cooker and make biryani, it doesn't make any sense. You can never sell it. At least you cultivate your basmati rice, half the problem at least is solved. That's what we are doing, like ARC is doing now. But that's not enough. You have to make equipment. And ARC also demonstrated some of the equipments during the supercap line fabrication. Some equipment are missed. And then with the help of the present director and then our Anandar and all, we made that some equipment and demonstrated. So unless the manufacturing research is done, and then this gap will continue, and you are 100% right. So people should focus on that as well. Okay? Thank you. You want to add? Just Anandar want to add.
To add on to Sir response. So Sir was saying about that fabrication of that cell, you need that all that imported equipment. When it comes to the material with our limited facility, we will go up to TR level 3. So maybe in the grams level, maximum 100 grams level. Beyond that, if you want to go, that's what Sir was mentioning, that industry collaboration, where they have all sort of facility. For example, our case, we don't have that 20 kg milling unit or continuous pusher type furnace to validate our lab scale process. Where we have actively involved the industry collaboration, there they have all sort of facility. So there you can go up to, you cannot go tens of 1 ton, 2 ton production and all. At least you can go up to that 25 kg, 50 kg level. Once you demonstrate that level, so then that industry come forward. For that, again, the designing of that process. For example, solid state process, if you design within the country, there are specialists who can fabricate that milling unit, who can fabricate that furnace. That kind of scalable process, if you develop within the country, at least material development, you can do it without any issue. But again, that indigenization of equipment for fabrication of cell, that it takes a long time.
But don't worry too much about that, because if you are a PhD student, you keep knowing about the issues and challenges, but you focus on your fundamental research, whatever method it is, because training is very important, fundamental knowledge. Then it can be translated by some other means. But during the PhD time, you should not work think too much about all these things.
He is owning a startup.
Oh, yeah, okay, start. Then you are facing the problem actually. Okay, okay. Oh, is it? I thought you are a PhD student. You look so young. Good, good. All the best. Yeah.
Yeah, good evening, good afternoon. First, I thanks to panelists to the great discussion. I have one question. We have, I think, in graphene kind, graphite and coal material in India is a natural source, and other than we have export the carbon activated carbons, but till now we are lagging in energy battery based grade. Graphite and carbon fiber. So I ask a panelist like that, why we are lagging this field as compared to China and Japan?
I think this question was partly answered during our discussion itself. That Epsilon, they make synthetic graphite already, and then they have their companies in America, and then they supply because wherever demand is there. Epsilon is an Indian company, but they will set up in India only when they have the market. Like I said, for LFP, what our people have established, still they could not sell it because there are no takers. There are no companies there. So it is not that we cannot do that one. In India, we are able to do, and then actually they did it. So it's only the matter of how the business model and the entire chain of the technology that should sustain, like the reason why I said, if you don't have equipment manufacturing in the country and you have to depend, then that gives a problem. Otherwise, technology of making the materials is not an issue. Okay? So exporting will come when you have these problems solved, because even our people make LFP today with all these equipment. If the cost is not matching with the import, because a person in America, they import from China, they import from India, and they should match. And the cost comes in two ways. One is, like we discussed, the equipment and then raw material supply chain, blah, blah. And the second one is scaling. So unless you scale it as economy of scale, as the scale goes up, the cost comes down. So for that also, the business has to be sustained. And another problem in the country is that the incentives, what are coming from the government, they go to the battery manufacturers are the high-end ones, but the component, because if you take battery, you have the current collectors, copper and aluminum foil, you have the aluminum cans. So a lot of things are there, which also still these companies import, although we can make all these things within the country, because these people don't make unless there is a demand. So it is not impossible in the country, only the demand has to be created, that's all.
So thanks for enlightening us regarding this experimental difficulty, and I am a computational material chemist.
Then you will ask more difficult questions.
No, it is not difficult question. It is like, our common goal is to develop the technology and go for a Viksit Bharat, that how our Bharat can be Atmanirbhar in that sense. So what I feel, there is a gap between this development of materials from the computational point of view, how decrease the time, so that it will not take 10 years with the use of computational tools and AML that can be doable in a certain years. So that means the material discovery, we are in the right direction, but we can enhance in the certain ways. So my question is there any gap you feel inside India? Because outside I know basically there is an inverse design. What you want from your expertise, can you tell us? Then we'll work for 1 year, and next 4 years or 5 years, then you can go for that synthesis and other materials will be there. So my question is how we can help you whenever you are talking about your experimental point of view. Because as a computational chemist, I always think, I wish I could have your brain like an experiment so that I can apply that one in my computational research. So that's why how we can help you so that the problem you are facing, maybe atomistic models, AIML or anything, because I am a person, I am also doing AIML and computational molecular dynamics. There are very exciting areas in terms of battery, electrode, electrolyte and so on. That's what, can you please, three of you, I request enlighten this one.
So the computational chemists, AIML scientists, and the experimentalists, they live in silos. They work in silos. They never talk to each other because you want to publish your paper, and then I want to do my experiments, and then I want to publish my paper, and then sometimes we feel that we are competitors each other. So that is the problem. We know each other also for a long time, and then I never tested your outcome of your computational this one what you want. So it never happened because I feel that okay, I am working with my LF, my few materials what we are working there, and then we go on that. So what is required is especially with the faster computational models and the AI ML techniques and all. I think the screening of the materials and then predictive models, they really help to cite some of these combinations which immediately it has to be tested by some experimentalist. So it is like that. If you are doing that, you need to have some collaborator within the IIT to just say that yes, you take Narendra Kora, you take him or anyone, and then get it tested that it is possible or first of all it works or not. It may not be taking a big leap in the first instance, but then once you go to that level, then the research institutes or industry will take. It is very, very important that is missing. Elsewhere they do that. That's why they keep coming with the materials with slight modification. Even the LFP itself has got several brands with slight modification. They will tell you what kind of LFP you want. You want high charging rate, high energy density, high long range and all, because these are all coming like this only. So we need to have the collaborations right from the beginning. The day you plan to make a material and design, you start talking with the people, experimentalists, and then start working, then your life becomes easy and their life too.
Yeah. So one of the potential opportunity for the theoretician to work on that hot carbon, you need a lot of engineering aspect you have to solve that issue. One of the major issue what we are facing is that initial coulombic efficiency, it is very poor. Whether it is bio-waste or industry waste derived carbon, we are getting only about 60 to 70% initial coulombic efficiency. Lot of sodium ion it get accumulated in that SEA layer and all. It is not reversible. And then there again a lot of aspect we have to consider, that number of closed pore. There are capacity gained in two ways. One is absorption, another one is sodium ion diffusion. So more of diffusion it should happen in that the closed pores. So where you can define that when I am putting this much percentage of open pore, closed pore, what is my output? Whether I am getting that able to improve the initial coulombic efficiency. If experimentalist, if we start doing that, it takes time. With your theoretical that expertise, if we give our input in terms of open pore, closed pore, and then surface area, and then that electrolyte additive, those kind of information if we can give, and then if you can predict this many experiment, this many things, and then we take that selected experiment and then do that. That's where theoretician and then experimentalist, we can work together, at least for to develop that high performance hard carbon materials and all.
Thank you, Dr. Tata, Anandan, and Dr. Raghu for this very insightful discussion and interesting discussion after that. Let me very briefly summarize what we have discussed in the last 1 hour or so. We discussed about what does it mean in terms of translational research. We discussed especially in terms of carbon materials, where we need to focus on in terms of translational research, be it the carbon fibers or the hard carbon or even the synthetic graphite, which is required for the self-reliant India. Then also we discussed about the challenges before the researchers in terms of valley of death before commercializing and going into the scale-up. And also we briefly discussed about the path forward for our PhD students to focus on when they're starting their research, that how do they need to think about the problems in terms of making an impact in the long term. And finally, we discussed about the importance of not just science, but also the engineering aspects, and of course, the benefit of collaboration across the disciplines. If we really want to make an impact, if we really want to develop the technologies for the societal benefits. So with this, and in fact, among the science and engineering, of course, the last question, Professor Bhavani, about the collaboration between the computational and the experimental people, of course, and that's how we are doing it from last 4 years. Yeah. So with that, I must thank all the panelists for their time and then very fundamental insights about this. We have a token of appreciation for the panelists before we close the session.
No.
We will take a break now for lunch. Lunch is arranged at the fourth floor of the fourth floor dining hall of the guest house. So we'll proceed now, and we will reassemble here at 2 o'clock for the first technical session on carbon fundamentals. Thank you.
a postdoctoral fellow at the Carbon Laboratory and pass out PhD graduate from the Carbon Laboratory. And it is my pleasure to chair this session on advances in carbon materials from fundamentals to applications. So carbon materials have been the heart of modern innovation, driving breakthroughs in energy storage and conversion. Along with that, it has played a huge role in environmental sustainability and developing next generation technologies towards bettering the human life and at the atmosphere at the whole. So today's session, this technical session, brings together diverse perspectives across both the fundamental research and the practical applications. We have an excellent lineup of speakers today. Each presentation will be followed by a 5-minute Q&A where you can ask your questions, queries, doubts, or your suggestions you can ask with the speaker. And I will be very happy if the audience actively engages in this session and I will kindly request the speakers to adhere to the allotted time. So our first speaker is Dr. P.K. Jain from ARCI Hyderabad. He is an associate director with expertise in carbon composites and advanced materials, contributing significantly to translational research and technology development, including several high-impact national projects. I invite Dr. P.K. Jain sir to kindly deliver his talk to the audience.
Okay, right. Thank you, Ankit. Good afternoon. It's always a big challenge post-lunch session. And that to be when you have heard that it is a first time in first. But do justice with the carbon. Good human resource. Okay. Or other. Just check it out. After lunch, still they are there. Okay. Okay. In online, you have an advantage. You just switch on and then go do whatever you want to do. We also do some things. Okay. Those who have not visited must visit ARCI, one of the beautiful campus we have. And as it told that we are working on different materials, like carbon materials. I look after the carbon, the advanced ceramic, and sol gel coatings. As I told you, we are materials research lab and we do a lot of processing like laser processing or the coatings centers are there. Center for Nanomaterials where Dr. T.N. Rao, Dr. Vijay, Dr. Sharda, Dr. Anandan, they all are associated with nano, but we work on to a different type of carbon. I'll just show you. The Center for Fuel Cells and Center for Automotive Materials, they are located in Chennai. And we have a Center for Technology Transfer, which is the bridge between the two, the industry and the institute. So they look after the requirement of the industry, all our legal things they look after. We have a one unit in the Gurugram Center also. Till now we have transferred many technologies, some of them are listed here. And of course, some of them are which are not listed because few of them are added. Now we have transferred LFP and other technologies also. Last two are the technologies where I was directly involved. Now I am confined to the carbon. We have seen that carbon since morning, people are talking about it is being used now in the batteries. So people are more concentrated about the carbon as a powder. But carbon as a bulk is also having a lot of applications. So as you know, carbon by nature, it has given a very good inherent properties, one of the hardest material, one of the softest material, one of all sort of properties you can do, all sort of tailoring. Everything is possible with the carbon. You can make the high surface area carbon, the low surface area, depending on your applications. Now this fullerenes and carbon nanotubes and graphene has added the value of the carbon. But before that also carbon was very, very important into the strategic applications. Now as we know carbon, why it is hard, why it is soft, because of the hybridization. Of course, we will not talk about the diamond, because diamond itself is a big material for the, not only for the ornament, but for the strategic applications also. Why graphite is very, very important? These are the inherent properties which makes graphite very, very important, like it is having a low density, chemically inert, and a high temperature in electrical conductivity, low coefficient of thermal expansion. All those things are there, self-lubricating, biocompatible, everything. But which makes it is indispensable for high temperature is, this is the only material which can retain the strength at high temperature. There is no other material which can retain the strength at high temperature. This is one of them. Not one of them, the only material. Now, having all those applications, the carbon, the graphite was first used in 1942 in World War, in a missile as a wing. This was having a very good properties, but it has a one negative properties, it is having a brittle structure. You just give a small load, it will break. Like in our pencil, if you have seen, you just cannot use it for the mechanical properties. The structural properties are very, very poor. So then the concept of composite has come. So any material which is, when it is converted into a fiber, will gives the highest properties. So carbon was converted into a fiber, and then that same carbon fiber was mixed with a carbon matrix and make into a carbon-carbon composite, which is called carbon fiber reinforced in carbon matrix. How it is done looks very simple. In morning session, 1 or 2 sentences was there about the carbon fiber. As we know, carbon fiber, we are using it for last 4 decades, 5 decades in India, but not even a single kilogram is made in India. We are all this around 1200 to 1500 tons we import every year. And that is because of where we are finding it, it is indispensable, then only we are importing it. There are hundreds of applications which makes carbon fiber inevitable in many, many areas. But because it is not available freely, we are not using those applications. So this composite was made, as it was told in morning. A carbon fiber is made from the PAN, polyacrylonitrile, the pitch, whatever hydrocarbon, petroleum pitch is there, the vapor grown fiber, rayon based. All fibers are having certain good properties or bad, but the PAN is the mostly it is commercially made PAN fiber. But the pitch fiber is for the high temperature, because that gives the high modulus. One of the highest modulus of graphite can be exploited when you are making it from the pitch fiber. But the carbon fiber, commercially it is from the based fiber. You can just see the diameter of a human hair and the carbon fiber. The human hair is in the bottom and the carbon fiber, it varies from 5 to 7 micron depending on the precursor. As you can see from this graph, the specific modulus and specific strength, one of the highest is into the carbon. All other metals, ceramic, everything is glasses are very, very low. The specific strength and specific modulus is the highest in carbon. And within carbon, once you are making in carbon fiber, that is called the modulus, the high modulus or high strength fibers, the high modulus and high strength. So there are intermediate modulus fiber which have a balance. You have to make a balance, because once you go for a high modulus, you have to compromise with the strength, or vice versa. Now, how carbon fiber is made? As in morning, Dr. Tata has told, if you just take the shirt and burn it, that will convert into carbon fiber. But that fiber will not have any strength. That will not be structural applications. So you require the fibers, anything you burn it, only carbon will left over. But whatever carbon left over should have sufficient strength or sufficient applicability for you. So you require a high molecular weight pen fiber, so that when it convert into carbon, which will give the high strength fiber. So that becomes a big challenge in the engineering part. So science we know, but the engineering is missing, because you have to make a continuous fiber. It was morning also, it was told consistently. When the fiber runs for kilometer, each meter should have, each diameter also should be consistent. The properties should be consistent, which is a big, big challenge. So in India, efforts were made by NAL and others, but somehow could not able to succeed. ARCI is also trying to make it, but not as a development, as we are trying to collaborate with the Russian partners, so that directly we can do that is called lateral technology transfer. We take the technology from Russia and try to develop it here. Now what happens when you take the polymer and convert them into a pen fiber? This, all your shirts, sweaters are made from the polyacrylonitrile, okay? But the modulus or the molecular weight is very, very low, 30,000 to 40,000. But to make it a carbon fiber, you require a specific acrylic fiber, that is called SAF, which should have minimum 2 lakhs of molecular weight. And then you have to convert them into a pen fiber. When it is a thermoplastic, so you have to have a oxidation. Oxidation will give a structure which will convert them into a thermoset. And that there the stretching and other things are very, very critical, and there many fibers the technology fails. So after this stretching, it will convert into oxidized fiber, and that oxidized fiber has to be carbonized and then graphitized. And you can get from this polymer also. And from the petroleum pitch also you will get it. Now this is the carbon fiber. Now carbon fiber is the main load bearing material, but you will not find an applications where unidirectional loads will be there. There will be definitely, like if you see your roof, there will be the rods are bidirectional. So some of the applications require bidirectional, some of the applications require the three-dimensional properties or radial properties. I will show you where it find the radial applications also. The carbon fiber has to weaved accordingly. So depending on your end application, you have to use the carbon fiber either into the cloth form or into three-dimensionals or into different end directions or even the radial. Now when it comes to all aircraft brake pads are made from the carbon fiber composite. There is no brake pad which is available without the carbon composite. Now if you see a 400 tons aircraft, when it comes to at halt in the airport, the speed is 800 kilometer, half mv square. Mass you know, velocity you know, how much energy it will generate. No material can withstand that type of heat except the carbon, because the carbon dissipate heat very, very fast. That's why carbon composite is the inevitable material. Like in all our missiles program, the nose tip, when the missile re-enter into the atmosphere, the temperature touches around 2500 degrees centigrade. There is no material which can withstand 2500 degrees centigrade. So the carbon-carbon composite nose tip is made from this material. Now there is a specific lab in DRDO, ASL, Advanced System Laboratories, which is having a specific dedicated group to make carbon-carbon composite. Now how carbon-carbon composite is made? You take a carbon fiber, whether it depends on your one directional, two directional, three directional or anything, and then you can put them into a thermosetting resin or thermoplastic pitch or hydrocarbon vapor depending on your processing, and then you paralyze it. So all other material will go except the carbon. The leftover, already you started with carbon fiber, so matrix also should also be converted into carbon. And then you continuously do, because when during pyrolysis, a lot of pores comes, you again refill it. That is called the densification process or impregnation cycle. And finally, you will get it when you heat treat it up to 2600, you will get a carbon-carbon composite. Morning it was told why it is not being used, because the high capex is there. No industry can start a carbon-carbon composite less than 100 crore. So, and unless you have that type of capex, you cannot start. And once it is in a government structure, the market is very, very limited. If you put a 1000 crore factory and if you will not get the returns, the factories, the return on investment is very, very low. So that's why only the government can afford, where it is inevitable, whether it is ISRO or DRDO or DAE. All activities related to carbon-carbon is happening into that. But now in the last 1 decade, the government has given a lot of scope for the private industries to come forward. So we also did something like when we have taken, so what exactly, how the properties are controlled? The properties are controlled what type of carbon fiber you are taking, what type of matrix system you are taking, and what is the end heat treatment temperature, and of course the very, very important, the interface. What type of interface is being made between the fiber and the matrix? Because fiber is commercial, matrix is commercial, the processing is only will decide what type of end properties you are going to get it. So we have taken the high strength carbon fiber, different grades are there, HT3 and HTA, the high modulus fiber, which is called HM45, HM35, and of course intermediate also. And the matrix was coal tar pitch and phenolic resin. So what happens when you take the high modulus fiber or high strength fiber, the surface groups will also, because you give the surface treatment, when it is a graphite, it is in a fully structured graphite, convert into a graphite, so the functional group attachment also will be low. When it is in the form of carbon, then only the functional group will be more. So you have a different type of functional groups that will decide what type of interface it will happen. So when we have made a polymer composite, we have found that the fiber which is having a high surface group will have a very, very strong interface, and the polymer matrix gives a very, very high good properties, which you can see from here. The flexure strength is measured. So we found that the flexure strength, the interlaminar shear strength, everything is very high when it is in the polymer stage for a high strength fiber. But when you convert that into a carbon composite, the story changes. The strength of the strong interface will give a different type of matrix failure. You can see if it is either this thing or it is like along the fiber. So this cracks will decide what type, how much load it can take it. And then we have observed that after the secondary heat treatment, that is called a graphitization, the story is completely changed. The strong interface will fail very low load as compared to the comparatively when gap is there. So you can see here, when there is a complete interface, a strong interface, the fracture surface will be catastrophic. When there is a gap, this is like a fiber pull out. When there is a more gap, it will be like this. So ultimately you require a fiber pull out where the energy absorption will be very, very high. This is, I think, repeated. Okay. So what we did, we tried because this carbon composite has to be carbonized and the carbon fiber also undergoes into carbonization. So we tried whether we can take a fiber before the carbonization and take it into convert them in like a in situ carbonization of carbon, this oxidized fiber as well as the matrix. So we have taken the fiber from here, this is called oxidized pen fiber, and then convert them into carbon composite. And we found that the strong interface, because this is at the oxidation level, the oxygen groups are very, very high, the interface is very strong. And the modulus, density, everything is not comparable to the carbon-carbon composite. But when we have converted them into a graphitization temperature, we found that during this there is annular gaps happen in the matrix. And we observed that there is all those things, the coal-tar pitch, when you convert them into a coal-tar pitch where the interface is different as compared to the resin, then properties are different and we got a very good properties. 250, 220 like this. 250 is a flexural strength which is generally you get it in the T300 grade fiber. So this paper was published in a carbon, of course. We have got this mechanical strength of, we call it commercially, it is called Penex fiber, and we can see that the strength is comparable. We also work on carbon nanotubes. This carbon nanotubes, different techniques are there, arc discharge, CVD and many more. So everything is depends on your what type of carbon nanotube you want, you have to adopt that. We also have a arc under water, the fluidized bed reactor. When you make a carbon nanotubes, it is not that easy, whatever you will make it, many times along with the carbon, other graphitic material also forms. So now these graphitic materials will not contribute that way, whatever way you want. So you have to remove those graphitic material. So removing, first identifying, it is not easy because not all techniques will segregate carbon nanotube with the other graphitic material. So you have to have a specific protocol, whether you have to have chemical treatment, thermal treatment and the mechanical treatment to separate those things. If you do a excessive chemical treatment, there is a chance that nanotubes will get degraded. So all those things are depends on your treatment optimization. Many people works on carbon in many forms, whether it is nanotubes or anything, but unless you optimize the parameter, you will not end up. That's why there is a problem, the consistency of the properties. People feel that they are working on nano, but maintaining a consistent property is a big challenge. So you have to have that repeatability in your processing, then only you can do that. So if you optimize the processing of purification, like chemical, thermal or mechanical, then only you will get the high pure carbon. And getting it, how to analyze that is also a different type of challenges. Now once you do this agglomeration comes to another problem. If you disperse into any solution, any solvent, any resin, it will agglomerate. If it is agglomerating, you are making a composite, but all your composites properties will not be consistent. So that's the reason you have to have a proper dispersion. So to know a proper dispersion, you should know what type of dispersion things you have to use it. So one should know the delta potential. I will try to finish it in within 3 minutes. All those things, distribution and dispersion is looks to be similar, but they are different terms. If you do the heat treatment to the carbon nanotubes, you can improve the properties. This is, and you can go through the Raman spectroscopy, how the properties can be improved. Another important properties of carbon nanotube is the field emission properties. This is by nature, because of its atomically sharp tip, it gives a very high field emission. And vertically aligned carbon nanotubes, in our center we have made it, and we did a project for defense because they require a very high emission ratio. So of course the edge carbon gives the highest, so we have used the other center to make it a laser scribing, and that has given a very high current yield. So this is of course don't go by the numbers. The important thing is it gives a very good field emission. Now we are working on to a different type of field emitter where the carbon fiber is being used. Another product we have developed, a exfoliated graphite, where we have taken this graphite flakes chemically treat and expand it, you will get a vermicular structure, and you can press it, roll it without any binder. So the graphite, which was very brittle in nature, can get a flexible graphite. These all those things, you don't go the single stage, all different intercalation, but ultimately these are the products which was made and found in a different industries, like the wheel and axle plant seals, which is used for casting their wheels, the bipolar plate for the fuel cell, these are the fuel cell stack and the bipolar plate. Another important property is it is a highly porous material, so it can absorb the oil from the oil water spills. So we did some, it can be selectively absorb the oil, and around 80 ml per gram oil can be absorbed. The same exfoliated graphite can be used for making a graphene, and we have a small industrial reactor where we can make the graphene in a kilogram level. You can tailor the surface properties by the different treatment from hydrophobic to hydrophilic. This is same graphene is used into a oil, and you can get a very good lubricating oil into our applications. We did, one of the person has completed PhD also in this. Of course, this don't go by that, how much percentage you have to add, all those things are different. As I told you, the arc under water can give you a different type of nanostructure, and these nanostructures sometimes gives a nano onions, carbon nano onions, and those nano onions gives a different type of properties. The recyclability also we initiated some time back, that if you take the old tire tubes, can be also converted into a valuable carbon, and the coin cell was made. We don't work directly because some of the persons they came, we are not from the battery person, but some of the person they do. This is the autoclave where we have developed a graphite foam. This is a highly porous graphite foam where the density is around 0.8, and we got a specific thermal conductivity more than 130. This is a 1 minute I will go, just run fast. Ceramic department, where high temperature this silicon carbide is made for the Aditya L1 mission for our satellite. This is a different type of thrusters and other things is also made from the silicon carbide material. Silicon carbide, this porous filters is used in a heater. This is another big important project, a low expansion glass ceramic, which is used for defense and the space applications. This is used for the gyro applications, our ceramic group works. Anti-mine boot, this honeycomb structure is used for the anti-mine boot, where this person, the soldiers, whenever they will put the step onto the anti-mine, even though blast happens, the most of the impact will be captured by this boot, and you can save the person. Zinc sulfide dome, which is also made by our ceramic group, which is used in our missiles. These are the things. These are the transparent ceramic which is made. We have a very good state of art facilities in our ceramic. A bulletproof, because when you use it, a visor like a helmet can be become bulletproof. But what happened to the glass? The glass is not bulletproof. So the transparent ceramic is being used. SOFC is another activity our ceramic group has started. I will not go through because this is under development, and these are the things. Silicon carbide space mirror. So carbon, we have developed different grades of seals also, and also there. Okay, thank you very much for that. If any questions are there, of course after lunch questions.
Thank you, sir, for the insightful talk and the wonderful applications of the different carbon materials which you have done throughout your lab. We have a 5-minute question answer session, so anybody who is having questions can ask, sir.
Nice talk, sir. I ask one question. Which method you use to graphite to graphene? You show one PPT, you convert graphite to graphene.
your question is how we have converted graphite to graphene.
Yeah,
There
which
are
method
many
you
techniques.
use?
There are many techniques. You can use it any technique. By people have used the tape also, but we have expanded the graphite and then sonicated it. And after sonication, we found that it can be converted into graphene. The parameter has to be optimized. Yeah. Manohar. Mm-hmm. Okay. I think two things you have mixed up. The brittleness is not from the fiber. Brittleness is from the matrix. Okay. So fiber is always a flexible. Whether it is in pen fiber or carbon fiber, it is always flexible. There is no brittleness. The main problem comes the high molecular weight. You cannot extrude easily. To making into a fiber from a pen polymer into an extrusion, and the extrusion is around 14 to 15 micron pen fiber, and that pen fiber at the end it becomes to 5 to 7, so 50% reduction. So this control reduction is another challenge, and then extrusion of 14 to 15 microns of a high molecular weight polymer is another challenge. So that's why we are able to 30,000-40,000 molecular weight, absolutely no problem. We are master in that. Up to 150 also in India, people have attempted. Dr. Tata T.N. Rao has told about Pasupati acrylon. They are making vigorously a pen fiber. They have attempted also to convert into carbon fiber, partially successful, but not into a real terms. Second challenge comes like NAL has done. Okay, the extrusion is one challenge. Then what happens? Extrusion has to retain the morphology, the fiber. So what they got it a bean type structure, not the circular morphology. So what happens when they get a bean type structure as a fiber? It may qualify, but when you convert them into a composite, it will not give you a full properties. There comes the problem. And 90% carbon fibers in India people are targeting for strategic application, where certification and other things are very, very critical. Like whether it is defense or space or anything, where the certifying agencies goes to everything. Like when you translate into a properties, there you will not get the full translation. Yeah, please.
Somewhere you mentioned purified CNT. Basically, if you are deriving carbon from carbon precursor, so how to purify that carbon product from the precursor?
You mean to say that the source is also carbon?
Yeah.
After conversion also it is carbon. So what is the purification process? Okay, good. So in all the cases, whether it is CVD or it is arc discharge, the processing temperatures are different. Okay, when you do the arc discharge, the graphite, you have to bring the two graphite electrode and pass a very high current. So the carbon will convert into vapor, plasma generates, convert into vapor and reorganize themselves into the nanostructure. So depending on that, sometimes C60, sometimes nanotubes, sometimes graphite. All those parameters are not too much controllable because everything is happening into a chamber. So when you are making it, you will get a combination of all. Now what is happening? Each carbon is having a different thermal degradation temperature. Yeah. So you have to optimize that up to what temperature particular carbon will degrade. Okay. And heat treat that particular powder into that temperature in a phase manner. And then you can do that purification.
Okay. Under inert atmosphere.
Okay. And in CVD, the source itself is a gas, hydrocarbon gas. That hydrocarbon you crack into a carbon and then try to deposit it. And you create a condition in such a way with the help of catalyst, metal catalyst, it will grow into nanotubes. Okay. So both nanotubes are different. One is top down, another is bottom up. Okay. Yeah.
Sir, one question here. Sir, you said that like...
He told 5 minutes, so I had to consume
yes.
5 minutes.
So...
okay. Yeah. Pardon?
Metal catalyst, while we are synthesizing these carbon nanotubes, and what would be the role of this metal catalyst in case if these metal catalysts are trapped in the CNT mixtures? So sometimes we consider it as impurities, right?
Okay.
So is there any role in that?
Yeah. See, when you are looking for a CVD-based nanotubes, metal catalysts act as a nucleating point. That around that only the carbon will grow, the nanotube structure will grow. Now this will become like your scooter approach, it is called. The nanotube will be near to the metal catalyst, and how to purify that itself is another technology. Okay? You have to heat treat in such a way or chemical treat it that this the metal catalyst will go away. Like depending on your processing, like if it is a CVD, a generic CVD or a fluidized CVD, you will get a different type of microstructure. If you do any things, you can get even the spiral nanotubes also. So those controls, if you know, then you are having a good control over the synthesis. But in arc discharge, you don't require any metal catalyst. That is through a carbon is converted into vapor of carbon only and redeposited. Everything is happening within the plasma. Okay? Yeah. Okay, if no questions, you can always visit ARCI. Thank you very much. After lunch, clappings are also less. Okay, thank you. And I must thanks Dr. Professor Chandrasekhar Sharma organizing, because we both are into two corners of the city looking after the carbon. Thank you, sir.
Thank you, sir, for the insightful talk. So as we move forward into the session, our next speaker is Dr. Deepu J. Babu, sir, from IIT Hyderabad. He is an assistant professor working at the interface of nanoscience and energy in the Department of Material Science and Engineering, with research on nanoporous and carbon-based materials for separations and carbon capture, with in fact impactful contributions to the sustainable technologies. Connected with the So you have 20 minutes and then 5 minutes question and answers.
Good afternoon, everyone. So I'm Deepu. I'm working in the Department of Material Science. So I'll just start with a video. Just wanted to show you something. So this was during my PhD. I was working on these vertically aligned carbon nanotubes. So we made these vertically aligned carbon nanotubes, and I prepared it by CVD technique, and then I use it for gas adsorption applications. So let's see this video. These are super hydrophobic vertically aligned carbon nanotubes. You can see it stretches the interface of water. Just out of curiosity, I made this, I uploaded this. Has got nothing to do with today's talk, but just wanted to show you. I want to bring your attention to something here. This is me back probably 10, 12 years back. I was working on different carbon-based materials. My postdoc was also on carbon-based materials, so I actually wanted to work quite a bit on carbon-based materials. Then I applied to IIT Hyderabad here, and then there's already a carbon lab, right? So if I just say that I will be working on mostly on carbon-based materials, probably my department might not even consider, right? That's why I had to come up with another name, right? No, only the top side. Top side, yeah. It's a silicon substrate. Yeah. So that's how we started with the porous materials group. We work quite a bit on different kinds of porous materials. So we try to bring in, so I have a very interdisciplinary background. My BTech was in mechanical, master's in material science. My PhD was in inorganic chemistry, and my postdoc was in chemical engineering. So quite a different, so we try to bring in these different aspects here. We work on quite a bit of, quite a number of different materials like MOPs, different kinds of MOPs, etc. We also work quite a bit on chemical vapor deposition of different two-dimensional materials. We will talk about that in this talk. We look at different kinds of applications, mainly gas separation applications. Also deal with the fundamental studies of nucleation and crystallization process. From the application perspective, we work mostly on membrane-based separation as well as adsorption-based separations. Two of my students will be presenting poster here. One of them, as I mentioned, we are working on adsorption-based studies. Anybody who has done a BET knows that the minimum amount of material that you require for doing a BET is somewhere around, let's say, 30 to 50 milligram at least, right? Or we would say 100 milligram, right? But if you're producing two-dimensional materials like graphene, and if you're doing it on a CVD-based process, right, it's difficult to get 30 milligram. You probably will have to spend maybe months, right, to produce 30 milligram of your sample. So here we are developing a quartz crystal microbalance-based technique to study the gas adsorption on thin films. The advantage is this one has got a sensitivity close to around nanogram scale. So our objective is to study the gas adsorption characteristics of thin films here. The second poster, the other student, Ashish, who will be presenting here, this is about flash graphene synthesis. This technique was actually developed in Rice University, but it has got a great scale-up potential in the sense, one faculty from the civil engineering forwarded a paper to us asking that, can you produce graphene, can you give us graphene in gram scale? For them, if you add 0.05 weight percentage of graphene in concrete, they are seeing a significant increase in the compressive strength, almost 25 weight percentage increase. We figured that CVD is obviously not the way to go forward because forget about gram, even milligram is a pain with CVD process. So we started with the flash graphene based setup. Basically you have a different capacitor bank which charges quite a bit and you flash for it to a couple of seconds, the temperature increases significantly, reaches around 2000 to 3000 degree. Carbon basically vaporizes, reorganizes. You are using a copper catalyst, so you are not producing copper. Copper actually kills carbon nanotubes. So you're not producing probably other carbon materials, which probably we'll have to check in. And carbon reorganizes and produces in the form of graphene. So we tried with different materials. He's an MTech student. We just started trying this. He built the setup. We started trying. This is the bituminous coal. You can see the Raman spectrum. No particular features. D and G band. No discernible 2D band. But after the flash, you can see that there is actually quite a prominent 2D band. These are the first results. So it's a long way to go, but I believe it's quite promising. Right, coming back to the talk, I have to build a story, so I will focus on the membrane-based gas separation here. Why membranes? Because if you look at the global energy expenditure, you can see that almost 10 to 15% of the energy that goes into separation, that goes or that is spent globally, just goes into the separation process. We might not even realize that, right? Why is this the case? Because most of the separation technologies, I think now probably people might start realizing it because of the petrochemical crisis that we have, and then start realizing how much this has gone into our lives, right? So if you look at the different separation process, most of the separation process that is there in the industry right now were initially developed probably 50, 80 years back. So at that time, emissions were not a point of concern, right? And emissions were not a point of concern. So recently, there's a lot of talk about emissions and energy efficiency, etc. So if you look at this spectrum, you can see that the distillation-based techniques occupies the high energy end of the spectrum, and you have other techniques like adsorption and membrane-based process, which occupies the low energy spectrum region. So our group tries to develop different kinds of membranes for different kinds of application. I'll give you a couple of different examples. If you look at the global primary petrochemical production, this is dominated by two major chemicals. You have ethylene and you have propylene, right? And then if you look at propylene, for example, if you look at propylene production, it consumes around 10 gigajoule per ton for producing 1 ton of propylene. And you can see that 80% of this energy, 80% of this energy goes for just for separation of propane from propylene. Because it is a very tough separation, all the physiochemical characteristics are very close by. It employs almost 200 trays. So you can see here, this is a Dow chemical plant in Freeport, Texas. You can see this is the only reactor part, and you can see these large columns. These large columns are actually for separating propane propylene. In fact, around 200 trays are used for separation of propane propylene. Another major application is the carbon capture application, right? India has also made a commitment to reach net zero by 2070. Currently, India emits around 3.2 gigatons of carbon, right? It is bound to increase. Definitely, it's bound to increase. So if you have to put in perspective, each one of you sitting here will be responsible for capturing around 2,000 tons of 2,000 kilograms of carbon dioxide per year. That's a scale that we are looking at. Now, this is again not an easy separation. There are different techniques for this: adsorption, absorption, and membrane-based process. These are the different techniques which are typically used for carbon capture applications. One good advantage with the membrane-based separation is that because of its modularity and because of its small size, if you have a good high-performance membranes, then you can easily retrofit it to the existing industries. This is one of the major advantage. But if you look at the membrane market is currently dominated by polymeric membranes. And polymeric membranes are not used for any carbon capture application. This is because the polymers typically swell. And once they swell, your membrane performance decrease. And moreover, if you look at the membrane, you look at this membrane, typically you have in the y-axis, you have the selectivity, and in the x-axis, you have the permeance. And polymeric membranes typically have a trade-off between your selectivity and permeance. One way to overcome this is to start looking at inherently porous materials, or simultaneously reduce the thickness to a few nanometers. So if you look in this direction, the ultimate membrane you can think of are graphene-based membranes, two-dimensional materials, right? Because it is just one atom thick, nothing beats that, right? It's just one atom thick material. It's quite stable, thermally and chemically stable. Unique for an inorganic material, it's flexible too, right? And that's the reason why in the last 10-15 years, there has been quite a bit of interest in developing graphene-based membranes for gas separation applications around the globe. Now, where I did the postdoc, we were also working on this, developing these graphene membranes for different applications, also for carbon capture applications. We developed this large area graphene membranes and demonstrated carbon capture application. But if you look at the graphene-based membranes, one of the major bottleneck is that these membranes are inherently non-porous, which means if you have a pristine graphene, it is impermeable even to a helium molecule. Forget about carbon dioxide, it is impermeable even to a helium molecule, which means you will have to drill pores in these materials. When I said drill, I use that word deliberately because in the initial studies, people actually drill pores using electron beams, right? And then they moved and developed other techniques like plasma, ozone, etc. But if you look from a basic energetic point of view, any process which involves the pore generation in graphene typically leads to a pore size distribution. And if you have a pore size distribution, that kind of kills your selectivity. Because if you have a pore size distribution, for example, if you have CO2 and nitrogen, CO2 is the smaller molecule, nitrogen is the larger molecule. Now, once you have a pore size distribution, nitrogen also starts passing through the larger pores, which you don't want. But any process you use for pore generation typically leads to a pore size distribution. This is because pore expansion typically consumes less energy than pore nucleation. So as a result, it is very challenging, and this is one of the major bottlenecks currently in this field, to develop a pore generation strategy which has got a very narrow pore size distribution. So I came back here. I also wanted to start working on this, but I very well knew that I won't be able to beat the postdoctoral groups as well as the groups working in MIT and other one. So we wanted to try a different approach. So we asked ourselves, what are the different materials which can be used, which are two-dimensional, but at the same time inherently porous. So now, once you have inherent porosity, this can be used for gas separation application, though you won't have this bottleneck of pore generation. So we figured two different kinds of materials. We are working on this. Here I have to claim that our group is very young, probably 3-4 years, very long way to go. This is just the first part of the story. So we zeroed in on two different kinds of materials, carbon nitrates and graphidines. How many of you have heard of graphidines here? Just raise your hands. Okay, I'm glad that at least I could see few hands here, right? Carbon nitrate, probably almost all of you are familiar with, at least you might have heard, but what you might not have heard is this is a very controversial material. Most of what is known as carbon nitrate, there are certain groups, Bettina Lotsch group from Germany and other groups, they claim that it is actually not carbon nitrate. It might not be even carbon nitrate, this might be a cousin of polymeric melon, because these are typically joined together by NH or NH2 groups. Anyway, we are working on this, but in today's talk, I'll be focusing on this part, the graphidine. What is unique about these two materials is that these are inherently porous materials. You can see that there are pores here through which the gas can pass, and there are pores here too, where the gas can actually pass through, which can be used for separation applications. Let's look at graphidine. Graphidine belongs to the larger family of material which are known as graphines. It's a little known cousin of graphene. If you look at graphidine, the starting material is something called hexaethynyl benzene. You kind of develop a technique for polymerizing it, and you end up with a structure like this. These materials are two-dimensional films, and if you look at the pore size, this is around 3.4 angstrom. The advantage is that you have a very high pore density. The pore density is around 10 raised to 14 per centimeter square. The state of the art for the graphene-based material has reached only 10 raised to 13. So when you have 10 raised to 14, you expect it to have very good gas flux and good selectivity. Now, why is this 3.6 angstrom interesting? This 3.6 angstrom is interesting because it sits right in between different light gas molecules, and it can be used for many separation applications. So it can be used for separating carbon dioxide from methane, or nitrogen from methane, or hydrogen from methane, different applications. So one of my PhD students, he started working on this. We looked at many different techniques for synthesizing these graphene. We looked at chemistry-based techniques, interfacial polymerization, CVD-based techniques, combination of interfacial technique as well as the catalyst-based approaches. So finally, we were able to get very thin layer of graphidine using a copper-based catalyst. Now, we are at a stage where we can synthesize very large areas of graphidine. And along the process, what we have seen is that if you are using graphene as a substrate, the growth dynamic changes entirely. Why this is interesting is if you look at the graphidine structure, let me see whether I can pull. Yeah, if you look at this graphidine structure, this particular bond is notorious because it can just rotate. And if it just rotates, instead of getting a 2D film, you start getting a 3-dimensional structure. And 3-dimensional structure is not good for membrane application. So you have to limit your growth along the 2-dimensional films. This was our motivation behind using graphene as a substrate, because then you can exploit the pi-pi interactions between graphene and your material, and then you can use it for producing very thin films of graphidine. And when you see that if you're not using, if you're directly growing it on copper, you get a thickness of around 250 nanometer, and the Raman is just okay. But if you are using graphene as a substrate, then your thickness drastically reduces. You get a highly crystalline film. You can see the crystallinity here. The crystalline fringes are also here. And more importantly, you get this characteristic peak in Raman. And this Y peak is the fingerprint for graphidine. this is observed only when you have high quality graphene. Now, we have successfully synthesized graphene. Now, at this stage, we know how to synthesize graphene in a thin manner, in a proper crystalline structure. But anybody who has worked on two-dimensional materials is familiar with this transfer technique. This is the classical PMMA-based transfer technique. No fancy science here. You caught a polymeric material, transfer it to another substrate, wash away the polymeric material. It works beautifully. The problem is, once you have a porous structure, this does not work. The problem is, once you have a porous structure and you do the acetone-based washing or washing for removal of your other impurities, the evaporating water just ruptures your film. Because these films, keep in mind, these are few nanometers in thick, right? So these just ruptures the film. So we have to come up with a way to prevent this process. There are different techniques. What we are using is, there's a process called NIPS process, non-solvent induced phase separation process. We use this process as a substrate or a supporting material onto which we transfer graphene and then etch away the copper. We were successful quite a bit in obtaining graphene, but here and there we observe these large cracks. These are some of the challenges that we are facing currently. We observe from place to place, we observe quite a bit of cracks. Remember this slide, I showed you this particular slide before. I also mentioned that the pores are around 3.6 angstrom, right? But what I did not mention to you was the pores are 3.6 angstrom only when you have an AAA stacking. But typically, you don't get an AAA stacking. What you get is a staggered stacking, AB or ABC kind of stacking, which means you're blocking the pores. This is a major challenge. We'll have to figure out different ways for overcoming this challenge. One way, what we have found, is a recent paper which is published in 2025, and they use copper 111 based catalyst. Anybody who is working on graphene is also familiar with the characteristic feature of copper 111. They used a copper 111 phase for controlling the stacking sequence. So this is something that we are currently trying out. The other option is, instead of using HEB, where 6 of these are interlinked, you start using something like the TEB. The advantage would be the pores that you get in what is known as HSGDY are significantly larger. And in this case, when you have the stacking now, even if you have a staggered stacking, your pore gets smaller. And that smaller pores can be very well used for gas separation applications even. So we are also pursuing in this direction. And we have successfully synthesized large area, at least for the lab scale, large area films. And we have also obtained good permeance. A permeance of around something greater than 1000 GPU is considered to be very good in terms of gas separation membranes. And the hydrogen methane selectivity that we have obtained now is close to 11, with something called Knudsen selectivity. For example, even if you have a 1 nanometer pore, right, all the gas molecules will be passing through there, and you will be getting selectivity of around 2.8. Now, our values are significantly higher than 2.8, which means that we are at a stage where we are observing some molecular based cutoff. But it's still a long way to go. We would ideally like to further improve the flux and selectivity, have to optimize the crack transfer and the sealing process, and then would also like to look at the controlling the stacking sequence. Thank you.
Thank you. Yeah. So the floor is open for questions. Due to lack of time, we'll be able to take only 2 questions. So, Tata sir.
Very rapid fire, 2 questions only. Yes. One is, how do you, when you want to take this, you've grown the membrane on copper 111 or so.
Yes.
But how do you take it, lift off, and then use for the membrane? Because copper is not porous.
Yes, but you can easily etch away the copper. This is a standard process in graphene transfer.
So you can take some freestanding one, or you have to lift it to some big porous one.
You have graphene and then you have a film. You float the entire thing in, let's say, solutions like ammonium persulfate. Yeah. So that will etch away the copper. Then you can scoop it using a porous substrate.
Okay. But because you said you tried the gas separation also.
Yes.
So that you must have some kind of
fixer where the gas has to enter from one
Yes,
side. Huh?
yes, yes. So
Okay.
we have built a membrane module and all.
Wonderful, wonderful. And the other one is you said by flash method.
Yes.
You were what were you making in the first slide? First that. Yeah, this one.
Yeah.
So you're making graphene, right?
Graphene, yeah.
But can you use any laser, pulsed laser or something instead of flash to increase the production rate or something? No?
Could be tried.
Yeah, because this may be a little bit big.
Yeah,
size.
this is quite big. I think the temperatures around we need, as you know, I think we need around 2000 to 3000.
Yeah, so
probably one could use
we don't
laser
know other
too.
lasers,
Yeah.
but there may be it may possible. Okay,
Yeah.
Right. Thank you.
Yeah. The whole field started again with the laser too, right?
It's a very wonderful presentation.
Hi, sir. That's a very nice presentation. Material that you're working on. What are the benefits of using graphite compared to covalent organic frameworks in
a
membranous?
strict way, if you look at this graphite, though nobody has called it as a cough, this is actually a cough, if you think in a straight way, right? This is because you look at all the bonds, it's just carbon. That's the only defining feature here. That makes it the allotrope of carbon. But I would say this is again a kind of cough. But then again, one of the advantages is you take any typical cough, I mean, any generic cough that you know of. Typically, the pores are in the larger nanometer range, right? Nanometer or beyond, which is not suitable for gas separation applications. So here you have this material where your pores are in the sub-nanometer range, which is very interesting for gas separation applications. So that's what we are looking at.
Yeah. Thank you.
Yeah. 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 Long way to go. Yeah. Yeah.
So let's have a round of applause for sir. Thank you, sir, for the talk. As we move forward to the session, our next speaker is Dr. Ramya Araga. Dr. Mani Pujita Illa, sorry. So, fine. So, Dr. Ramya has been an alumnus of our lab, and she is currently faculty at NIT Warangal. Her work focuses on carbon and polymer-based nanomaterials for energy and environmental applications, including photocatalysis and wastewater treatment, with a lot of research in the sustainable materials research. I invite Dr. Ramya to deliver her talk to the audience.
Okay, thank you. Very good afternoon, everyone. Before proceeding with the presentation, I would like to introduce myself, though formally the introduction has been given. Myself, Dr. Ramya Araga. I am an alumna of a Carbon Laboratory. I did my PhD during 2013 to 2018. And currently I am working as a faculty in the Department of Chemical Engineering, NIT Warangal. So, as a part of the C15 summit, I would like to present a segment of our research, which is entitled Synergistic Effects of a Carbon Nanotube Heterojunctions in Advanced Photocatalyst System. So, before we talk about the advanced photocatalytic systems, let me briefly introduce, though you know what is a photocatalysis, let me briefly introduce what is a photocatalysis. The photocatalysis, which is a type of advanced oxidation process, and it
it acts as a sustainable AOP process which utilizes the photocatalyst, and upon excitation, either by using UV light or a visible light, it generates highly reactive oxygen radicals, especially the hydroxyl radicals. These will help us to degrade the organic pollutants which are present, either in the environmental, aqueous stream or in the solid phase. So among the various photocatalytic materials, the TiO2, which is known as widely studied by the researchers because it is a low cost and its non-toxicity. However, TiO2 is having major disadvantages such as a low utilization of visible light. It can be excited only under the UV light, so that is the major disadvantages due to its wider band gap, which is approximately 3.2 electron volts. And the other disadvantage is it's a rapid recombination rate of a photo-generated electron hole pairs. So they quickly recombine with each other. That is another major disadvantage. Now, these can be overcome by modifying the photocatalyst through doping. The doping can be done either by using metals or non-metals. And in order to avoid the rapid recombination rate, we can follow the coupling of photocatalyst with other materials to form heterojunctions. Now, if we are able to modify the photocatalyst through these two approaches, these are referred as advanced photocatalytic systems, which works effectively under visible light and will efficiently work towards the degradation of organic pollutants by overcoming the rapid recombination rate of the photo-generated electron hole pairs. Now, as I mentioned, coupling these photocatalysts with other materials to form heterojunctions. So what are the heterojunctions? Now, heterojunctions are nothing but it is an interface between two semiconductor materials which are having different band structures. Now, if you look at, I hope I am audible. If you look at the various heterojunction structures, those are being classified. These are classified commonly into three types: the conventional heterojunctions, PN heterojunctions, and the Z-scheme heterojunctions. If you look at the conventional heterojunctions, based on their band structures, they are again being classified into three categories: type 1, type 2, and type 3. If you look at the type 1 heterojunction, the valence band and the conduction band of a semiconductor A is larger than the conduction band and the valence band of a semiconductor B. That means semiconductor B band structures are completely contained within the band structure of semiconductor A. So this will facilitate the movement of photo-generated electrons from semiconductor A to the semiconductor B, and photo-generated holes from semiconductor A valence band to semiconductor B valence band, and it will facilitate the further degradation of the pollutants. So sorry. And if you look at the type 2 heterojunction, the band structures of a semiconductor A, which is a bit higher than the band structures of a semiconductor B, and in this case, the migration of photo-generated electrons and carriers will proceed in the other way around when compared with the type 1 heterojunction. And the type 3 heterojunction, the band structures and the band alignments does not align at all. So this is the reason the separation of photo-generated charge carriers cannot be maintained as separately throughout the process. So that is the reason type 3 heterojunction is not being used commonly across the degradation processes. Now if you look at the PN heterojunction mechanism, so upon the excitation, the P-type and N-type heterojunctions, if you look at the Fermi level of a P-type is very much near to the valence band of, it is very near to the valence band, whereas the Fermi level of N-type semiconductor is very much near to the conduction band. Now, upon the excitation, the electrons which are present in the N-type will migrate towards the P-type and leaves the holes behind. In the similar case, the electrons which are generated through the exciton, they will migrate towards the N-type semiconductor and leaves the holes behind it. So this is an effective architecture to proceed with the degradation process, because which creates the internal electric field which keeps on separating the electrons and holes continuously throughout the process. And in terms of Z-scheme heterojunctions, there are two types which are in physical contact with each other, whereas the other kind is there is no physical contact between the semiconductors or the photocatalysts. Now, the semiconductors or the photocatalysts which are not in physical contact with each other will be coupled with the help of either donor or acceptor pairs or through the other means. In case of a direct Z-scheme heterojunctions, they are in physical contact, and as they comes into contact with each other, while maintaining the closer contact, the electrons which are excited in the photocatalyst 1, which will be recombined with the holes which are present in photocatalyst 2 valence band, whereas the electrons which are excited in the photocatalyst 2 will be maintained separately, and they will not come back to the holes because these are already occupied by the electrons, and these holes and the electrons cannot be coupled or cannot be recombined, they will be maintained separately. So this configuration is considered to be more effective to perform the degradation process. So considering this, we try to form the Z-scheme heterojunction by using a single wall carbon nanotube on the TiO2 photocatalyst. Now, so the recombination rate can be reduced. However, the actual band gap need to be come down as well. So in order to do that, we have incorporated the Ag plus ions into the TiO2 lattice. So the band gap of pristine TiO2 has come down to 2.8 electron volts. The photocatalyst was active under visible light, and the recombination rate was reduced because of the heterojunction that is formed with the single walled carbon nanotube. And by measuring the conduction band and valence band of each TiO2 as well as the heterojunction material, that is a carbon nanotube, we have identified the positions of all the valence band and the conduction band of each material, and we have identified that this heterojunction is very much similar to Z-scheme heterojunction. Now, we have implemented this material towards the photo degradation of, towards the photo degradation of microplastics, and we focused on polystyrene microplastics, which were which we have synthesized at the laboratory scale, because we didn't work with the real-time microplastics which are polydiverse in nature and will absorb lot of surrounding chemicals, which makes the analysis more complex. So within the batch degradation experiments, we have identified that the prepared photocatalyst was performing effectively. This has been compared with the pristine TiO2, that is the bare TiO2, which was not at all modified, which was activated or excited only under the UV light. So we have achieved only 7-8% mass loss with respect to the polystyrene microplastics which were dispersed in the aqueous phase. And upon coupling it with Ag plus into the TiO2 lattice, we have achieved 38% mass loss, and followed by TiO2, which was only heterojunctioned with the CNT but not doped with the Ag plus ion. We achieved again 34.38% mass loss. In case of ATC, that is corresponding to the Ag plus doped TiO2 coupled with heterojunction, we have achieved 57.84% mass loss, and this is only towards the batch degradation studies. And later on, we have optimized all the operating parameters such as the effect of time, temperature, photocatalyst doses, and the percentage concentration of the photocatalyst that is present, and the doses of the photocatalyst. And with these optimized parameters, we have proceeded with the closed loop continuous degradation process, and we have noticed the improved kinetics in the degradation process, and the measured carbonyl index, which is corresponding to the breakage of the polystyrene chain scissors, this value confirms the degradation is happening within the polystyrene microplastic, which is contributing to the value of 0.42. And this has been cross-verified by using HNMR analysis and by measuring the total organic carbon that is present in the pristine samples as well as the photo-degraded samples. In case of a bare TiO2, the total organic carbon initially present was 78.78%, ppm, that is mg per liter. It came down to 72.43 mg per liter after 120 hours exposure. Whereas in case of Ag doped TiO2 heterojunctioned with the CNT, we have reduced the organic carbon from 78.78 ppm to 55.27, which is indicating that the effective degradation process is proceeding with the modified photocatalyst. And as the degradation proceeds, we have identified what are the intermediates present, because the intermediate which are being produced should not be more toxic than the pristine polystyrene material. So based on the GCMS analysis, we have identified that the intermediates are less toxic when compared with the polystyrene microplastics. And so these are the conclusions. The modified photocatalyst, which was doped with Ag plus into its lattice and heterojunctioned with the CNT, has contributed well, performed well, and reduced the concentration of the polystyrene microplastic up to a certain extent. However, it is not 100% degradation. This is the starting. There is a lot of work to be done. I mean, there is more way to go. And so the visible light excitation has been achieved by replacing it with the UV light excitation. And the prepared Z-scheme photocatalyst, this photocatalyst has performed effectively because of the separation of the photo-generated charge carriers, electrons and holes. So this is a part of the work that we have been carried out. And so because of the time constraint, I could not present all the technical details of this work. However, these are the various publications that we have come up with. If you are interested, you can dig into the details. And this is my group, and she is Ms. Bhagyalakshmi, who has currently worked on this research problem and very recently gave her open synopsis and about to wind up with the thesis. If you have any questions, I'd be happy to answer.
So thank you. I suggest everyone to utilize the tea session after a tea break after this session to ask as many questions to our alumnus. We'll move forward with the next session. The next speaker, Dr. Mani Pujita Illa. She is also an alumnus of our carbon laboratory and currently a faculty at the NIT Trichy in the Department of Material Science. She'll be presenting her work on the different energy storage systems. Let's welcome her to the dais.
Hello. Good afternoon, everyone. This is Pujita. I am Carbon Lab alumni and as well as Cellulose Lab alumni. I work with Professor Chandra and Professor Mudrika at IIT Hyderabad from 2015 to 2020. Currently, I am at NIT Tiruchirappalli in the Department of Metallurgical and Materials Engineering. Today I will be telling a story about how discarded waste can be converted into a next functional cathode materials. So this story begins in 1789 when graphite was first discovered or first named for its ability to write. So it was basically used to mark the sheeps which are grown. But then people realized that it is much more than that. Its heat resistant properties as well as the lubrication properties made people to use it in cannon applications like missiles and other things. But now people later on what happened is they found it for its use in many applications, including the current electric vehicles. But the problem is graphite is kind of become a strategic material over the period of time, and it is strictly controlled. Now, fast forward today, what we are doing is, we all know electric vehicles are booming, and then we use electric vehicles now mostly. But let's see in future. There is an estimation that about 3.7 to 4 million tons of batteries will come for recycling at the end of 2030. So now how we tackle this problem? So this generates a huge amount of waste, battery waste, which is becomes an environmental disaster, because we know that it consists of lot of elements in it. We can see it as that way, or we can see it as an untapped resource which we can tap into. Now, if we see a particular battery, let's say end of life cycle battery, people say that, and if let's say we categorize it to it, if say the end of life cycle battery consists of 70 to 80% of its capacity, it becomes end of life for that particular battery. And then there are two ways of using it. One, you keep it for large scale storage purposes like stationary storage, you repurpose it. Otherwise, if you can also recycle it. If you do use for stationary purpose, what happens again, it will come after some time, it will come for recycling. So now what we do is, even if further recycling is required, it will only create huge problem. So we need to understand how it is going through. Now if you see at what scale. So now if you see inside a battery, the graphite consists of almost 20 weight percentage. When compared to lithium and cobalt are very less in the battery. So that 28% can we tap into. And also graphite is sourced from a single region and controlled from a single region globally. So now it is not just environmentally important, but also we can also build a supply chains which are independent and locally resourced. Let's say we recovered graphite, we got 28% from the battery. So what do we do with that? There are three particular ways. One is at a lower level, it can go into different industrial usage, because we have a lot of use for the graphite. The next stage is at a higher level, you can go back, put into same EV battery after restoration. And then the next exciting path is upscaling. Upscaling is basically you take a material and make much advanced materials from it. So this is where our work lies, upcycling. For this upcycling, we are saying that we will use the graphite which is there in the battery. But the graphite, the fresh graphite and the used graphite are not same. Over the time, the used graphite will consist of electrolyte impurities, SEI layer impurities, lithium compounds and other things. Also, during the repeated recycling, it kind of distortion will happen for the cycling process. You know, the expansion will happen. So before reusing it, we need to recover it and restore its structure. So here we made an attempt to restore the spent graphite from the lithium ion batteries. So you take lithium ion batteries, discharge it using NaCl solution, or you can also use electrical discharge method. You discharge it, separate the layers, and then you separate the layers of cathode, anode and separator, and take the anode part and then sonicate it, and then you will get the graphite from the sonicated part. And then there are different kinds of treatments that are available which are conductor for battery graphite. So here we made an attempt to understand how different kinds of treatments will affect the spent graphite. So here majorly we choose three types of treatments. One is thermal process. Thermal process basically restores the graphitic structure, but it itself is not sufficient. It only restores the structure, but chemical impurities such as lithium is still there in the thermal processing. Further, we have expanded. We have did two types of treatments. One is acid treatment and then alkali treatment. So acid treatment, you all know, we used H2SO4 along with pyrolysis treatment to fully restore the structure. And in case of alkali treatment, we treated it with KOH and then restored. So whatever the treatment is, we get different kinds of or different states of graphite. We can see from the XRD, SEM, and then you do TEM analysis. So the structure which we get depends upon the treatment what we give for the battery. So this is one work we are currently doing, and we are currently doing the cost estimation or energy estimations for this particular work. Next, as I said earlier, we are upscaling the material or the recovered graphite. Our group majorly works on aqueous based batteries, so particularly zinc ion and aqueous aluminum ion batteries. One attempt we made here is to use the recovered graphite as integrated with MnO2 cathode for the zinc ion batteries. Aqueous batteries are comparatively safe and low cost when compared to the current lithium ion batteries for the large scale purposes. So what we did here is, we can see we made composites with graphite, different weight percentages, and then we optimized the recovered graphite composition in the MnO2. MnO2 basically has a high theoretical capacity for the zinc ion, but the problem with MnO2 is there are three problems. One is MnO2 is low in conductivity. The second part is it is structural integrity is poor, as well as there is a problem with dissolution in the aqueous electrolytes. So by integrating recovered graphite into the cathode material, we have tackled this problem, which we can see from the impedance curves that are presented here. There is a improved impedance, and then we can also see the cyclic stability has improved and rate performance has been improved. We up to 2000 cycles the performance is about stable at a high at high current density around 0.5 ampere per gram. And also we have done GITT studies for understanding the diffusion of zinc ion in the cathode material. So that is one thing. And also we try to understand the mechanism how the zinc ion or the zinc intercalation is happening in the material. That is also done. We have observed that there is a formation, there is both intercalation of H plus and zinc ion in the cathode composite, which gives a superior stability when compared to the MnO2 alone. So that is one work. And the next work, we work with aqueous aluminum batteries, which we further integrated. Aqueous aluminum batteries itself comes with a lot of other problems. Aluminum ion, you know, it's a large size, high charge density. When aluminum ion is intercalating and de-intercalating, the problem is because of high charge density, electrostatic interactions with the host lattice is more, as well as you find it out for sluggish kinetics will be there. So for tackling this, you need a material which is more open or a porous structure which is having a high large interstitial size where aluminum can diffuse easily. So here we are investigating a material called as Persian blue analogs, which consists of a 3D network kind of structure with large interstitial spaces, which can be used for intercalating the hydrated aluminum ion. So we have done the studies. After incorporating, the PBS are also again less conductive and not stable. So by incorporating recovered graphite into PBS or a composite, enhance the performance. And the noteworthy thing is here is that at a high cycling rate around 5 ampere per gram, it still works. This is still ongoing, very recent work we are doing. So that is all. So what we are doing is basically taking a degraded anode material from the current batteries or used batteries and making it into a functional cathode materials for the aqueous batteries. So that is all. So this is my group, and I work on other things as well, like I work on solid state electrolyte materials for sodium ion batteries, and also bacterial cellulose, which I worked with during my PhD time, that also I work with. So that's all for today's presentation. Thank you.
So thank you, Dr. Pujita, and the wonderful audience. So due to again lack of time, we move forward to the end of the session. We'll have the presentation of the mementos and the coffee table book to our speakers. We kindly request all our speakers to join on the dais. Please. Dr. Ramya? Yeah. Deepur. Dr. Deepur, sir. So we have a tea break, and you can also visit the posters presented by our participants to the conference outside the auditorium.
I request all the poster presenters to be there on the posters. Judges will come. There are best poster awards as well. So please be there near your posters. There are at least 3 judges who will be visiting you in this break. Thank you.
Good evening, everyone. I hope you all had an insightful section on carbon materials earlier. Now we can move to the second section on emerging trends in energy storage technologies. I am Soni, postdoctoral fellow in Carbon Lab and a recent PhD pass out from this lab. And it's my pleasure to serve as the section chair for this section. We have an excellent lineup of speakers today, and I am delighted to welcome each of them. The section will consist of individual talks followed by a 5-minute Q&A section, and I encourage the audience to actively participate in the discussions. First, we will begin the section with our first speaker, Dr. B.V. Sharada, Scientist G from ARCA Hyderabad. She is a leading scientist with extensive expertise in functional materials and surface engineering for energy applications. We look forward to her valuable insights and contributions. Ma'am, you may please.
Very good evening to all. Thank you, Dr. Soni. It's very nice feeling to speak under the chairing of my own student. Today's title of my presentation is Advances in Lithium Sulfur Battery Technologies. First of all, I would like to thank Professor Sharma and his team. And also I would like to congratulate them for the Crystal Year celebrations. And I love this. This is the innovation always Professor Sharma keeps. Even for the Crystal, he has a sentence which really shows what they are doing. So coming back to a small introduction for myself, I am from Center for Advanced Materials and Batteries at International Advanced Research Center for Powder Metallurgy and New Materials. So I mainly work on all batteries, most importantly on lithium sulfur batteries and also metal oxide based pseudocapacitors. And as all of you know, ARCI is Autonomous Research Institute under the Department of Science and Technology, and the main mandate of ARCI is translational research, translating the fundamental research, upscaling it and transferring to industry. And there has been a lot of discussion by our former director, Dr. Tata Narsingh Rao, and Dr. Anandan, my colleague who is working on lithium sulfur batteries. So, as already mentioned, ARCI always works on upscaling and transferring the technologies to industry, and these are the 4 technologies in which I was involved, so I am just showing such several technologies have been transferred, and also we do the contract research whenever a startup comes to us and asks us to solve their issues. We work on that R&D and then give the solutions for them. So now, coming to the topic of today's presentation, you can see from this plot that greenhouse gas pollution is in billions of tons of CO2 equivalent per year. You can see over here 1990 GHG is above 1 billion tons of CO2 equivalent, and there is always effort to reduce it. And from EV point of view, if you see, from battery EV scenario and fuel cells, these are the only 2 technologies that can rapidly bring down by year 2090. You can see slowly it is falling with the newer technologies of battery materials as well as the cells. So we have to reach, and to reach this, there has to be continuous evolution of the research both on materials and cells. And coming to the energy storage, because this session is on energy storage, I want to show that the energy storage project capacity is for globally, if you see, pumped hydro is the maximum, but then it is followed by the electrochemical energy storage devices, and in that lithium-ion batteries are dominating the electrochemical energy storage. And if you see in India, there is a continuous growth in the requirement and the market of lithium ion or sodium ion and lithium sulfur batteries. So for that, we need to not only limit to R&D at lab level, we also have to look for commercialization of our research. So you all know this. As I said, there are different ways of energy production, like solar energy. then wind energy and also hydropower, and the energy that is coming from these renewable sources also has to be stored, not only the grid power. So, and the applications of storage, energy storage, you can see over there. The saturated market is for the power electronics and home appliances and the cell phones, etc. Whereas the growing market is for storing of renewable energy, the EVs, different electric vehicles, you can see the whole range over there, and also for aerospace. And for the aerospace, most important battery material is, battery chemistry is lithium sulfur. However, coming to the EVs, you can see for the lithium-ion batteries, these are all the anodes and cathodes. And post-lithium-ion batteries, which is concentrated mostly recently, is on sodium-ion batteries. I think Professor Amartya will be speaking next. And then lithium-sulfur battery is mostly for the automotive applications for the long range and also for the aerospace applications. And the research is also required for power management and control, and then also for establishing the supply chain. So now coming to the actual batteries and cells, what are all the properties that need to be taken care when you are doing research on the batteries? First is the energy density. So to establish a good energy density, you have to work with the voltage plateau, potential gaps and specific capacity, and cost analysis. Other than the scientific research, you also need to take care of the cost analysis. During the morning panel discussion, lot of discussion also happened on the cost analysis, where Dr. Anandan was mentioning on how to reduce the cost if that has to be a material or a technology has to be commercialized. And then the other one, not only the energy density or specific capacity, you also need to take care of the cycle stability, because unless also the initial cycles show very high performance, if the cycle stability is not very good, again it is not commercially viable. And the other one is safety concerns, which we have seen few years ago and they are taken care of, and now we have lesser accidents. Now these two are what are very close to commercialization, lithium-ion battery, mostly working on the cost reduction. So first NMC, then LFP. In LFP also first generation, second generation, third generation, and now people are working on the fourth generation. Whereas for the sodium-ion batteries, you can see the market is slowly and steadily increasing. So although not much of commercialization happened except in China, but it is moving very fast towards the commercialization, and several materials for both cathodes and anodes are being done. At ARCI, we are working on the hard carbon materials, layered oxides, and also NVP. NVP is more close to upscaling. We could prepare at 10 kilograms per batch, and now we are working with a company to commercialize it. The industry is ready to take this technology, and we are working with Amar Raja, who is sponsoring the project on layered oxides, and hard carbon also we are working with another industry. Soon we are going to sign an agreement. Now, since I am going to speak on lithium sulfur batteries, what are the advantages of lithium sulfur batteries over the lithium ion batteries? Although the voltage is very low, 2.1 volts compared to lithium ion battery of 3.9 volts average, the specific capacity you can see is much higher, 1675 milliamp hour per gram compared to that of 180 per LFP. And also specific energy or energy density is also 2500 watt hour per kg. This makes lithium sulfur battery very attractive over the other battery chemistries. You can see also from here, lithium sulfur is lying over here. You can see this is commercial, okay, which are very close to commercial. From the industries we have this data. They are reporting about 400 to 450 watt hour per kg energy density. That is by Zeta, which has prepared the pouch cells, and they have shown this energy density. And mostly for the commercial applications, people are working on cylindrical cells, pouch cells, and the prismatic cells. At ARCI, we are working on the pouch cells mostly now, right now. And as I already mentioned, lithium sulfur batteries are very important for the aerospace applications and long range automotive applications. And aerospace applications particularly, it is very important because it has very high energy density and specific capacity, which makes it a very small pack in comparison to lithium-ion batteries. So this is a very preferable battery chemistry for the aerospace applications, and the major players for the lithium-sulfur battery are Zeta, Oxys, Lyten, and these other companies, but which are more close to commercialization. And there are no commercial batteries available in the market. Only very recently, Zeta and Lyten have shown that we can buy their battery packs in pouch cell format. And so everything is good, very high specific capacity, and Lyten has shown that they can fly a drone by using this lithium sulfur battery chemistry. But with all these advantages, why is it not being able to get commercialized? There are issues with the lithium sulfur batteries, which the research groups have been working on it. First one is the cycle life. So you can see over here, in lithium-ion battery, it is intercalation, deintercalation process, whereas in lithium-sulfur battery, it is redox reactions that take place between the sulfur. So here, sulfur is the cathode, not the carbon, but carbon plays a very, very important role in the cathode. And the sulfur, the redox reactions between lithium-sulfur is the process for producing the specific capacity or energy density. You can see over here the charge discharge curve. In that, you can see sulfur S8 becomes Li2S8, Li2S6, Li2S4, Li2S3, Li2S2, and Li2S. So this is the final product which takes part. And again, it is converted back to sulfur. So during this whole process, what happens is, when it is converted from S8 to Li2S8 and Li2S6, these are in the liquid form. So these intermediate products which are in liquid form, they get dissolved into the electrolyte and they travel towards the anode, and there they get deposited, and that's how the cycle life is continuously falling. So in order to reduce this, and the other challenges are that you are using sulfur as cathode. So sulfur has very high volume expansion. So you have to take care of the high volume expansion. Second is, sulfur is an insulator. So you have to take care of the conductivity of sulfur also. Then the third one is the shuttle behavior. As I mentioned, is Li2S8 and Li2S6 dissolve into the electrolyte, and also Li2S, which is the final product, also is an insulator. So you have to take care of that also. And another issue in lithium sulfur batteries is higher self-discharge compared to that of lithium-ion batteries. So we have to work on each of these problems. And first one is volume change. We worked on using the porous carbon as sulfur host. So by using a very optimized amount of meso to micropores of carbon, you can control this. So the sulfur is melt diffused into this carbon host, which is porous carbon, and then you can control and increase the cycle life to an extent. And then other one is insulating nature, again by using the porous carbon host, which is the a conductive material. So this causes conductivity to the sulfur for the redox reactions. And the other one is electrolyte also. In the electrolyte, you have to use additive. Li2NO3 is used as an additive, and you can see the difference in the charge discharge curve when an additive is used. So these are all the methods that improve the lithium sulfur battery cycle life. But the most important is, although you are using porous carbon where meso and micropores are there, but still after certain hundreds of cycles you have reduction in the cycle life. So in order to address this, we have to use electrocatalysts along with the carbon host for carbon, which is a sulfur host. So we co-embed, we work, so there are 4 types of these electrocatalysts. One is metal, other is metal oxide, metal sulfide, and metal carbide. So we worked on metal and metal sulfide, and my work on metals is with Dr. Soni and Professor Sharma again, where she has worked on, so why we need to use a dual? We have used iron cobalt as the catalyst, electrocatalyst. So people have also worked with single catalyst, iron or cobalt, but by using the iron cobalt dual catalyst, you can see over here the Gibbs free energy. You can see in that plot, see it goes to, so for sulfur S8 to Li to S8, it is almost similar, but when it comes to Li to S8, the Gibbs free energy is much lower for dual catalyst compared to a single catalyst, and then slowly it increases again it is highest for Li to S, but for a co-catalyst, FeCO catalyst, it is lowest compared to the single catalyst. So we have taken help of this and we worked on iron cobalt co-embedded zero-gel based carbon, and the innovation in this work is a single pot process for preparing FeCO co-embedded zero-gel carbon as cathode host for the sulfur. So sulfur is the one that is taking care of the electrochemical reactions, and as I mentioned, the porous nature of carbon with the meso and micro is also very important. You can see that some pores are below 2 nanometers and others are above 2 nanometers, and this is very, very important. The ratio is also very important to maintain the cycle life. You can see from here the cyclic voltammetry and the charge discharge curves, rate capability steps and all. And at 4C, even at 4.2, so you hear from lithium-ion battery research and sodium-ion battery research is that the electrode loading, mass loading is very high, about 20 to 30 milligrams per centimeter square in pouch cells, etc. But in case of lithium-sulfur batteries, you cannot go beyond 7 milligrams because of the insulating nature of sulfur, although you use carbon as sulfur host. So you can go maximum up to 9 milligrams, which is reported. You cannot go beyond that. So you have to manage with this 7 to 9 milligrams per centimeter square, and we have gone up to 4.2 milligrams, and you can see at 4C it has given a very good specific capacity of about 500 and odd per centimeter square at 4C also. That's a very good result, and we have patented it. And then, as I said, at ARCI, whatever we do, if we are successful with the fundamental research, we go again upscaling this, and the 50 grams batch is done at IIT Hyderabad itself, and once that is proven, you can see over here, even at the 50 gram scale, we got a very good results even at 2C, and then we have further upscaled it to 1 kg at ARCI. You can see the whole process, and there is no decrement in the specific capacity at 2C, 0.2C. You can see about 800 milliamp hour per gram. So this has encouraged us to further process and prepare at 5 kilograms per batch, which is under progress now. And we have made a single layer pouch cell. And again, while making a coin cell, it's actually easy, because you know you have lot of literature, but when you are upscaling a process to make the pouch cells, we realized that the lithium-ion battery facility that is being used cannot be used for the lithium-sulfur battery because the anode is lithium. In case of lithium-ion batteries, graphite is the cathode. So the coating and the calendaring and the pouch cell making can be done even at 10% humidity dry room. Whereas in case of lithium-sulfur batteries, you need to do the pouch cell stacking at below 0.5 humidity. So now we are establishing at ARCI. However, we have made this at in a glow box, and we could get a working pouch cell. So we are going to make multi-layer pouch cells using the same iron cobalt modified porous carbon sulfur composite for the lithium sulfur batteries. And Amar Raja is interested in taking the technology if we are successful with the further upscaling and getting the required cycle stability of 1000 cycles. And the next electrocatalyst, as I mentioned, MnO, like we have tried even with oxides, but oxides we found that are not so stable as metals or metal sulfides. But molybdenum sulfide is very well known as an electrocatalyst because of several properties. Even it is used even for hydrogen research. Many of you who are working on the hydrogen research, you know, because of its electrocatalysis for the oxygen and hydrogen evolution. You can see over here the MOS2 with sulfur vacancies acts as a very good electrocatalyst. And again, as I mentioned in case of metal electrocatalyst, here also you can see over here from Si to Li to S8 when it comes, the Gibbs free energy is coming down to negative minus 3.75 electron volts compared to that of carbon. So this is what is making the difference for the actual quicker, that is, it is catalyzing the reaction from Li to S8 to Li to S very quickly by electrocatalyzing, and you can see over here, and one more you can see is the energy barrier for converting from initial stage to the final stage. The transition stage, TS, you can see over there, is much lesser when MOS2 is used along with the carbon. You can see from the bottom right plot, the an energy barrier is only below 1 electron volts, whereas when only carbon is used, it is about 2 electron volts. This is what is playing a major role in case of molysulfide electrocatalyst with carbon with molysulfide electrocatalyst. And again in molysulfide, you have two types of MOS2. One is 2T and the other one is 1T and the other one is 2H. 1T is electronically more conducting, and the other advantage is that even during the basal planes, in the basal planes the catalysis happens, whereas in case of 2H, first is it is semiconducting, and also at the edge planes the electrocatalysis, it is active for electrocatalysis. So we are trying to optimize the content of 1T plus 2H phase, because complete time is over. So complete 1T phase or 2H phase is not good. So a particular optimization of 1T and 2H phase is very important. So you can see over here the results, modified carbon sulfur composite, and Raman gives the combination of 1T and 2H phase, and these are the results. You can see up to 500 cycles, it has maintained a 74.5. Now after optimizing, we are expecting that the cycle capacity retention will increase to above 80%. And for commercialization, again, you can see from this graph, currently what is reported is about 300 to 350 watt-hour per kg, and the goal is to work for greater than 500 watt-hour per kg. And we recently have a project from ANRF, again myself and Professor Sharma are going to collaborate for working on the pouch cells, multi-layer pouch cells for the lithium sulfur batteries. And we have been speaking about carbon. So here carbon is a host material along with the electrocatalyst, and for the lithium sulfur batteries always lithium is taken as the anode, but now we have to work on new materials, because lithium again as anode is not very stable after more than 1000 cycles. Now the new research from Zeta Energy again have shown that aligned carbon nanotubes which are lithiated are acting as very good anode material, and they have made the pouch cells and shown that it is working out well. And the other ones are solid electrolyte, which is again going to increase the cycle life of lithium sulfur batteries. And we have been speaking a lot about this valley of death. From research to the commercialization, ARCI is putting its efforts to bridge the gap between the academia and the industry. So any of you startups who want to work with ARCI along with Professor Sharma, we can work on the fundamental research as well as the upscaling of the materials. We are going to establish a rapid prototyping facility of 2 megawatt capacity, and this is the group at ARCI and at IIT Hyderabad with whom I worked. I also worked with Mr. Satyam, who was an MTech student on the metal sulfur batteries. Thank you very much.
Thank you, ma'am, for the insightful presentation on lithium sulfur battery. Now I request audience to ask questions, and I request to limit to 2 questions due to the time constraint.
Yeah.
Carbon nanotubes, how would one lithiate it?
So this is what we are trying to do. Actually, people at lab level has tried it, but when we have to try at pouch cell level, so they have used this, made a coin cell and put it in the lithium electrolyte, but at coin cell level it is okay. I looked into this Zeta Energy, they have already made, they are showing the energy density, but for that much area of the electrodes, now we are working on that. So soon we want to come up, maybe different deposition processes we have to look for to get that sufficient lithium. Because with the lithium metal foil, this is the problem we are facing, that the dendrites are forming after several hundreds of cycles. Whereas it is expected that with lithiated carbon nanotubes, aligned carbon nanotubes, it is minimized. So we have to work on this, how to do it for large scale. Of course, lithiation at coin cell is easier, no problem. Yeah.
Good presentation. Thank you. Ma'am, I have one question on MOS2, like how to restrict ourselves to control about the phase formation of MOS2, like 2H or 1T. That is
1T
one.
and 2H.
Yeah.
Yeah. So it depends on what process you are using. Okay. So if you are using a hydrothermal process, the time and the temperature. Okay. And if you are using a solid state process, again, the milling parameters and the annealing temperature. These are the most, and we are also successful to an extent to control this 2H and 1T phases.
And how to control the formation of metal oxide, means like, of course, I also work in a similar lane, but the problem is like I used to see the development of metal oxide besides with MOS2 or whatever the TMDs.
So in our process, we have not found MOS2 so much, but it doesn't matter in case of lithium sulfur batteries because metal oxides are also electrocatalysts. So it doesn't really matter. Okay. But in our process, we have very clearly checked there is no metal moly oxide formation. Yeah.
Thank you.
Thank you, everyone. Now I would like to invite Professor Chandrasekhar Sharma for felicitating Dr. Sharda. Moving to our next speaker. Our next speaker is Professor Amartya Mukhopadhyay from IIT Mumbai. Professor Mukhopadhyay is a distinguished academician known for his contributions to advanced materials and energy storage research. We look forward to his perspectives on emerging direction in battery technologies. Professor, please.
This is forward, sir, backward, point. Thank you.
Okay, right, fantastic. So let me first thank Professor Chandrasekhar Sharma for inviting me. And in fact, we are here to celebrate the wonderful 15 years of the Carbon Laboratory, and should congratulate Chandra and all his students and postdoctoral researchers for the same. I have some connection with the Carbon Laboratory, a bit indirectly, but it's a nice connection. So my first PhD student, Ravi Kali, did his postdoctoral research with Chandra, and then one of his very good PhD graduates, Pujita, who is sitting here and whom we listened to an hour back. So she did her postdoctoral studies with me. So it's a wonderful exchange that has happened. And of course, I have been part of some PhD thesis evaluation, etc. And it has always been a pleasure to work with Chandra for whatever it is. And so it feels very nice to be here and to be part of the celebration. Now, so talking about batteries, I always show this map. Of course, it does not list all the institutes where battery-related works go on, but it shows that all over the country there are a lot of activities, and in fact, there is no space to add anything more on this slide, so which is a very good scenario. Now, in IIT Bombay, we have a lot of groups working on various aspects related to batteries, different battery chemistries, various aspects like including simulations and even now recycling. In terms of facilities, we have prototyping facilities. So we have the lab scale prototyping. This is a picture from my lab. single layer pouch cell facility, and we also have a pilot scale facility which can make a few tens of ampere hour cells, both pouch as well as cylindrical. Now this is about my group, and so right now the focus is on the sodium-ion batteries, and we work on the cathode materials. I will talk a little bit about those, alloying-based anode materials, and I will probably also show 1 or 2 slides on that. Now, more importantly, why we need batteries or energy storage is because of this, right? So we still have a lot of places in the country where we have power outages, so we need robust grid energy storage, and which is also sustainable and cost effective. We all are aware of this problem in the cities, moving from the small towns and the villages to the cities. We come across another set of problem, and we need the electric vehicles for that, and affordable electric vehicles for that, right? And India 2030 targets 218 gigawatt hour of battery cell manufacturing. Today we have hardly a few gigawatt hour, but let's see. One should be optimistic. The sodium-ion battery, it's good because not because it is it is supposed to be less expensive once the supply chain is taken care of, and supposed to be sustainable as well, but because it has advantages related to fast charging, then like storage at 0 state of charge, so much safer to be stored and transported, wide temperature window of operation. So these are a lot of operational and safety advantages of sodium-ion batteries, and of course the existing lithium-ion cell fabrication facilities, which they come into existence in the country in hopefully in a year or so, maybe with the LFP lithium-ion cells. So those can be directly used for the sodium-ion cell fabrication. So that's another big advantage. However, there are challenges, and that's why researchers are interested. So on both sides, anode side, there is a challenge. Graphitic carbon does not work. Cathode side, there are challenges. Not one challenge. We need high capacity cathode material. We need to go, because we need to go up the energy density ladder. But then those high capacity cathode materials, they are unstable when it comes in contact with air, water. When you cycle it for multiple cycles, a lot of structural transformations make it unstable. So there are a lot of issues to be addressed, right? But that's why it becomes very interesting. Now, if I talk about some of the grand challenges for sodium-ion batteries, so one of them will be elevating the volumetric energy density. This is where the sodium-ion batteries lack in comparison to lithium-ion batteries. The gravimetric energy density is also a little low, but not too low, but then the volumetric energy density is where it lacks. So elevating the volumetric energy density is very important, and the worst offender for volumetric energy density is basically the hard carbon. So one has to get rid of the hard carbon based anode to do that. Then the low temperature performance is much better than lithium ion cells, but that is one of the important advantages of sodium ion batteries, so there should be focus on that. Of course, when it comes to energy density, it has to go beyond the LFP lithium ion for many applications. And again, fast charging is another advantage like low temperature performance, so there has to be focus on that, so that that becomes a real advantage when for the usage of sodium ion battery. Now, talking about elevating the energy density, a plot not made by me, so it's jumbled up, not my fault. But what I want to show is that if you want to go up the energy density ladder, we need the layered sodium transition metal oxides, because those are the ones which have much higher capacity compared to most other type of cathode materials. These are the different structure types for layered sodium transition metal oxide depending on the coordination of the oxygen ion coordination of the sodium ion. If it's octahedral, it's called O type. If it's prismatic, which has a lot of advantages, it's called P type. So the advantage with P type coordination is that the sodium transport becomes very fast, unlike the octahedral type coordination. But one of the problems with the P type coordination is that fitting in a lot of sodium in this layer becomes difficult. The maximum one can usually achieve is about 0.7 per formula unit, and which is a big problem. Now, another problem with all layered sodium transition metal oxide is that they are highly hygroscopic in nature, so handling storage becomes an issue, and also one cannot even think of using water to prepare the cathode slurry. So one has to go with NMP as shown here. So these are some of the typical issues like multiple structural transformations during charge discharge, sodium vacancy ordering, Yan-Taylor, transition metal dissolution. So those are anyway there. One has to address them. But a major issue is the air-water instability. So handling storage becomes a major problem, and one has to use NMP for preparing the cathode slurry, and many countries want to completely get rid of the usage of NMP for various reasons. So these are some of the aspects one needs to look into, and I will show a little bit of our work related to improving the air moisture instability, so much so that we can go ahead and prepare aqueous processed cathodes. Now, why is it important? Is because if one can actually make the cathode materials air and water stable, the handling storage becomes very simple. One does not need to store them in dry room conditions, so there is a lot of energy and cost savings. Now, if one can prepare the cathode using water, when one does not need to use NMP, again there is a lot of energy savings because the NMP extraction etc. is not needed. Again, dry room is not needed, and water is less expensive than NMP. So overall one can save cost by about 15% just for the cathode preparation step. Now, coming to energy consumption, overall, say for a 1 gigawatt hour sodium ion battery plant, cell manufacturing, one can reduce energy consumption by this much and also carbon footprint by this much on an average. So it's very important to make these cathode materials air and water stable. Now, how to do that? Not just that, but even many performance parameters can be tuned by looking at the very structural aspect of the layered transition metal oxide. The interesting and the nice thing is that the oxygen ion is connected to sodium ion on one side, a highly ionic bond, but the same oxygen ion is bonded to a transition metal ion on the other side, a ionocovalent bond. So while this is highly ionic, one cannot do much to this bond by itself, but one can tune the effective negative charge on the oxygen ion by tuning the covalency of this bond. For example, if we make it more covalent, the electron density moves away from the oxygen ion, and then this bond can become weaker and longer. And by contrast, if one makes this bond a little bit more ionic, the effective negative charge on the oxygen ion increases and the sodium oxygen bond becomes stronger and shorter. So one can tune the effective negative charge on the oxygen ion, and one can tune the sodium oxygen bond strength and the length. So these can help improve the air water instability because one can suppress the spontaneous sodium extraction when exposed to humid air or water, and by tuning the effective negative charge on the oxygen, one can make the p-type structure, stable with a higher sodium content. So these are the various things one can do. So again, not going into the detail of how one can improve the air water stability based on tuning the effective negative charge. The other way in which one can again improve the air water stability without going into much detail is if one can place a cation in a tetrahedral site of the sodium layer. That is because the sodium insertion extraction, including the spontaneous dissociation when exposed to air water, will happen via the intermediate tetrahedral site, and if one can block it by a cation which can be stable at the intermediate tetrahedral site, like titanium 4 pulse, a D0 cation in this case, one can improve the air water stability. So much so that one can go ahead and prepare aqueous process slurry, and interestingly the aqueous processed cathode exhibits better cyclic stability than the NMP processed counterpart, and that is because of the better binding stability of the aqueous binders as compared to the PVDF binder when used with NMP. Now coming to the high sodium containing P2 or the prismatic. So in the prismatic coordination, the oxygen ions are directly one on top of the other. So now if we want to fit in more sodium here, my oxygen ions will come closer. But then there will be repulsion between them, and so the structure will become unstable. But if I can lower the effective negative charge on my oxygen ion, I can push in more sodium, have the oxygen ions come closer and still maintain the structure stable. So that is the overall idea. So now if we can increase the covalency of the transition metal oxygen bond, if we can increase the covalency, then one can in principle stabilize the P2 P2 structure at different sodium contents, including very high sodium content. And this map clearly shows a segregation between the reported P2 and O3 structure cathode materials based on a descriptor called charge to size ratio, which we coined. So it basically is an indicator of the covalency. I did not go into detail of this, so I will just leave that. Overall, the more covalent oxides will form a p-type structure, and the less covalent ones will form a o-type structure. So by increasing covalency, one can have p2 structure with a higher and higher sodium content. So like as long as the charge neutrality is maintained. Because if one keeps increasing the sodium content, one cannot go up the charge to size ratio because of maintaining the charge neutrality. So there will be a cutoff. Anyway, so based on this idea, we could develop a 0.84 sodium containing P2 structured layer transition metal oxide, and which has a good capacity because of the high sodium content, and also it's very, very stable. It's also very stable when aqueous processed. As I'm showing here. So again, one can see the aqueous processed ones exhibit better cyclic stability than the NMP processed one, similar to the O3 structured cathode material. So now, yeah, so it's a full cell with the aqueous processed P2 structured cathode. Now this is about elevating the capacity by invoking anionic redox and also very stable anionic redox. Not going into details here because of lack of time, but again the high covalency helps the anionic redox become very stable in this case, and one can see even increasing the upper cutoff to get capacity close to 200 milliampere hour per gram does not negatively affect the cyclic stability a bit too much, even though considering that the electrolyte also becomes unstable when we go up to 4.5 volt. Right. So yeah, this shows some proof regarding the reversible anionic redox. So not going into detail. Now going to the other side, the anode material, as I said, graphitic carbon does not work with sodium ion batteries. It does not work. Nothing to do with the interslab spacing or the interlayer spacing. So we can neglect this part, right? But overall, sodium does not get stored in the graphitic carbon lattice. But it can get stored reversibly in a disordered carbon or hard carbon lattice. However, there are problems related to potential sodium plating, because a lot of sodium gets stored at a potential very close to the sodium plating. So at low temperature, high current density, there will be a finite chance of sodium plating and the irreversible capacity loss. So the carbon experts can actually work on improving this first cycle irreversible capacity or minimizing the first cycle irreversible capacity loss, and that will do a lot of good to the sodium ion battery community, and also improving the reliability of the performance of hard carbon. Like even batches from the same vendor, say Curare type 2, we have, I'm just taking the name, no, I mean nothing to do with Curare, but any make, there is always a batch to batch variation which many of us have found. And that is because unlike graphitic carbon, which has a well-defined structure, hard carbon does not have a well-defined structure. It does not have a structure per se. So little bit change in the structure affects the performance in major terms. So that's one area where the sodium ion battery needs a lot of work on the hard carbon based anode. But if we want to look for alternate anode material, tin is a very good choice. And that will also elevate the volumetric energy density significantly. Hard carbon has a very low density, tin has a very high density, and also much higher capacity for sodium storage. The volumetric density can get enhanced in significant terms. However, tin volume expansion contraction, as we know, during desodiation, so it will disintegrate, there will be mechanical stresses, disintegration, and so one would typically need a lot of nanoscaled buffers like graphenic carbon, carbon nanotube, all those which again lower the volumetric capacity and also lead to irreversible capacity loss. So important work will be to use tin without any such nanoscaled carbon buffer. And that's one of the things we have tried to use. Okay, so this shows how less tin can store probably more sodium than hard carbon. And some of the startups are also looking at tin-based anodes for sodium ion batteries. Now, so if we can alloy tin suitably, for example, tin bismuth in this case, one can improve the cyclic stability in significant terms just by ball milling the tin bismuth without the need of any nanoscale carbon on any kind of buffer. So that keeps the volumetric capacity intact while improving the cyclic stability in significant terms. Moving further, we use the metallurgical process of solid solution precipitation strengthening by using a little bit bismuth, lowering the bismuth to 10 weight% as per the phase diagram, and invoking the principle of solid solution and then precipitation of bismuth out of solid solution, which is called solid solution cum precipitation strengthening, we could make really inherently strong tin, and which again shows very good stability over multiple cycles, these 1000 cycles here, and without the need of any nanoscaled carbon or any buffer as such. So with this, let me come to the end of my talk. So I hope I have been able to tell you something about how to improve the air-water stability of the layered sodium transition metal oxide cathode materials and why we need to do that. High sodium containing P2 structured layered transition metal oxide, and now precipitation strengthened tin which does not need any buffer to retain capacity over multiple cycles without any problem as such, in half cell as well as in full cells. Right, so these are so let me acknowledge the funding agencies, the collaborators and the PhD students. So a major part of the work that I showed, that I've shown was done by Bachu Sravan, who was a postdoctoral, after PhD from my group, he was doing postdoc at MIT. Now he has joined a battery company in the United States. Adrija is looking at the oxygen redox part, which I showed a little bit about. Then Pranay and Noel did primarily worked on the tin-based anode material. So Pranay already graduated. Noel is doing his PhD right now. Okay, so with this, my group thanks all of you. This is also more than 15 years old now. So that's a startup which we co-founded last year in summer. It's still a toddler. And more importantly, so we have the Battery Research Society, which was again established 2024 summer. And so the membership is open. So in case you are still not a member, please do apply for membership. Last year in December, we had the first international meeting of the Battery Research Society successfully conducted in Bangalore. The chairman was Nagafani from IISc Bangalore. This year, save the date, December 9 to 11 in Varanasi, a very nice place. We have the first national meeting of the Battery Research Society, and I would like to see all of you there. And so it will be chaired by Professor Rosie from IIT BHU. So with this, I finally come to the real end of the talk. Thank you very much.
Thank you, sir, for the insightful talk on sodium ion battery. Now I invite audience for their question. Kindly limit the questions to 2 questions.
It's working?
Yeah. Yes.
Yeah. Thank you, sir. For a battery, generally we consider voltage curve is the heartbeat of any battery actually. So particularly in even one of the work regarding the aqueous approach and with the NMP approach, the aqueous approach was showing nearly flat compared to NMP approach. So what will be the approach? Is there a kind of thermodynamics or just it's kind of
the potential profile will not change, or it has not changed?
No, but if you see on that diagram, so
the potential profile cannot change because it is the potential profile is determined by the cathode or anode material and a little bit by the electrolyte. So which all remains the same. So which one?
Slope. I am talking about the slope, sir. Actually.
Which one?
Yeah, your first work actually you presented.
This one?
Sir,
let me see.
Screen is not visible.
Oh, okay. I did say it will come.
Yeah, this one. You see that aqueous process looks like kind of better slope. Whether
no,
as
it's fairly similar.
No,
so
no, the discharge portion basically.
I think it's fairly similar. So the x-axis scale is not the same, which should actually be same for presenting. But otherwise, so there is hardly any
Like
difference in the
it's
behavior.
looking like dropping more in case of PVDF, but in your aqueous approach, it was really good actually. Looks like actually again, it looks like.
To me, it's.
Yeah.
I think it's the same. There is no plateau in either case, because the structural transformations are suppressed by the composition.
Yeah,
So
that's
there
the
is,
question actually.
yeah, right. So only to start with, you see the O3P3 plateau, O3 to P3. That's all. Okay, so you mean the initial part is a little flatter here as compared to here. So that should not be related to the aqueous processing. That may be related to the little bit of IR effect maybe. There is a slight nucleation over potential as I can see here, which is not here. So that's a very good observation in the first cycle. But again, that cannot be anything to do with the aqueous processing as far as I can think of.
Okay, because we generally think of the thermodynamics way. Actually.
No. So that is related to the material, right? So aqueous processing is just about mixing the cathode and the material and the binder and the carbon additive, right? So it cannot be all. The only difference it can be is probably with the resistance, which may change the IR part a bit, but then, as you pointed out nicely, this part is now looking a bit interesting because I can see a slight nucleation over potential here. There is nothing here. So that's actually interesting, which I did not note earlier. Right. But the discharge is fairly similar. I don't find any difference in the discharge as such. Yeah. Nice observation.
Look at the hard carbon. Sodium ion battery, we know the kinetics are faster than lithium. The question comes when you want to design a hard carbon, the pores, let's say we design more closed pores than open pores, and you have less surface area. That is preferable to address your ICE issues. But how to address this kinetics again? When you have less surface.
Yeah, again, I have never worked on hard carbon per se. So yeah, so by changing the ratio of closed porosity to open porosity, you can like tune the slope capacity versus plateau capacity. All these things are fine. Now in general, just like it is graphite for lithium-ion battery, it is hard carbon for sodium-ion battery, which is the bottleneck for the rate capability of a cell, right? So whatever you do, hard carbon will not let you go beyond a certain charging current because it will lead to sodium plating. So irrespective of how much open versus closed porosity you have, because the potential profile at the end is very close to the sodium plating. So it will lead to sodium plating. So that is the bigger bottleneck, right? But if one increases the surface area, again the plating problem is still a problem, right? And that is on top of the irreversible capacity loss, which kills the cell. So like less than I would say less than 5, but typically 2.5 or less than that specific surface area is preferable. But again, I have not worked on hard carbon, so I don't know how to tune these.
No, the worry is we can tune that, but the worry comes the kinetics get slower when you reduce the surface.
Yes,
so
but at least the cell will work.
Cell work, yeah.
But if you have so much 20% first cycle irreversible capacity loss, the cell will die very soon.
Correct.
Unless you have too much of sacrificial sodium.
Thank you.
Thank you, sir. Next, I am pleased to invite our alumni, Dr. Manohar Kakurne, and the first PhD graduate from the Carbon Lab. Now, he is assistant professor at NIT Warangal, and his research focuses on electrochemical energy storage and innovative material design. And we look forward to his presentation. Welcome, sir.
Yeah. Good afternoon, everyone. Are we offline? Yeah. So we know we are online.
Insightful presentation.
Hello everyone. Just Manor has presented, and after that there was an announcement from the chair. Is there any question to him or not? Nobody asked the question. Then I thought, should I give the presentation or not? So that is the dynamic in my mind. So I will try to finish up as soon as possible. And question is open at any time. You don't need to become at the last moment. You can ask me anytime actually. So as being a postdoc here, I was here. After that I moved to the USA being faculty there, and then I come back to the India again as a startup. So this is the kind of different transition for me, because being a researcher and being a faculty in US and coming back to the India, so where in US electron also counts, where the electron goes actually for your reactions, and India where you are going is counts actually. So it has different meanings. But let's celebrate the 15 years of Carbon Lab with celebrating the 15 years of metal CO2 battery excellence. Before that, lot of talk has been done. So I thought the talk should be on some different chemistry. So the metal CO2 battery chemistry is one of my chemistry in my bottom of heart. I can say that the chemistry is there. And as you started any YouTube videos, you know there is something called come with the advertisement, right? Same thing is here. Now this is 30-second advertisement is there. You cannot skip. So the thing is that I currently leading the startup, that is the Brahmayan Private Limited in Bhubaneswar. We basically make advanced materials. We started with the graphene oxides and the reduced graphene oxides. By the way, if you order this material from the Amazon, for 1 gram you will get almost 400 rupees. But if you buy directly from me, from a website, you will get 300. So this is discount for you guys only for 15 years of Carbon Lab. Coming to the point, so metal CO2 battery is a very new chemistries. Already there is a lot of fights with the chemistry of the batteries, whether lithium ion, sodium ion, lithium sulfur is going on actually. Every faculty, every startup is trying to say that my battery is the best battery, and that is there. So, but in between we come up with the new chemistry called as the metal CO2 battery chemistries, and it is a really new chemistry. You can see at the first in 2000 around 11 or 12 this concept is formulated through the publications, and after only 8 years the Carbon Lab started to make the metal CO2 batteries with their own having some contribution in the field. Basically this slide is from the chemical reviews, that is a very good reviews. They only cited that this work, and they have given that 2021 first lithium CO2 battery is established from the Carbon Lab, which has a different meanings, has a different contribution in that field. Again, the thing is that you can think at that point 2021 the topic was so new, even a nature journal will not accept your paper on this topic because the topic is new. So the publications work on the audience also, as well as the how many people can cite those things actually. So this way you can see that much of tough the chemistry was,
And Carbon Lab has started that works, and has today we can see there are a lot of application even in nature also. So you see the how the any new chemistry or new field is grow over the periods. Just you have to keep one thing, that is believe on that chemistries. So lithium CO2 battery chemistry is like not kind of lithium-ion batteries. It has very complex chemistry, I can say, because in lithium-ion battery or lithium-sulfur batteries, all the batteries you see only two elements. One is a solid, another is a liquid. But this chemistry has a solid, liquid, and air also. So it makes very complex actually. So right now people are not able to solve the ACI problem in the lithium-ion battery itself, even it is commercialized. Think of this metal CO2 battery is the biggest challenge in that cases. Further, the chemistry is very simple. Here we use one side is the lithium anode and another side as a CO2 as a cathode. CO2 as a cathode means the CO2 will come through the porous structures and the lithium will be going through the electrolytes forming the lithium carbonates. Now we will discussing about the more about the perspective of this metal CO2 battery in general way, because this is the last talk for today's. So metal CO2 battery has different way like aqueous and non-aqueous systems. So non-aqueous system I already work with the Carbon Lab here, and for aqueous systems I work in the USA also. So you see in the aqueous systems, like particularly the iron, this is iron is given by from our lab actually as the aqueous system in metal CO2 batteries. And particularly non-aqueous systems, you can consider a lithium, sodium, potassium is a better choice. For aqueous system, we can consider a non-alkali metals like zinc, aluminum, magnesium, and iron. Now coming to the main point that most of the people are discussing about the metal CO2 battery is that it is a battery or it is really fix the carbon, because the metal CO2 battery has been projected as a carbon fixer also, and that's why the people are having the mind on that. Okay, metal CO2 battery something is different than the existing battery technology. So now the question is that if this metal CO2 battery is really battery, then how it will fix the carbon, because once you charge it, once you discharge it, CO2 will consume. When you recharge it, CO2 will come to back to the atmosphere. Then how it will be the carbon fixing battery actually. So now going to that answer is that if you are working this battery as a primary battery, yes, it can fix the carbon, as the lithium is reacting with the CO2, it forms the lithium carbonate. So lithium carbonate can be a fixing, but still primary is not a way to say that is a carbon fixing. Now so that there is a research is going on that metal CO2 battery to see the other part of that, how it fix the carbon. So you see this is the more scientific slide again I am putting. This is the slide where you can see this particularly is the Raman. This Raman is nothing but the during the discharge, this lithium is going move towards the cathode sides, reacting with the CO2 and forming a lithium carbonate. And you see the chemistry is that lithium reacting CO2 forming carbonate plus carbon. So according to this graph, D band is there, G band is there, that represent the carbon, and the lithium carbonate is there already. So we can see the discharge follow the rule actually. Now the concept is that how about the charge, because carbon is involved there as a solid product actually. So now you see the charge is very interesting. You see in the charge, this is the Raman during the charge, during this charge. So you see the carbon is remaining as it is. So it tells us that during the discharge, lithium reacting with the CO2 forming the lithium carbonate and the carbon, but during the charge, this lithium carbonate get back but not the carbon. So then based on that chemistry we can see that CO2 is now coming as a carbon, and then I can say that CO2 fixed the carbon. So this is way how the lithium CO2 battery has been considered as a carbon fixing as the element actually. So with the time constraint I will tell you that the primary battery CO2 fix is almost 100% I can say, but again the energy cost will be considered for here. But the secondary battery, yes, it fix almost 33% of the CO2. Means 3 CO2 if you put it into the battery, almost 2 CO2 will be come back during the charge, but at least 1 will be the consume, it will be deposited as a carbon plus oxygen Again, I am putting the word plus oxygen. And that can be validated with this graph where you can see oxygen evaluation is happen actually. So with this slide and overall slide, we can say that metal CO2 battery is a carbon fixing also. Now coming to the again case is that energy storage battery or not, because it fixed some extent of the carbon. So now the thing is that in the previous slide your substrate was a gold. Now we are using the substrate is the ruthenium. So in ruthenium case we observe that basically the researcher observed that not only lithium carbonate will back but carbon also will back. So when you have the substrate as a ruthenium, then you observe that it has a complete charge process, means it has the energy storage application also. So that's why it is called as energy fixing CO2 fix as well as energy storage device. And obviously there is as I said that the chemistry is very new. Till now we did not find out how the ruthenium is fixing this problem as energy storage and how it's happened with the gold substrate. Again, if you guys are working on metal CO2 batteries or any air batteries, there is simple way to develop the new chemistries. That is that just you put the any metal rod, any metal such that the metal has one part is covered with a tape, another part is untaped, and just put it into the solution, whatever the solution you are using for a lithium ion battery, whether it is salt or without salt. So in that cases, what you have to do it, your objective is that to bring the metal CO2, then put it the CO2 environment also, and just keep it this setup for at least overnight, and then you try to come up with the opening that setup in the next morning. So you will find that so where you tape it already like this tape it nothing will be formed, but something is deposited out air actually. So we found that okay, if you do the more analysis, particularly in these cases I did, so you will find that over this depositions there is extra peaks, and after that there is no peaks. That peaks represent the zinc carbonate actually. So we can say that zinc has a reaction with the CO2. Now again the word I use is the reactions, whether it is chemical or electrochemical, that we need to be justified. For that we have to make a full cell. Once you make a full cell, you will observe that when you have the zinc or the substrates like a carbon or anything, you will find that the deposition of the same compound, that is zinc carbonate. Then you can say that that reaction was not the chemical reactions only, but it was the electrochemical reactions. This way we come up with the new chemistry kind of thing, that is zinc CO2 battery or iron CO2 batteries. So this is a very fundamental way to bring it with the new chemistries. The fundamental way to bring it with the lithium ion battery is that go with the band structure, go with the homology calculations. If see that it's work for you, then you can say that it works. For a metal CO2 battery, it's very new, growing. Still not we did not figure out how the first principle will work out here actually. Okay, so again the concern with the metal CO2 battery is the reversibility. You see when you use the metal CO2 battery, the capacity is 16,000. Again I am repeating the word 16,000. That much of capacity we are reporting as a CO2 battery, but you see if you charge this battery again back, hardly you will get a 10% of charge it. So the main concern about the metal CO2 battery is the reversibility, and the prominent factors that are associated with those batteries is that there is a blockage of pores and active sites because we are using the CO2 on the porous structures, and that depositing the lithium carbonate, which is very hard to decompose, and that is the reason we did not get the charge back. And another problem is that if you want to get charge back, you have to need a more energy, but on that more energy electrolyte is not stable, so electrolyte also will decompose, and that is the true problem with the metal CO2 or metal air batteries. So again the problem with that is that the researchers are smart, so they come up with the limited capacity testing. This is a very dangerous testing actually. It comes with your benefits. So it is that here you can see it is 16,000. Again it is 16,000. You see where they tested 500. So almost 30 times less. Means you are earning 100 rupees. You are now earning only 3 rupees. Is it justifiable? Then we have to make a question on it actually. So another is that over that question or answer kind of things, try to do your testing on the limited capacity such that it will at least beat the lithium-ion batteries. We don't want that 1800 watt-hour per kg of capacity of the metal CO2 battery, but at least it can beat the current lithium-ion battery, which has almost 150 milliampere hour per gram. So that will be best way to go ahead with the metal CO2 battery testing when you consider the capacity. Also capacity per gram. Again, this gram is very important. Lots of researchers and lots of startup plays with the gram actually. The gram is always try to bring it with your original gram of the total weight of the batteries. Okay, just again going with the time actually, so just I will take 2 minutes, Sony. So again, promising part of the metal CO2 battery is that whether this metal CO2 battery will solve the problem of Mars or not, because you heard that metal CO2 battery is a very good alternatives in particularly in in Mars missions. The Mars mission has their own like Mars environment has their own concern. Particularly, it has a gas composition problem, which is not having the total CO2. It is average temperature is minus 60 degrees Celsius and average pressure is minus 6 millibar actually. So you can think of the pressure is also low, temperature is very bad, and the gas composition also different actually. So these three factors we need to be figure out to make it okay. It will be useful for the Mars. So over that the first the flag whatever we are showing in 2021 that is carbon made is the gas composition. So carbon laboratory has a contribution of this 15 years of the research experience in the particular metal tree is that testing this battery in the gas composition with all the requirement like 95.9 CO2, remaining O2, CO and all these things. And that time we tested only the single charge discharge and we published that concept in the materials letter with the feature also actually. But now today the Carbon Lab in the position to do at least more than 100 cycles. That is a good achievement I can say in this field. So another problem is that low temperatures. So there are a study, they are doing the low temperatures. So basically the low temperature is, as I said, that average low temperature is minus 60 degrees Celsius. So you think of operating the any batteries minus 60 degrees Celsius is challenging. So particularly we should have the electrolyte, which maybe have the freezing point is minus 100 degrees Celsius kind of things. So right now the researcher with this kind of electrolyte we can utilize for a minus 60 degrees Celsius. And you see the kinetics, they observe that particularly the growth of the discharge product is almost very fine when you are using the minus degree Celsius temperatures, because the same like minus temperature means your current is low. Your kinetic is low, obviously it will be grow very small particle compared to the high temperatures. So another thing is that with that previous is our gas composition, previous one is the temperature. Now one of the study recently, I think that is basically motivated from our work, but I cannot say exactly how they are claiming their works, but anyway, so the temperature plus gas composition they have took it and they have tested this concept in the room temperatures and 0 degree Celsius. So means the temperature also is working well, gas composition is also working well. So metal CO2 battery for Mars is working almost the same, just now need to fix the pressure actually. So pressure is the concern actually. So then we have already talked, as I said that I work with the metal CO2 battery in the other countries also. So there also we figure out that if you want to have the two CO2 molecules in one atmosphere, their distance is 3 nanometers, but in the Mars atmosphere it is a 15 nanometers actually. And so that if you want to bring that all the CO2 in 1 liter of CO2 at 1 atmosphere, you need to be cover at least 175 liters of Mars atmosphere actually. And that problem is kind of, they say that, or we come up with the solution, just use compressor. That's it. Because the compressor if you use, this is one time you have to use, not the all the time you have to use. So the best way to go with the compressor to solving that slow kinetics problem of the CO2 in the present of this. So yeah, there is a problem with the, again with the materials, also material selections. The for that we have already with the review paper with the NASA and University of North Texas, that when I was a faculty there. So we already published that paper regarding the unlocking the metal CO2 battery for Mars explorations. As a Mars is the red planet, we need a chemistry which is related to that Mars. That's why we come up with the iron CO2 battery also. And I think finally I can say that TRL level for metal COT batteries to define at this moment is very difficult because it is a Mars mission. Mars mission means lot of money can come, and this TRL can be solved in within a couple of years. With that, I will summarize that metal COT battery is not only energy storage, it is also fix the CO2 but also generate O2. With that, I will thank you here. Thank you.
Thank you, sir, for your presentation. I request audience if they have any questions.
Sure, sure.
Lab, you are using 100% pure CO2, right?
No, we have the mixer of that.
Are
95.
replicating the
Exact
air
composition
of Mars?
the Mars. Yes, yes.
Okay, then no questions.
Yeah, okay. Thank you. Thank you.
Thank you, sir.
Thank you. Yeah, no, no, no. That guy is going to Mars, but I will go to the Lingampalli actually.
With this, we come to an end of the technical section 2. Now I like to invite Professor Chandrasekhar Sharma to the stage for felicitating our speakers and inviting all the speakers, Amartya sir, Manohar sir and Anil sir to be in the stage.
Very good. So I used to continue. I used to continue some research. Now only selling the powder.
I am dealing on the carbon lab.
You can turn off, I think. Otherwise, close the lid.
You can close it. So that it can come.
Thank you and congratulations once again.
Oh, a lot of efforts are there.
Thank you all. I sincerely thank all the speakers for their insightful presentation and the audience for their active participation. Our next scheduled activity is the Carbon Lab visit. Those who are interested and are kindly requested to coordinate with the registration desk for further arrangements. Also, we are delighted to invite you all to the cultural program by Kavali Night by the Varsi Brothers, which will begin at 6:45 p.m. at Auditorium 1. We warmly welcome everyone to join us for this cultural evening. Thank you.
Yeah, so I mean, if you want to visit the Carbon Lab, please see at the registration desk, and we will reassemble, not in this room, there is a main auditorium, where we will reassemble for the cultural program at 6:45. So see you all there.
Good evening, ladies and gentlemen.
This day marks a momentous occasion, the 15th anniversary of our Carbon Lab's journey in pushing the frontiers of innovation, discovery, and excellence. From humble beginnings to groundbreaking achievements, we have grown together, turning challenges into triumphs over these remarkable 15 years. As we celebrate this occasion, we take a short break from research and step into something equally powerful, a music that speaks to the soul.
Yes, we are referring to the Sufi music. There is something timeless about the Sufi music. As Allama Iqbal says, दिल से जो बात निकलती है असर रखती है पर नहीं ताकत परवाज मगर रखती है. And that is exactly what Hawali does. It connects, uplifts and stays with you.
Tonight, we are honored to welcome a musical legacy that has echoed for 9 centuries of devotion and melody.
From the sacred courts of the Mughals to the Nizams of Hyderabad, their ancestors, Padma Shri Aziz Ahmad Khan Warsi and Ustad Zahir Ahmad Khan Warsi, have preserved the pure essence of Sufi Qawwali since the times of Hazrat Nizamuddin Auliya and Amir Khusro. They are recognized especially for their Sufiana Qawwali, Ghazal, Thumri, Bhajan, and classical Bandish. So please put your hands together for Asad Ahmad Khan Warsi ji and Amjad Ahmad Khan Warsi ji and their team from the incomparable Warsi brothers.
छब बनाई के मैं जो पी के पास गई,
अपनी छब बनाई के मैं जो पी के पास गई।
जब छब देखी पीहू की मैं तो अपनी भूल गई।
अरे नैना मिला के मुझसे नैना मिला के,
नैना मिला के मुझसे नैना मिला के, नैना मिला के मुझसे नैना मिला के,
नैना मिला के मुझसे
नैना मिला के मुझसे नैना मिला के मुझसे
हमारी दुनिया बदल के रख दी, नजर का मिलना हुआ बहाना।
हमारी दुनिया बदल के रख दी, नजर का मिलना हुआ बहाना।
उधर निगाहें मिली किसी से,
उधर निगाहें मिली किसी से,
इधर ये दिल बन गया निशाना।
नैना मिला के मुझसे नैना मिला के मुझसे नैना मिला के मुझसे नैना मिला के।
आशा जन इन नयनन में सो पलक ढांप तो हेलूं।
साजन इन नैनन में सो पलक ढांप तो हेलूं।
ना मैं देखूं और को ना तो है देखन दूं,
मिला के मोसे नैना मिला के मोसे नैना मिला के मोसे नैना मिला के मोसे
नैना मिला के सेना चला के
नैना मिला के सैना चला के
बात अघम कह दी नीरे मोसे नैना मिला के
बात आदम कह दी नीरे मोसे नैना मिला
मैं
के
जो गई थी देखन बजारिया
मैं जो गई देखन बजारिया
आजा निजाम से मोरी लड़ गई नजरिया बात अघम
कह दी नीरे मोसे नैना मिला के
बात अघम की भी का बात अघम की सो कहन सुनन की नाए
का बात अघम की सो कहन सुनन की नाय।
बात अघम यानी छुपी हुई बात जो कहने सुनने की नहीं है, जो सिर्फ समझने की है आंखों से। जैसे लड़ गई नजरिया आई बात, तो वो क्या बात है? बात अघम कह दी भी का बात अघम की सो कहन सुनन की नाए। और जो जाने सो नाय कहे और जो कहे सो जाने नाय। बात अघम
कह दी नीरे मोसे नैना मिला के
हाँ, बल बल जाऊं मैं तोरे रंग रजवा
बल बल जाऊं मैं
तोरे रंग रजवा बल जाऊं
रंग रजवा बल बल जाऊं
मैं तोरे रंग रजवा मैं तोरे
रंग रजवा मैं तोरे रंग
रजवा मैं तोरे रंग
रजवा मैं तोरे
खुसरो रैन सुहाग की सो जागी पी के संग।
खुसरो रैन सुहाग की सो जागी पी के संग।
तन मोरा मन पीहू का सो दोनों एक ही रंग।
आहे अपनी सी
रंग दी नीरे मोसे नैना मिला के अपनी सी रंग दी नीरे मोसे नैना
रंग तुम्ही रंग रजवा तुम्ही हो, रंग तुम्ही रंग रजवा तुम्ही हो। रंग के धनी मोरी रंग दो चुनरिया
अपनी सी रंग दी नीरे मोसे नैना मिला के
गोरी गोरी बैया हरी हरी चुरिया
गोरी गोरी मैया हरी हरी चूड़िया गोरी गोरी मैया हरी हरी चूड़िया
वाकी गोरी गोरी बैया वाकी
गोरी गोरी मैया बाकी गोरी गोरी मैया बाकी गोरी गोरी मैया बाकी गोरी गोरी मैया
वाकी गोरी गोरी बैया वाकी गोरी
गोरी गोरी मैया बाकी गोरी गोरी मैया बाकी गोरी गोरी मैया बाकी
अरे जचता मेरी नजर में कोई नाजनी नहीं, जब से वो दिल नशी है कोई दिल नशी नहीं। ऐसा हसीन कोई खुदा की कसम नहीं, जैसा मेरा सनम है किसी का सनम नहीं। ओ बाकी
गोरी गोरी मैया बाकी गोरी गोरी मैया बाकी गोरी गोरी मैया बाकी गोरी गोरी मैया बाकी
हरी हरी चुनिया गोरी गोरी मैया मैया पकड़
हरी नीरे मोसे नैना मिला के
मैया पकड़ हरी नीरे मोसे नैना मिला के मैया पकड़ हरी नीरे मोसे नैना
मोसे
मिला
नैना मिला के नैना मिला के मोसे नैना मिला के मदवा पिला के
प्रेम भटिका मधुआ पिला के प्रेम भटिका
वो है मदवा पिला के प्रेम भटिका
मधुआ पिला के प्रेम भटिका
प्रेम भटिका मदवा पिला के अपने माथे पे बिंदिया को सजा रहने दो, ये सितारा मुझे मंजिल का पता देता है।
अपने माथे पे ये बिंदिया को सजा रहने दो, ये सितारा मुझे मंजिल का पता देता है।
और इश्क गर एक तरफ हो तो सजा देता है, इश्क गर दोनों तरफ हो तो क्या बात है, मतलब समझ में आ गया। और मैं किसी जाम का मोहताज नहीं हूँ हसरत, मैं किसी जाम का मोहताज नहीं हूँ हसरत, मेरा साकी मुझे आंखों से पिला देता है। मतवारी कर दी मेरे मुँह से नैना मिला के, मतवारी कर दी मेरे मुँह से नैना मिला के।
धने 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 तसद्दुक हजार मैं खाने, और तेरी नज़र की लताफत शराब क्या जाने। ये वो शराब नहीं है जो बार में मिलती है, उससे भी मुझे कोई एतराज़ नहीं है, वो सब अच्छी बात है। हाँ, मेरे को चाय पीने की आदत है बस, और कुछ नहीं। और तेरी नज़र की लताफत शराब क्या जाने, गिला नहीं जो गुरीज़ा है चंद पैमाने, निगाह यार सलामत हजार मैं खाने। और नज़र उस अंजुमन नाज तक बआसानी नहीं जाती, अगर जाकर पलटती है तो पहचानी नहीं जाती। और कितने तीर उनकी नज़रों के उतारूं दिल में, दीदा शौक़ ने डाला है अजब मुश्किल में। तेरे जलवों के सिवा क्या है निगाहो दिल में, तू ही तू है मेरे एहसास की हर मंजिल में। मतवारी कर दी मेरे मुँह से नैना मिला के, मतवारी कर दी। एक शेर समाज फरमाइए कि कौन है जिसने मैं नहीं चखी। अच्छा, मैं कहते हैं शराब को, कौन है जिसने मैं नहीं चखी, कौन झूठी कसम उठाता है, कौन झूठी कसम उठाता है, मैं कदे से जो बच निकलता है, तेरी आंखों में डूब जाता है।
मतवारी कर दी मेरे मुँह से नैना मिला के,
आप तो सैया बने मनमोहन,
आप तो सैया बने मनमोहन,
आप तो सैया बने मनमोहन,
आप तो सैया बने मनमोहन, आप तो सैया
बने मनमोहन,
सैया बने मनमोहन, सैया बने मनमोहन, सैया बने मनमोहन,
ओ सैया बने मनमोहन, सैया बने मनमोहन,
सैया बने मनमोहन, सैया बने मनमोहन, सैया बने मनमोहन, सैया बने मनमोहन,
ओ सैया बने मनमोहन, सैया
बने मनमोहन, सैया बने मनमोहन, सैया बने मनमोहन, सैया
बने मनमोहन। अजल से तेरे संग ये बंधन हुआ है, मैं जोगन हूँ तेरी तू मेरा पिया है। तुझे क्यों ना चाहूं, तुझे क्यों ना पूजूं, मेरे मन के मंदिर का तू देवता है सैया
भले मन मोहन सैया भले मन मोहन सैया भले मन मोहन सैया भले मन मोहन
मन के मंदिर में बिठा कर मैं तेरी पूजा करूं
मन के मंदिर में बिठा कर मैं तेरी पूजा करूं
तू मुझे देखे न देखे
तू मुझे देखे न देखे
मैं तुझे देखा करूं बने मन
मोहन सैया भले मन मोहन सैया भले
आपको तो सैया बने मन मोहन मोहे बेदम करी नीरे मुझसे
नैना मिला मोहे बेदम कर दी नीरे मुझसे मोहे बेदम कर दी नीरे मुझसे नैना मिला के
खुसरो निजाम के बल बल जइए
खुसरो निजाम के बल बल जाइए
वाके बल बल जइए वाके
बल बल जाइए वाके बल बल जाइए वाके बल बल जाइए वाके
बल बल जइए वाके
बल बल जाइए वाके बल बल
खुसरो निजाम के
बल बल जाइए वाके
ओ बल बल जइए वाके बल बल जइए
बल बल जाइए वाके बल बल जाइए
बल बल जइए वाके बल बल जइए
बल बल जाइए वाके बल बल जाइए
वाके बल बल जइए बल 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 जइए
बल बल जाइए बल बल जाइए वाके बल बल जाइए
गाम के बल बल जइए मोहे सुहागन की मेरे मोसे नैना मिला
मोहे सुहागन की निर्मोह से नैना मिला के
मोहे नैना मिला कर मोसे
नैना मिला के नैना मिला के मोह से
नैना मिला शुक्रिया थैंक यू
आपके सामने हमारे और सबके फेवरेट चंद्रनेहा साहब की फरमाइश पेश कर रहे हैं।
वो मुलाकात वो हंसी लम्हे वो नजर से नजर का मिल जाना वो मुलाकात वो हंसी लम्हे वो नजर से नजर का मिल जाना आँख रोशन है उन नजारों से हर नजर में खुमार बाकी है मेरे रश पे कमर मेरे रश पे कमर तूने पहली नजर
मेरे रश के कमर तूने पहली नजर
जब नजर से मिलाई मजा आ गया
मेरे रश के कमर तूने पहली नजर जब नजर से मिलाई मजा
आ गया
मेरे रश के कमर
रश के कमर रश की कमर
रश के कमर रश के
मेरे रश की कमर रश की कमर जरा मुस्कुरा दो, ये पर्दा हटा दो, इधर मेरे दिल पर भी बिजली गिरा दो। बर्क बिजली को कहा जाता है। जरा मुस्कुरा दो, ये पर्दा हटा दो, इधर मेरे दिल पर भी बिजली गिरा दो। मुझे आजमाना है अपनी नजर को, बला से जले कोई जलवा दिखा दो।
बर्क सी गिर गई, काम ही कर गई, आग ऐसी लगाई मजा आ गया। बर्क सी गिर गई, काम ही कर गई, आग ऐसी लगाई मजा आ गया।
ये ऐसी आग है जो गालिब साहब का मशहूर शेर है कि ये इश्क है ऐसी आतिश गालिब, जो लगाए न लगे और बुझाए न बने। ये आग, इस पे एक बहुत खूबसूरत शेर याद आया है कि आग ऐसी लगाई, ये इश्क नहीं आसान, बस इतना समझ लीजिए।
ये इश्क नहीं आसान, बस इतना समझ लीजिए।
एक आग का दरिया है और डूब के जाना है।
बर्फ सी गिर गई, काम ही कर गई, आग ऐसी लगाई मजा आ गया।
जाम में घोल कर हुस्न की मस्तियाँ,
जाम में घोल कर हुस्न की मस्तियाँ,
चांदनी मुस्कुराई मजा आ गया।
चांदनी मुस्कुराई मजा आ गया।
चांदनी मुस्कुराई, चांदनी मुस्कुराई, फिर मुस्कुरा के प्यार से देखा मेरी तरफ, फिर एक जरा सी बात पे रहना पड़ा मुझे। फिर मुस्कुरा के प्यार से देखा मेरी तरफ, फिर एक जरा सी बात पे रहना पड़ा मुझे। यानी वो रूठ गए थे, फिर मान गए, फिर रूठ गए, फिर ब्रेकअप हो गया, उसके बाद फिर मुस्कुरा के देख रहे हैं। तो एक शक वाली बात है कि ये क्या हुआ। फिर मुस्कुरा के प्यार से देखा मेरी तरफ, फिर एक जरा सी बात पे रहना पड़ा मुझे, और बदनाम करने वालों का एहसान मंद हूँ। बदनाम करने वालों का एहसान मंद हूँ, क्योंकि अपनी जुबान से कुछ भी ना कहना पड़ा मुझे। चांदनी मुस्कुराई मजा आ गया,
चांदनी मुस्कुराई मजा आ गया।
चांद के साए में ऐ मेरे साकिया,
चांद के साए में ऐ मेरे साकिया,
तूने ऐसी पिलाई मजा आ गया।
चांद के साए में ऐ मेरे साकिया, तूने ऐसी पिलाई मजा आ गया।
बेहिजाबान वो सामने आ गए,
बेहिजाबान वो सामने आ गए,
और जवानी जवानी से टकरा गई,
और जवानी जवानी से टकरा गई।
आंख उनकी लड़ी यूं मेरी आंख से,
आंख उनकी लड़ी यूं मेरी आंख से,
देख कर ये लड़ाई मचा गया।
आंख उनकी लड़ी यूं मेरी आंख से, देख कर ये लड़ाई बजा गया।
उधर भाई साहब एक बैठे हुए हैं जो तालियां बजा रहे हैं, और शूटिंग उनके लिए एक शेर कहना चाहूंगा कि नजर नजर से लड़ी है, जरा ठहर जाओ, कमान छूट पड़ी है, जरा ठहर जाओ। शुक्रिया। और किसी से मिलने का वादा हो तो चले जाना, तमाम रात पड़ी है, जरा ठहर जाओ।
आँख उनकी लड़ी यूं मेरी आँख से, देख कर ये लड़ाई मजा आ गया।
आँख में थी हया हर मुलाकात पर,
आँख में थी हया हर मुलाकात पर,
सुर्ख आरिज हुए वस्ल की बात पर,
सुर्ख आरिज हुए वस्ल की बात पर,
उसने शर्मा के मेरे सवालात पर,
उसने शर्मा के मेरे सवालात पर
ऐसी गर्दन झुकाई मजा आ गया।
उसने शर्मा के मेरे सवालात पर ऐसी गर्दन झुकाई मजा आ गया।
उसने शर्मा के मेरे सवालात पर मैंने पूछा, मेरे सवालात जरा गौर से समाप्त फरमाइए कि मैंने पूछा कि कत्ल कीजिएगा, हंस के कहने लगे कि आंखों से, और इतना कहते ही कत्ल कर डाला उसने आंखें मिला के आंखों से।
उसने शर्मा के मेरे सवालात पर ऐसे गर्दन झुकाई मजा आ गया।
उसने शर्मा शर्मा के,
शर्मा शर्मा के उसने, शर्मा शर्मा के उसने, शर्मा शर्मा के
मेरे सवालात पर मैंने पूछा कि कल शब कहाँ थे, मैंने पूछा कि कल शब कहाँ थे, पहले शर्माए फिर हंस के बोले, आप वो बात क्यों पूछते हो जो बताने के काबिल नहीं है।
उसने शर्मा के मेरे सवालात पर।
एक और शेर शर्मा जी के लिए याद आया है, उसमें शर्मा की जब ये तकरार चल रही है तो एक शेर शर्मा जी के लिए भी कहना ज़रूरी है कि हमें मालूम है आप क्यों चश्मा लगाते हैं, हमें मालूम है आप क्यों चश्मा लगाते हैं। और चोरी तो हर कोई नहीं करते, मगर वो जो चोरी होती है, जिसे आपने जिस किसी का भी दिल चुराया है उन्हीं से पूछिए कि हमें मालूम है आप क्यों चश्मा लगाते हैं, कि यह है काम कुछ ऐसा जो आंखें चुराते हैं।
उसने शर्मा के मेरे सवालात पर ऐसी गर्दन झुकाई मजा आ गया।
उसने शर्मा के मेरे सवालात। मोहब्बत में किया वादा मुझे सच्चा नहीं लगता, मोहब्बत में किया वादा मुझे सच्चा नहीं लगता। तुझे देखा है जब से दूसरा अच्छा नहीं लगता, तुझे देखा है जब से दूसरा अच्छा नहीं लगता। वो मेरा कुछ नहीं लोगों मगर फिर भी ना जाने क्यों, मेरा कुछ नहीं लोगों मगर जाने।
ये मेरे फर्जंद हैं फराज खान वारसी, एक बार हिम्मत अफजाई के लिए तालियां बजा दीजिए।
मोहब्बत में किया वादा मुझे सच्चा नहीं लगता, मोहब्बत में किया वादा मुझे सच्चा नहीं लगता। तुझे देखा है जब से दूसरा अच्छा नहीं लगता, तुझे देखा है जब से दूसरा अच्छा नहीं लगता। वो मेरा कुछ नहीं लोगों मगर फिर भी ना जाने क्यों, वो मेरा कुछ नहीं लोगों मगर फिर भी ना जाने क्यों। उसे देखूं किसी के साथ तो अच्छा नहीं लगता।
उसने शर्मा के मेरे सवालात पर
गर्दन झुकाई मजा आ गया।
रेत ही रेत थी मेरे दिल में भरी,
रेत ही रेत थी मेरे दिल में भरी।
प्यास ही प्यास थी जिंदगी है मेरी,
प्यास ही प्यास थी जिंदगी है मेरी।
आज सहराओं में इश्क के गाँव में,
आज सहराओं में इश्क के गाँव में।
अरे आज सहराओं में, बल्कि ये कहना अच्छा रहेगा, आज सहराओं में IITH के गाँव में बारिशें गिर के छाई
मजा आ गया। आज सहराओं में इश्क के गाँव में बारिशें गिर के छाई मजा आ गया।
बारिशें गिर के छाई मजा आ गया, बारिशें गिर के छाई। यानी कोई ऐसे तो होंगे जो किसी के इंतजार में होंगे, उनके लिए ये शेर है कि वो आ रहे हैं, आते हैं, आ रहे होंगे, ऐसे बेकार ख्यालात ने दिल तोड़ दिया। और हम तो समझे थे कि बरसात में बरसेगी शराब, आई बरसात तो बरसात ने दिल तोड़ दिया।
आज सहराओं
में इश्क के गाँव में बारिशें गिर के छाई मजा आ गया।
गरे गरे गबा गा बनी बनी दर निनि दर निनि दर निनि दर निनि दर वी दर 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 गा गा बा बनी नि दर दर नि दर गा गा बा बनी नि दर दर नि दर गा गा बा बनी नि दर बा बनी नि दर बा बनी नि दर निनि दर निनि दर दर
आज सहराओं में इश्क के गाँव में बारिशें गिर के छाई मजा आ गया
ओ मेरे रश पे पवन शुक्रिया थैंक यू पिया इन नैनन में सो पलक ढांप तो हेलूं पिया इन नैनन में सो पलक ढांप तो हेलूं ना मैं देखूं और को ना तो है देखन दूं नील गगन से भी परे सैया जी का गांव नील गगन से भी परे सैया जी का गांव दर्शन मन की कामना पत रखियो हे राम जब से राधा श्याम के नैन हुए हैं चार श्याम बने हैं राधिका और राधा बन गई श्याम सांसों की माला पे सिमरू मैं पी का नाम
सांसों की माला पे सिमरू मैं पी का
नाम
सांसों की माला पे सिमरू मैं पी का
यही मेरी बंदगी है यही मेरी पूजा सांसों
की माला पे सिमरू मैं पी का
एक का साजन मस्जिद में एक का प्रीतम मंदिर में और मैं बस सांसों
की माला पे सिमरू
मैं पी का नाम सांसों की माला पे सांसों की माला पे
माला पे
सांसों की माला पे
सांसों की माला पे
सांसों की माला पे सिमरू मैं पी का नाम
सांसों की माला पे सिमरू मैं पी का सांसों की माला पे सिमरू मैं
ओ पपी है तू ये क्यों आंसू बहाता है ज़बां पर तेरी पी पी किस लिए रह रह के आता है जो खुद ही जल रहा हो और क्यों उसको जलाता है सदाए दर्द गम क्यों दर्दमंदों को सुनाता है काटू तोरी चोंच पापी हरा दारू तो पे लोन मैं पी की पी मोरा तू पी का है कौन
सांसों की माला पे
मैं पी का ओ प्रेम के रंग में ऐसी डूबी
प्रेम के रंग में ऐसी डूबी प्रेम के रंग में
ऐसी डूबी
प्रेम के रंग में ऐसी डूबी प्रेम के रंग में
डूबी खुसरो दरिया प्रेम का सो उल्टी वा की धार
खुसरो दरिया प्रेम का सो उल्टी वा की धार
जो उबरा सो डूब गया जो डूबा हुआ पार
ऐसी डूबी प्रेम के रंग में ऐसी डूबी
बन गया एक हीरो
बन गया एक हीरो
प्रेम की माला जपते आप बनी मैं शाम
सांसों की माला पे सिमरो मैं बेगाना
प्रीतम का कुछ दोष नहीं है
प्रीतम का कुछ दोष नहीं है
वो तो है निर्दोष
वो तो है निर्दोष
प्रीतम का कुछ दोष नहीं है वो तो है निर्दोष अपने आप से बातें करके हो गई मैं बदनाम
सांसों की माला पे सिमरो मैं बेगाना सांसों की माला
प्रीतम का कुछ दोष नहीं है वो तो है निर्दोष क्योंकि एक फारसी का बहुत खूबसूरत शेर याद आया है जिसकी मौजू ये है कि बेजुर्म खता कत्लम ए नाज बुता कर दी खुद तेग जदी बरमन नामे दिगरा कर दी यानी बिना जुर्म के मुझे कत्ल कर दिया उस नाज बुता यानी खूबसूरत मूरत ने और खुद मुझे कत्ल किया नाम दूसरों का रखा यानी प्रीतम तो निर्दोष है कि जमानत तुमने ली है हश्र में आलम पनाही की
जमानत तुमने ली है हश्र में आलम पनाही की
तुम्हारा नाम लेना ही सनद है बेगुनाही की
प्रीतम का कुछ
दोष नहीं है
वो तो है निर्दोष
अपने आप से बातें करके हो गई मैं बदनाम
सांसों की माला पे
सिमरो मैं बेगाना गाने दारे नी रे गा रे रे सा सा पा म ग म ग ग रे गा रे रे सा नि द प प द सा रे सा रे म ग प म ध प म द नि सा रे दा नि द दा नि प म प ध म प ध म प द ग म रे नि रे सा
सांसों की माला पे सिमरो मैं बेगाना
प्रेम पियाला जब से पिया है
प्याला जब से पिया है
जी का है ये हाल
का है ये
अंगारों पर नींद आ जाए कांटों पर आराम
सांसों की माला पे सिमरो मैं बेगाना सांसों की माला पे सिमरो मैं बेगाना
अंगारों पर नींद आ जाए कांटों पर आराम उम्र जलवों में बसर हो ये जरूरी तो नहीं हर शबे गम की सहर हो ये जरूरी तो नहीं और सबकी साकी पे नजर हो ये जरूरी है मगर सब पे साकी की नजर हो ये जरूरी तो नहीं और नींद तो दर्द के बिस्तर पे भी आ सकती है उनके आगोश में सर हो ये जरूरी तो नहीं अंगारों पर नींद आ जाए
कांटों पर आराम सांसों की माला पे सिमरो मैं बेगाना
जीवन का श्रृंगार है प्रीतम
जीवन का श्रृंगार है प्रीतम
मांग का है सिंदूर
शुक्रिया। अभी एक फरमाइश तो है शर्मा जी की तरफ से, मगर मैं अपनी तरफ से एक गज़ल सुनाना चाहता हूँ। बहुत खूबसूरत आजकल गीत ट्रेंडिंग में है, और भाई साहब जो बैठे हुए चुटकी बजा की मज़ा ले रहे हैं, उनसे गुजारिश करूँगा आप लोग ज़रा आगे आके बैठिए। आई कांटेक्ट में थोड़ा सा आसानी हो जाएगी, और जो ऊपर बैठे हुए वो लोग भी प्लीज़ नीचे आ चाहिए। दिखाई नहीं दे रहे आप लोग, एकदम अंधेरा है। तो इनके बालों को देखते हुए एक शेर पेश करता हूँ कि काली जुल्फें नशीली आंखें हसीन चेहरा गुलाब जैसा।
काली जुल्फें नशीली आंखें हसीन चेहरा गुलाब जैसा।
अदा अदा से छलक रहा है शबाब तेरा शराब जैसा। काली
काली जुल्फों के बंदे न डालो,
काली काली जुल्फों के बंदे न डालो,
हमें जिंदा रहने दो ऐ हुस्न वालों।
काली काली जुल्फों के बंदे न डालो, हमें जिंदा रहने दो ऐ हुस्न वालों,
काली काली जुल्फों के बंदे न डालो। आप इस तरह से होश उड़ाया न कीजिए,
आप इस तरह से होश उड़ाया न कीजिए,
तू बन संवर के सामने आया न कीजिए।
काली काली जुल्फों के बंदे न डालो, हमें जिंदा रहने दो ऐ हुस्न वालों।
जो नजर आर पार हो जाए,
जो नजर आर पार हो जाए,
वही दिल का करार हो जाए,
वही दिल का करार हो जाए।
अपनी जुल्फों का डाल दो साया,
अपनी जुल्फों का डाल दो साया,
जिंदगी खुशगवार हो जाए।
काली जुल्फों के बंदे न डालो, हमें जिंदा रहने दो ऐ हुस्न वालों।
जंजीर में जुल्फों की फंस जाने को क्या कहिए,
जंजीर में जुल्फों की फंस जाने को क्या कहिए,
दीवाना मेरा दिल है,
दीवाना मेरा दिल है,
दीवाने को क्या कहिए। बस काली
काली जुल्फों के बंदे न डालो, हमें जिंदा रहने दो ऐ हुस्न वालों। काली काली जुल्फों के
न छेड़ो हमें हम सताए हुए हैं,
हम सताए हुए हैं,
बहुत जख्म सीने पे खाए हुए हैं,
जख्मों सीने में खाए हुए हैं,
सितमगर हो तुम खूब पहचानते हैं,
सितमगर हो तुम खूब पहचानते हैं,
तुम्हारी अदाओं को हम जानते हैं,
तुम्हारी अदाओं को हम जानते हैं।
दगाबाज हो तुम सितम ढाने वाले,
दगाबाज हो तुम सितम ढाने वाले,
फरेबे मोहब्बत में उलझाने वाले,
फरेबे मोहब्बत में उलझाने वाले।
ये रंगी कहानी तुम्हीं को मुबारक,
ये रंगी कहानी तुम्हीं को मुबारक,
तुम्हारी जवानी तुम्हीं को मुबारक,
तुम्हारी जवानी तुम्हीं को मुबारक।
हमारी तरफ से निगाहें हटा लो, हमें जिंदा रहने दो
ऐ हुस्न वालों, काली काली जुल्फों के बंदे न डालो, हमें जिंदा रहने दो ऐ हुस्न वालों। काली काली जुल्फों के बंदे न डालो, हमें जिंदा रहने दो ऐ हुस्न वालों।
मस्त आंखों की बात चलती है,
मस्त आंखों की बात चलती है,
मैं कशी करवटें बदलती है,
कशी करवटें बदलती है,
बन संवर के वो जब निकलते हैं,
संवर के वो जब निकलते हैं,
दिलकशी साथ साथ चलती है,
दिलकशी साथ साथ चलती है।
अरे हार जाते हैं जीतने वाले, नजर ऐसी चाल चलती है,
वो नजर ऐसी चाल चलती है।
हार जाते हैं जीतने वाले, वो नजर ऐसी चाल चलती है कि ये थोड़ा सा एक्सपीरियंस है इसलिए ये शेर याद आया है। हार जाते हैं जीतने वाले। अब मेरी शादी को 27 साल हो गए माशाल्लाह। तो एक हार होती है, एक जीत भी होती है कि आओ सखी मिल चौसर खेलें, पी अपने के संग, जीत गई तो पिया मिलेंगे, हारी तो पी के संग। और ये तो इनकी तरफ से हो गया। अब जेंट्स की तरफ से भी कुछ बोलना है कि हार और जीत क्या होती है। मोहब्बत हो अगर सच्ची तो ऐसे दिन भी आते हैं, मोहब्बत के खिलाड़ी हार कर भी जीत जाते हैं। वो अपने नाज बरदारों के खुद भी नाज उठाते हैं। और हार के जीतने वाले को क्या कहते हैं? हाँ, मोहब्बत के खिलाड़ी हार कर भी जीत जाते हैं। वो इतना जान कर ही जान की बाजी लगाते हैं।
हार जाते हैं जीतने वाले,
हार जाते हैं जीतने वाले।
वो नजर ऐसी चाल चलती है,
वो नजर ऐसी चाल चलती है।
जब हटाते हैं रुख से जुल्फों को,
जब हटाते हैं रुख से जुल्फों को,
चांद हंसता है रात ढलती है,
चांद हंसता है रात ढलती है।
क्या कयामत है उनकी अंगड़ाई,
क्या कयामत है उनकी अंगड़ाई।
जैसे नागन कोई मचलती है, काली काली जुल्फों के बंदे न डालो,
हुस्न वालो,
काली काली जुल्फों के संभालो जरा अपना आंचल गुलाबी,
संभालो जरा अपना आंचल गुलाबी।
दिखाओ ना हंस हंस के आंखें शराबी,
दिखाओ ना हंस हंस के आंखें शराबी।
सुलूक इनका दुनिया में अच्छा नहीं है,
दिल का दुनिया में अच्छा नहीं है।
हसीनों पे हमको भरोसा नहीं है,
हसीनों पे हमको भरोसा नहीं है।
उठाते हैं नजरें तो गिरती है बिजली,
उठाते हैं नजरें तो गिरती है बिजली।
अदा जो भी निकली कयामत ही निकली,
अदा जो भी निकली कयामत ही निकली।
जहां तुमने चेहरे से आंचल हटाया,
जहां तुमने चेहरे से आंचल हटाया,
वहीं अहले दिल को तमाशा बनाया,
वहीं अहले दिल को तमाशा बनाया।
खुदा के लिए हम पे डोरे न डालो, हमें जिंदा रहने दो ऐ
हुस्न वालो,
काली काली जुल्फों के बंदे
न डालो, हमें जिंदा रहने दो। हुस्न वालो,
काली काली
जुल्फों के बंदे न डालो, हमें जिंदा रहने दो।
शुक्रिया। कुछ फरमाइश? हाँ बोलिए। अच्छा आप जा रहे हैं क्या? अभी जो शेर बोला था फिर दोबारा नहीं, चलिए ठीक है, अब आगे कलाम पेश करते हैं। साकी की हर निगाह पे बल खा के पी गया, लहरों से खेलता हुआ लहरा के पी गया। ऐ रहमते तमाम मेरी हर खता मुआफ, मैं इंतहाए शौक से घबरा के पी गया। पास रहता है दूर रहता है, कोई दिल में जरूर रहता है। जब से देखा है उनकी आंखों को, हल्का हल्का सुरूर रहता है। ये
जो हल्का हल्का सुरूर है, ये जो
हल्का हल्का सुरूर है, ये जो हल्का हल्का
सुरूर है,
हल्का हल्का
सुरूर है,
हल्का सुरूर है।
ये जो
हल्का हल्का सुरूर है,
ये तेरी नजर का कसूर है,
तेरी नजर का कसूर है,
ये शराब पीना सिखा दिया,
तेरी नजर का कसूर है, शराब पीना सिखा दिया, तेरी नजर का कसूर है, शराब पीना
ये शराब पीना सिखा दिया, तेरी नजर
का कसूर है, कि शराब पीना सिखा दिया।
ये जो हल्का हल्का सुरूर है,
जो हल्का हल्का सुरूर है,
ये तेरी नजर का कसूर है,
तेरी नजर का कसूर है,
ये शराब पीना सिखा दिया,
शराब पीना सिखा दिया।
तेरे प्यार ने, तेरी चाह ने, तेरी बहकी बहकी निगाह ने मुझे एक शराबी बना दिया,
तेरी बहकी बहकी निगाह ने मुझे शराबी बना दिया।
शराब कैसी खुमार कैसा,
शराब कैसी खुमार कैसा,
ये सब तुम्हारी नवाजिशें हैं,
ये सब तुम्हारी नवाजिशें हैं।
पिलाई है किस नजर से तूने,
मिलाई है किस नजर से तूने,
कि मुझको अपनी खबर नहीं है,
तेरी बहकी बहकी निगाह ने मुझे शराबी बना दिया।
सारा जहान मस्त 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 मस्त, सारा जहान मस्त 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 मस्त,
सारा जहान मस्त,
जहाँ का निजाम मस्त,
सारा जहान मस्त, जहाँ का निजाम मस्त,
दिन रात मस्त, दिन मस्त रात मस्त, शहर मस्त शाम मस्त,
मस्त रात मस्त, शहर मस्त, शाम मस्त,
है तेरी चश्मा मस्त से हर खास आम मस्त,
है तेरी चश्मे मस्त से हर खासो आम मस्त,
हो मस्त शीशा मस्त सुबह मस्त जाम मस्त,
हो मस्त शीशा मस्त, सुबह मस्त, जाम मस्त।
यूं तो साथी हर तरह की तेरे मैं खाने में है,
तो सभी हर तरह की तेरे पैमाने में है,
वो भी थोड़ी सी जो इन आंखों के पैमाने में है,
थोड़ी सी कोई आंखों के पैमाने में है।
ओ सब समझता हूँ तेरी ईश्वरी है साथी,
समझता हूँ तेरी ईश्वरी है साथी,
काम करती है नजर नाम है पैमानी का,
तेरी बहकी बहकी निगाह ने मुझे शराबी बना दिया, तेरी बहकी बहकी निगाह ने मुझे शराबी बना दिया।
तेरा प्यार है मेरी जिंदगी,
तेरा प्यार है मेरी जिंदगी, तेरा प्यार है मेरी जिंदगी,
ओ बस मेरी जिंदगी तेरा प्यार है,
बस मेरी जिंदगी तेरा प्यार है, बस मेरी जिंदगी तेरा प्यार है, बस मेरी
जिंदगी जिंदगी मेरी
जिंदगी तेरा प्यार है, बस मेरी जिंदगी तेरा प्यार है,
मेरी मेरी जिंदगी 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 मेरी
जिंदगी तेरा प्यार है, बस मेरी जिंदगी तेरा प्यार।
कभी खुशी से खुशी की तरफ नहीं देखा,
कभी खुशी से खुशी की तरफ नहीं देखा,
तुम्हारे बाद किसी की तरफ नहीं देखा,
बस मेरी जिंदगी तेरा प्यार है, बस मेरी जिंदगी तेरा प्यार।
इश्क है मेरी बंदगी,
तेरा इश्क है मेरी बंदगी,
जो तेरी खुशी वो मेरी खुशी,
वो तेरी खुशी वो मेरी खुशी,
ये मेरे जुनू का है मौजूदा,
जुनू का है मौजूदा,
जहाँ अपने सर को झुका दिया,
अपने सर को झुका लिया,
वहाँ मैंने काबा बना दिया,
अपने सर को झुका लिया, वहाँ मैंने
मेरे बाद किसको सताओगे,
मेरे बाद किसको सताओगे, मेरे बाद किसको सताओगे, मेरे बाद
ओ किस किस को सताओगे मेरे बाद, किस किस को सताओगे मेरे बाद, ओ किस किस को सताओगे मेरे बाद, किस किस को सताओगे
मेरी वफाएं याद करोगे,
मेरी वफाएं याद करोगे,
रोगे फरियाद करोगे,
रोगे फरियाद करोगे,
मुझको तो बर्बाद किया है,
मुझको तो बर्बाद किया है,
और किसे बर्बाद करोगे,
और किसे बर्बाद करोगे,
दिल जलों से दिल लगी अच्छी नहीं,
दिलों से दिल लगी अच्छी नहीं,
रोने वालों से हंसी अच्छी नहीं,
रोने वालों से हंसी अच्छी नहीं,
दिल लगी में दिल गया,
दिल लगी में दिल गया,
ओह मेरा दिल गया दिल गया दिल गया,
मेरा दिल गया दिल गया दिल गया, मेरा दिल
दिल दिल दिल दिल दिल दिल दिल दिल गया दिल गया दिल गया,
मेरा दिल गया दिल गया दिल गया,
ओ दिल मेरा मुझसे लेकर कहते हैं वो,
मेरा मुझसे लेकर कहते हैं वो,
जाओ रास्ता लो तुम्हारा कुछ नहीं, मेरा दिल गया दिल गया दिल गया,
मेरा दिल गया दिल गया दिल गया, मेरा दिल गया दिल गया दिल गया, मेरा
आंख से छुप के दिल में बैठे हो, आए कैसी ये पर्दादारी है,
आंख से छुप के दिल में बैठे हो, हाय कैसी ये पर्दादारी है,
और तोड़ो दिल मेरा शौक से तोड़ो,
तोड़ो दिल मेरा, तोड़ो दिल मेरा शौक से तोड़ो,
चीज मेरी नहीं तुम्हारी है,
मेरा दिल गया दिल गया दिल गया, मेरा दिल गया दिल गया दिल गया, मेरा दिल गया दिल गया दिल गया,
ओह दिल लगी में दिल गया,
दिल लगी में दिल गया,
दिल लगाने का नतीजा
मिल गया,
दिल लगाने का नतीजा मिल गया,
क्यों हंसते हो तुम्हें क्या मिल गया,
क्यों हंसते हो तुम्हें क्या मिल गया,
मैं तो रोता हूँ कि मेरा दिल गया,
मेरे बाद किसको सताओगे, मेरे बाद किसको सताओगे,
मेरे बाद किसको सताओगे,
मेरे बाद किसको सताओगे,
मुझे किस तरह से मिटाओगे,
मुझे किस तरह से मिटाओगे,
कहाँ जाके तीर चलाओगे,
आगे तीर चलाओगे,
मेरी दोस्ती की बलाएं लो,
मेरी दोस्ती की बलाएं लो,
मुझे हाथ उठाकर दुआएं दो,
मुझे हाथ उठाकर दुआएं दो,
तुम्हें एक कातिल बना दिया,
हाथ उठाकर दुआएं दो, तुम्हें एक कातिल बना दिया, हाथ उठाकर दुआएं दो, तुम्हें एक कातिल बना दिया,
जो हल्का हल्का
सुरूर है। शुक्रिया, थैंक यू।
आपकी लिस्ट फॉलो कर रहे हैं जैसा पहले से, क्या बात है, इससे बहुत आसानी हो जाती है। पब्लिक का माइंडसेट तो समझ में आ गया कि हाँ हल्के हल्के शुरू पे ज़्यादा रिस्पॉन्स मिला।
लगे नहीं महाराज यारे हो, तारे बिना लगे नहीं महाराज यारे हो, नैना निखारी कैसा जादू किया रे,
तारे बिना लगे नहीं महाराज यारे हो,
तारे बिना लगे नहीं महाराज यारे
ओ पिया रे पिया रे पिया रे
तारे बिना लगे नहीं महाराज यारे हो,
बाबा नी दा बाबा गरे गरे रे सा, बाबा गरे सा, बाबा नी दा बाबा गरे गरे रे सा, थारे बिना मोहे चैन ना आवे,
तारे बिना मोहे चैन ना आवे,
ये धक 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 मारा जी घबरावे,
धक 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 मारा जी घबरावे,
बोले बांसुरिया सुन ले सवारिया,
बोले बांसुरिया सुन ले सवारिया,
बोले बांसुरिया सुन ले सवारिया, थारे बिना मोहे कुछ नहीं भावे,
पिया रे पिया रे पिया रे पिया रे,
थारे बिना लगना ही महाराज यारे हो,
तारे बिना लगे नहीं महाराज यारे
ओ प्यार की कलियां कब की रखियां,
प्यार की कलियां कब की रखिया,
रावा तक तक मैं फिर थकियां,
तक तक
ओ मैं थक गईया,
सांझ सवेरे देखन लागे,
आज सवेरे
देखन लागे,
थारी सूरतिया मारी अखियां,
पिया रे पिया रे
पिया रे
हो, तारे बिना लागे नहीं महाराज यारे हो,
बिना लगे नहीं महाराज यारे
थैंक यू। रब की कवाली है
इश्क कोई
दिल की दीवानी है,
इश्क कोई महकी सी प्याली है,
इश्क कोई
सुबह की लाली है,
इश्क
गिरता सा झरना है,
इश्क कोई
उठता सा कलमा है,
इश्क कोई
आंखों में दिखता है,
इश्क कोई
सांसों में लिपटा है,
इश्क कोई
मेरे दिल को तुझा से जुदा कर दे,
मेरे दिल को तुझसे जुदा कर दे,
बस यूं ही सुबह सोचूं तुझे तो शाम है, मंजिलों पे अब तो मेरी एक ही तेरा नाम है, मंजिलों पे अब तो मेरी एक ही तेरा नाम है, तेरी आग में है जलते कोयलों से हीरा बनते, तेरी आग में है जलते कोयलों से हीरा बनते, ख्वाबों से आगे चल के है तुझे पाना, तेरे वास्ते इश्क सूफियाना मेरा, इश्क सूफियाना मेरा, इश्क सूफियाना तेरे वास्ते मेरा, इश्क सूफियाना मेरा, इश्क सूफियाना मेरा, इश्क सूफियाना। साथ साथ चलते चलते हाथ छूट जाए ना, साथ साथ चलते चलते हाथ छूट जाए ना, ऐसी राहों में मिलो ना, साथ साथ चलते चलते हाथ छूट जाए ना, ऐसी राहों में मिलो ना, बातें बातें करते करते रात कट जाएगी, ऐसी रातों में मिलो ना, क्या हम हैं क्या रब है, क्या रब है, जहाँ तू है वहीं सब है, जहाँ तू है वहीं सब है, मेरे लब मिले मेरे लब खिले अब दूर क्या है जाना, तेरे वास्ते मेरा इश्क सूफियाना मेरा, इश्क सूफियाना मेरा, इश्क सूफियाना तेरे वास्ते मेरा, इश्क सूफियाना मेरा, इश्क सूफियाना मेरा, इश्क सूफियाना। ओ कवाली है इश्क कोई दिल की दीवाली है, इश्क कोई महकी सी प्याली है, इश्क कोई सुबह की लाली है, इश्क गिरता सा झरना है, इश्क कोई उठता सा कलमा है, इश्क कोई आंखों में दिखता है, इश्क कोई सांसों में लिपटा है, इश्क कोई मेरे दिल को तुझा से जुदा कर दे, तुझा से जुदा कर दे, बस यूं ही तू मुझको फना कर दे, यूं ही तू मुझको फना कर दे, मेरा हाल तू मेरी चाल तू बस कर दे आशिकाना, तेरे वास्ते मेरा इश्क सूफियाना मेरा, 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 इश्क सूफियाना। शुक्रिया, थैंक यू। अच्छा जी, थैंक यू, वेलकम सर। एक शेर आप लोगों के आने पे बोल के फिर ये लास्ट कलाम में पेश करता हूँ कि वो आए हमारी महफिल में, खुदा की कुदरत है, कभी हम उनको कभी अपनी महफिल को देखते हैं। शुक्रिया। या गरीब नवाज, या गरीब नवाज, या गरीब नवाज, ख्वाजा जी, ख्वाजा, ख्वाजा जी, या मोइनुद्दीन ख्वाजा जी या गरीब नवाज ख्वाजा मेरे ख्वाजा
ख्वाजा मेरे ख्वाजा ख्वाजा ख्वाजा
दिल में समा जा
समा जा
ओ ख्वाजा मेरे ख्वाजा
ख्वाजा ख्वाजा
दिल में समा जा
समा जा समा जा
शाहों का शाह तू अली का दुलारा ख्वाजा मेरे ख्वाजा गगर रे गगर रे गगर रे गा दिल में समा जा गगर रे गगर रे गा बेकसों की तकदीर तूने है सवारी
सवारी सवारी हो बेकसों की तकदीर तूने है सवारी सवारी सवारी
ख्वाजा मेरे ख्वाजा
ख्वाजा दिल में समा जा समा जा समा जा शाहों का शत्रु अली का दुलारा
तेरे दरबार में ख्वाजा
तेरे दरबार में ख्वाजा
नूर को है देखा
है देखा
तेरे दरबार
में ख्वाजा
सर झुकाते हैं औलिया
झुकाते हैं औलिया
तू है हिंदल वाली ख्वाजा रुतबा है तेरा प्यारा
दल बली ख्वाजा रुतबा है तेरा प्यारा
चाहने से तुझको ख्वाजा जी मुस्तफा को पाया ख्वाजा मेरे ख्वाजा
ख्वाजा
दिल में समा जा
समा जा समा जा
ओ शाह का शतू अली का दुलारा ख्वाजा मेरे ख्वाजा
मेरे ख्वाजा
दिल में समा जा
समा जा
हो बेकसों की तकदीर तूने है सवारी तूने है सवारी
बेकसों की तकदीर
तूने है सवारी सवारी सवारी
ख्वाजा मेरे ख्वाजा
है मेरे पीर का सदका 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 मेरा मन है कली हर बला हमारी आया है कुमार तेरा जितना भी इश्क करे बेशक कम है ये मेरे ख्वाजा
भी इश्क करे बेशक कम है ये मेरे ख्वाजा
तेरे कदमों को मेरे रहनुमा नहीं छोड़ना गवारा ख्वाजा मेरे ख्वाजा ख्वाजा मेरे ख्वाजा दिल में समा जा समा जा समा जा शाहों का शतू अली का दुलारा ख्वाजा मेरे ख्वाजा दिल में समा जा
दिल में समा जा
ओ बेकसों की तकदीर तूने है सवारी तूने है सवारी
बेकसों की तकदीर
तूने है
सवारी
सवारी सवारी ख्वाजा मेरे ख्वाजा
Thank you for that beautiful and soulful performance. It truly added a special dimension to our celebration.
It was truly delighting to listen to the music bearers of the गायकी of Delhi घराना। सुर और एहसास जब साथ आ जाएं तो महफिल यादगार बन जाती है और इस महफिल को यादगार बनाने के लिए तहे दिल से आपका शुक्रिया अदा करते हैं।
Let us honor Vasid Brothers and team for carrying forward such a rich and divine musical heritage and for enriching this evening with their music.
Now I request Professor Chandrasekhar Sharma and Padma Shri Professor Ashutosh Sharma to come on to the stage to felicitate the Varsi brothers and the team. Ladies and gentlemen, as we conclude this soulful segment, may the spirit of this evening stay with us. Here is to many more years of excellence, innovation, and togetherness. And we have final announcement to make. The tomorrow session will be starting at 8:45 sharp, 8:45 a.m. So be there on time, wearing the t-shirts that have been given to you, the conference t-shirts. Thank you one and all. The conference organizing team, please come on the stage and we'll have a group picture with the Varsi Brothers and team.